successfully ousted the foreign rulers from the Indian subcontinent in 1947. India's journey from the beginning of time is dotted with consequential
Hello MDS, hello Amartya, hello Dani ji. Can you hear?
Sriram. No, we are able to hear, but I think it may get broadcast there.
Yeah.
So we perhaps should not talk.
Ah.
It may start broadcast anytime.
थर्ड रो से चालू कर एक का प्रॉब्लम आ रहा है बाकी सारे ठंडी तो 70 उधर जो भी वो कम हियर
वीडियो दिए तो संदीप जी ने अभी
पॉइंट 6 में कलाम से
तो बड़ी यूज कम हियर कम
अब्दुल्ला
ये वहां पे तो करो ना ये वाला मिडिल रोज ठीक है नहीं
वो उसने फ्रीज का रखा बोल करूँ
बता दो ना चेंज कर दो ये लाइन मत बैठने देना
ये खड़े होंगे ना सर आ जाएगा वाली लाइन खाली करा दो तीन लाइन आगे की
ये
तीन लाइन आगे की यहाँ तक जब ये खड़े होंगे ना तो फिर सर आ जाएगा इनका
यहाँ पे नहीं बिठाने के तीन तीन रो आप तो
खाली कराओ
ये वाली रोज निकल ये वाली रोज छोड़ दीजिए
एक दिन तो बच्चे आगे बैठे
कैमरा सरस्वती बंदना क्या होता है
हेलो चेक म्यूजिक ऑफ कर दीजिए प्लीज
लाइक कर दे मैंने अच्छा लाइक देख लो
नमस्कार वी एक्सटेंड टू यू ऑल माननीय प्रधानमंत्री जी की सोच और अप्रोच इस देश की गरिमा को अमृतमयी बना रहे हैं Over 15,000 plus programs spread across 28 states, 8 union territories, and 150 plus countries globally. Azadi Ka Amrit Mahotsav is well placed to set off India into the Amrit Kal on the road to India at 2047. हमारी गौरवमयी संस्कृति हमें प्राचीन से जोड़े रखकर वर्तमान का जश्न मनाते हुए शिखरों पर खड़े नए नए भविष्य की ओर चलने को प्रेरित करती है हमारे देश के लिए सोने की जो चिड़िया की कहावत है जो सच्चाई है वो सिर्फ धन दौलत तक सीमित नहीं थी Several modern day concepts related to science, mathematics, metaphysics, astrology were conceived in the land that has served as the cradle of human civilization. अब समय आ गया है
कि हम अपने देश की उपलब्धियों को पहचानें और अपने देश के योगदान पर हम सब मिलकर गर्व करें। Presenting Dhara, an ode to Indian knowledge system, is a series of programs powered by lecture demonstrations. Today's event is dedicated to mathematics in India. आज हम मैथमेटिक्स में भारत के सदियों से चले आ रहे योगदान को और इंडियन मैथमेटिक्स के हिस्टोरियंस को नमन करते हैं। हमारा सौभाग्य है कि आज हमारे बीच में AICTE के मेंबर सेक्रेटरी आदरणीय प्रोफेसर राजीव कुमार उपस्थित हैं। आज के कार्यक्रम के वे चीफ गेस्ट हैं, उनका हम हृदय से स्वागत करते हैं। हम स्वागत करते हैं रिस्पेक्टेड प्रोफेसर के रामासुब्रमण्यम जी आपका और रिस्पेक्टेड प्रोफेसर पार्थसारथी मुखोपाध्याय जी आपका बहुत बहुत स्वागत है। मैं चाहूंगी यहाँ पर जितने भी जागरूक स्टूडेंट्स आए हुए हैं, बुद्धिजीवी आए हुए हैं, एक बार जोरदार तालियों से हमारे सभी अतिथियों का स्वागत करें। We begin any auspicious occasion with the lighting of the lamp. This is the tradition in our India. I would like to invite all our guests to please come up onto the stage and light the ceremonial lamp to begin this auspicious occasion. Asato ma sadgamya, tamaso ma jyotirgamya. Lead me from unreal to real, from the darkness of ignorance to the light of knowledge and wisdom.
श्री गुरुभ्यो नमः। हरिः ओम। गणानां त्वा गणपतिं हवामहे कविं श्रवस्तमम् ज्येष्ठराजं ब्रह्मणां ब्रह्मणस्पत आनशृण्वन्नोतिभिः सीदसादनम् देवीं वाचमजनयन्त देवास्तां विश्वरूपा पशवो सा नो मन्त्रेशमूर्जन्तुहाना धेनुरुवागस्मानुपसुष्टुतैतु कनिक्रतजनुषां प्रब्रुवाण इयरति वाचमरिते वनावम् सुमङ्गलश्च शकुने भवासि मातवा काचिदपि भाविष्व्या विदथ मातवा श्रियेण उदुवाधीन्मासु पर्णो मातवा विदधिषूमान् वीरो अस्ता पितृयामनुप्रदिशन् सुमङ्गलो भद्रवादी वदेहा अवक्रन्द दक्षिणतो गृहाणां सुमङ्गलो भद्रवादी शकुन्ते मानस्तेन ईशतमाघशं सोबृहद्वदेम विदधे सुवीराः सहनाववतु सहनौ भुनक्तु सह वीर्यङ्करवावहै तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
I invite Mr. Professor G.S. Murthy, National Coordinator, Indian Knowledge Systems
from Ministry of Education.
ओम पितृभ्यो नमः, गुरुभ्यो नमः, सभायै नमः, सभापतिभ्यश्च नमो नमः. A very good morning to all of you. Those who are joining us here in live in person, those who are joining us online, and those who are joining us through the YouTube live link as well. A very humble pranam to all of you and welcome to this great event, which commemorates the Jnana Ganga, essentially the Dhara, Jnana Dhara of this civilization, our Bharat civilization. This event is, as you know, this event is one of the first series of conferences that tries to show that the Jnana Ganga that was there in our India, essentially, is something that is continuing. It never stopped, has not stopped, it will not stop. It is a pravaha. Every day it reinvents itself, tries to basically, as the time progresses, as we say, it is Nityanutanam Chirapuratanam. It is Sanatana Dhara Jnana Pravaha. To commemorate that Jnana Dhara, we are having these series of conferences. We are beginning this with the Queen of all sciences, mathematics. Mathematics developed in India, and we have stellar group of scholars who have dedicated their lives to this pursuit of Vijnana. With that, the whole event was done with the Ministry of Culture, Ministry of Education, AICT, and the Indian Knowledge Systems Division of the Ministry of Education at AICT. And I welcome you all again to this event. And we'll begin off with the message from our Secretary, Ministry of Culture. Can you please play the message from our Secretary of Ministry of Culture, please? Thank you.
Namaskar. Azadi Ka Amrit Mahotsav is an initiative of the Government of India to celebrate and commemorate 75 years of progressive India and the glorious history of its people, culture and achievements. After a prolonged struggle spread over more than 100 years, on the back of several movements spearheaded by individuals and communities across the country, India successfully ousted the foreign rulers from the Indian subcontinent in 1947. India's journey from the beginning of time is dotted with consequential events, each of which added to the idea of India in a very unique and inevitable manner. For long, these events have been stories limited to folklore or a part of a historian's collective. It is time we walk down the annals of history and celebrate achievements which we didn't know belong to India. Claim our contribution which innately belongs to Bharat and take forward the continuum of India's contribution towards making the world a better place for humanity to thrive and coexist. Ministry of Culture are proud to announce Dhara, an ode to Indian knowledge systems, a series of programs powered by lecture demonstrations, celebrating and showcasing India's contribution and achievements across diverse fields. Our first event under this series is dedicated to India's contribution to mathematics through the ages. Mathematics in India has a very long, rich and hallowed history, starting from the most elementary thing in mathematics, namely the representation of numbers, through the way of expressing recursive relations, to arriving at the solutions of indeterminate equations, to the development of sophisticated techniques in handling the infinite and the infinitesimal. Indian mathematics have made remarkable contributions. Sulba Sutra, the oldest extant texts, explicitly state and make use of the so-called Pythagorean theorem, besides giving various interesting approximations to surds. Following this, Pingala's Chandrashastra, a text that deals with the prosody, lays foundations for various combinatorial techniques. By the time of Aryabhatta, the Indian mathematicians were fully conversant with most of the mathematics that we currently teach in our schools, which include the algorithms for extracting square root and cube root based on the decimal place value system. Unfortunately, most Indians are not aware of these remarkable contributions made by Indians to the development of mathematics. I thank Professor Sahasrabuddhe and the team at the AICTE for being our partners in today's event, and I hope Professor Manjul Bhargav's participation in today's event, alongside a stellar lineup of experts, will make today's sessions a catalyst to increased focus on such topics and conversations. Thank you all for being a part of Azadi Ka Amrit Mahotsav and giving impetus to all our efforts. Dhanyavad. Jai Hind.
Thank you so much, respected Secretary, Ministry of Culture. जैसा कि मैंने बताया कि हमारा सौभाग्य है कि आज हमारे बीच में AICTE के मेंबर सेक्रेटरी रिस्पेक्टेड प्रोफेसर राजीव कुमार उपस्थित हैं, जो कि आज के कार्यक्रम के चीफ गेस्ट हैं. आपने दिल्ली कॉलेज ऑफ इंजीनियरिंग से कंप्यूटर टेक्नोलॉजी एंड एप्लीकेशन से ME और IIT दिल्ली से PhD किया है. His areas of research interest are mathematical computing, software engineering, and image processing. He has published number of research papers in national and international journals and presented papers in India and abroad. हमारा निवेदन है आपसे कि कृपया आज के इस शुभ दिन शुरुआत में हम सबको संबोधित करें.
Thank you, madam. Namaskar. Honorable Secretary, Ministry of Culture, respected Bhargavaji, who is joining this program online from US, Professor K. Ramasubramaniam ji, Professor Mukhopadhyay, officers from Ministry of Culture, AICT, dear students, and those who are joining this program through online mode. Very good morning to each and everyone. First of all, I thank Ministry of Culture for giving us this opportunity to host this program in AICT campus. And as the nation is celebrating 75 years of independence, and in this series, various programs are being organized, and one important program from the Ministry of Culture is totally dedicated on mathematics, ancient mathematics. What we have done in the past, what our ancestors, everybody talks that mathematics has played an important role in Indian culture, but we have never documented it. And I think this is the first step by the Ministry of Culture, by the Government of India, where we are taking the work done in the ancient India to the world. I hope those who are joining this program, either through in person or through online mode, they will come to know and they will definitely start working, and they will also try to interact the researchers, those who have contributed already. I can see a galaxy of researchers, not only from India, from abroad, they are also participating in this program. So my request to each and everyone, please interact not only during this program and after this program. If you have interest in ancient mathematics, हम लोग पहले क्या थे मैथमेटिक्स में, हम उसको कैसे भूल गए, हम उसको कैसे रिवाइव कर सकते हैं, हमारे कंट्रीब्यूशन जो हमारे बुजुर्गों ने, हमारे एंसिस्टर्स ने किया है, उसको हम कैसे जन जन तक पहुंचा सकते हैं विश्व में, ये एक प्रयास है और इसमें आप सबका भागीदारी बहुत इंपॉर्टेंट है. मैं आशा करता हूं कि ये प्रोग्राम जो मैथमेटिक्स को डेडिकेटेड है वो एक बहुत सफल प्रोग्राम होने वाला है, और इस प्रोग्राम को आगे इस इनिशिएटिव को कैसे आगे ले जाना है, इसका एक रोड मैप मुझे लगता है कि इंडियन नॉलेज सिस्टम सेल जो एआईसीटी में स्थापित है वो एक रोड मैप जरूर बनाएंगे, और इसको कैसे आगे ले जाना है, आगे आगे क्या क्या प्रोग्राम करने, क्योंकि एक प्रोग्राम करने के बाद अगर हम इसको यहाँ छोड़ देते हैं तो शायद वो एक जस्टिस नहीं होगा. तो मेरे साथी आईकेएस में इंडियन नॉलेज सिस्टम आईआईसीटी में हैं, वो इस पे एक नोट लेंगे और इस प्रोग्राम को किस तरीके से हम लोग आगे ले जा सकते हैं, आगे किया जा सकता है, इसकी एक पूरी रूपरेखा तैयार करेंगे. इन्हीं शब्दों के साथ मैं आप सबका एक बार फिर से स्वागत करता हूं. पर्टिकुलरली जो हमारे छात्र कॉलेजेस और स्कूल से आए हैं, मैं समझता हूं सुबह के टाइम दिल्ली में ट्रैवल करना इतना आसान नहीं होता है, तो आपका भी मैं बहुत बहुत आभार प्रकट करता हूं कि आप लोग अपने स्कूल से यहाँ तक आए हैं, और आप यहाँ पर, मुझे लगता है कि आपको पूरा आनंद आने वाला है. आप समझ पाएंगे जो मैथमेटिक्स आप अपनी बुक्स में पढ़ते हैं, टेक्स्ट बुक में पढ़ते हैं, उसका भारत की जो हमारा इतिहास है उसमें किस तरीके से हमने उसको हमारे जो पूर्वज हैं उसको किस तरीके से आगे लेकर आए हैं, इसके महत्व को आप समझेंगे. इन्हीं शब्दों के साथ मेरा बहुत बहुत इस प्रोग्राम की सफलता के लिए मेरी बहुत बहुत शुभकामनाएं और नमस्कार. धन्यवाद.
Thank you so much, Professor Rajiv Kumar ji. हमारे बीच में रिस्पेक्टेड श्री रत्नेश झा ओएसडी कमेमोरेशन संस्कृति मंत्रालय भी उपस्थित हैं। आपका हम हृदय से स्वागत करते हैं। बहुत बहुत स्वागत आपका। तो अब हम सब ज्ञान गंगा में डुबकी लगाने के लिए तैयार हैं। Will be soon joined by the Professor Manjul Bhargav. Professor Manjul Bhargav is a Canadian-American mathematician and is Professor of Mathematics at Princeton University. आपको नंबर थ्योरम में नंबर थ्योरी में आपके योगदान के लिए जाना जाता है। आपको 2014 में फील्ड मेडल अवार्ड से नवाजा गया। According to the International Mathematical Union citation, he was awarded the prize for developing powerful new methods in the geometry of numbers. So may I now invite Professor Manjul Bhargav for his keynote address. He will be talking about the theme Beyond Zero, a survey of some of India's fundamental contributions to mathematics. He'll be joining us online.
नमस्कार, मेरी आवाज आ रही है? मेरी आवाज आ रही है? अभी एको आ रही है लेकिन अच्छा अब ठीक है। नमस्कार, अगर मेरी आवाज आ रही हो तो मैं आगे चलूं?
I'm sorry, we can listen to you.
You can hear me? You can hear me?
Please go ahead. Yeah. We all can listen to you. Please go
I
ahead.
hear an echo though. I hear an echo though. Is it okay now? Okay. You can hear me? Yeah? Okay, wonderful. Okay, well, thank you so much. Congratulations to India on this 75th year of independence. This is a wonderful occasion to celebrate and showcase India's cultural contributions to the world, and in particular in mathematics. And so what I thought I would do today is say a little bit about the contributions of India to mathematics that are not just the one that everyone knows, namely zero. So hopefully you can see my screen. So what I want to talk about today is beyond zero. We all know about zero as one of India's fundamental contributions to mathematics, but I want to talk about a survey of some of India's contributions that go beyond zero. The current reality, even after 75 years of independence, due to propagation of colonial era textbooks and writings, Indian roots of mathematics remain largely unknown to the general public. And so unfortunately, many of India's fundamental contributions to mathematics are generally not covered in school textbooks. I personally was lucky to have learned a lot about the mathematics of India as a child, because my grandfather, my Nanaji, was a Sanskrit scholar. And so much of what I learned about mathematics growing up was through what he and my mother taught me from the various copies of ancient works that were on Nanaji's shelves. But as I was learning these gems of Indian mathematics from these ancient works, I would then go to school in US and in India and learn different names, usually European names, for some of these fundamental mathematical objects and mathematical theorems that I had learned from these ancient Indian works. And I wondered, why is this the case, and what did all this mean? And of course, it means that we still have a colonial legacy that we are trying to get over. And decolonizing our textbooks is certainly one of the things we have to strive towards. But first we have to know what are the true contributions of India to mathematics. And so what I want to talk about today is 10 things, 10 contributions of India that I feel everyone should know, that should be in our textbooks, and that we should celebrate and be inspired by, and that the youth of India should be inspired by to reach new heights in mathematics. So first I'll start with a contribution that everyone does know. The concept of zero originating in India is of course well known. We've all seen the t-shirt that many Indians proudly wear saying, India's contribution to mathematics is zero. And sometimes some of these t-shirts even have a subtle subtitle saying, we always knew we were good for nothing. So while the statement about zero coming from India is true, when interpreted correctly, it's only one of a large number of fundamental contributions coming from India. Sorry, I'm hearing an echo again. Oh, great. So this pun, that India's contribution to mathematics is zero, well, that's true. The notion of zero does come from India. And this contribution of zero to mathematics is, of course, recognized and taught in schools around the world these days. But most of the other major contributions of India usually go completely unmentioned, even in schools in India. In fact, sometimes in India, even less is taught about the contributions of India than in other countries. And so today I want to point out some of these other fundamental discoveries beyond zero that were made in India that we all should know, and indeed that I feel should be taught in schools. So here's the famous t-shirt that I was referring to. Zero, India's contribution to the world of mathematics. We always knew we were good for nothing. I'm sorry, but the echo is back. So here are 10 non-zero Indian contributions to mathematics that everyone should know. So the 0th one is zero, but there are 10 more that I'd like to talk about today, briefly, a little bit about each one, so that everyone can go away knowing a list of 10 fundamental things that India discovered that I really feel everyone should know, that should be taught in school, and that are really appreciable by the public. One consequence of zero, and one use of zero, is of course the Indian numeral system, the Hindu numeral system, that we all use and the world uses to write numbers. There's also the Bodhayana Pythagoras theorem, that we all learn about the sides of a right triangle. There's the mathematics of language, originating in the work of Panini, modeling languages and modeling particularly the Sanskrit language. It's okay? You can hear me all right?
Hello. Yeah, it's fine. Please carry on.
Okay,
You're
thank
audible.
you.
Perfect.
Thank you. So there's the Indian numeral system. There's the Bodhayana Pythagoras theorem. There's the mathematics of language modeling, as in the work of Panini. The sine and cosine functions in trigonometry, the fundamental functions of trigonometry, also originate in India. The negative numbers, most people are not aware that we use negative numbers every day today, but they have their origins in the work of Brahmagupta. As our solutions to quadratic equations also have. The general quadratic formula, the solutions to Brahmagupta-Pell equations have their origins in the work of Brahmagupta. Then the binomial coefficients, the foundations of combinatorics, also have their origins in the work of Indian mathematicians and and poets, as do the numbers in the Virahanka Fibonacci sequence. Finally, the first error detecting and correcting codes have their origins in Indian works, and also the first exact formula for pi originates in the work of Madhava in the Kerala School of Mathematics. So I hope everyone goes away realizing that these are 10 fundamental contributions that originated in the Indian subcontinent. Okay, so before we move on to the 10 fundamental contributions and the non-zero contributions, I thought I'd say a little bit about what we mean when we say India's contribution to mathematics is zero. The way we write our numerals today, which are called the Indian numbers, which is called the Indian number system or the Hindu number system, comes from India. And it is perhaps India's greatest contribution to daily life, the way we write our numerals today. The ingenuity of the Indian number system is that any number, however large, can be written using only 10 symbols, namely 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0. No matter how large your number is, you can always write any number just using these 10 symbols. This is a vast improvement over other numeral writing systems that were used in other parts of the world, such as the Roman numerals, where to write larger and larger numbers, one needed to introduce more and more symbols. Whereas in the Indian numeral system, only 10 symbols are needed to write arbitrarily large numbers, any number. This remarkable Indian system of enumeration, which we use today to write any number with only finitely many symbols, is truly what has made all modern science and technological innovations possible. So what is the history of zero in the Indian number system? First of all, zero, the concept of zero was in the culture of India already for thousands of years. The concept of shunyata, of emptiness, of mind, experiencing emptiness, is a cornerstone of many of the Indian philosophical traditions. And so zero was already ingrained as a concept in the culture. And so that gave the right atmosphere to develop this incredible invention, the Indian number system. The first surviving reference that we have, it probably goes back well before this, the writing of this in this system. But the first surviving reference in which the Indian system of enumeration is used is in what's called the Bakshali manuscript, which goes back to about the year 200. When using only symbols 0 and 1, instead of using 0 through 9, one can still write all numbers, arbitrarily large numbers. And that's called then the binary system instead of the decimal system, but it's the same idea. It's still the Hindu number system, except we're now using only 2 symbols instead of 9 symbols. And this binary system of writing numerals first occurs in Pingal's Chandashastra, also around 300 BC, and is now the basis for all computer computation. So this fundamental contribution of the Indian number system is not just the way we write numbers by hand every day, but the computers also rely heavily on the same system using just the numbers 0 and 1. And that has its origins in the Chandashastra. The algebraic properties of the number 0, as a number in itself, like all other numbers. In the Bakshali manuscript, the 0 was actually just written with a dot. But it was Brahmagupta who said, this dot, this shunya, should actually be a number on par with any other number. And Brahmagupta's algebraic operations that the number 0 should satisfy, the identities that 0 should satisfy as a number, were first formalized in Brahmagupta's Brahmaspurta Siddhanta in 628, in the year 628. And this was the first time that 0 was not just being used as a placeholder in writing numerals, but it was treated as a number in itself, as important as number as any other number. And that was Brahmagupta in the year 628. That was an important development in mathematics, to realize that 0 is not just a placeholder, but it's in fact a number in itself. The Hindu number system was transmitted to the Arab world by around the year 800. It was popularized by the great Persian mathematician Al-Khwarizmi, who wrote this very important treatise on the calculation with Hindu numerals around the year 825. And it was also popularized by the great philosopher Al-Kindi, who wrote the treatise on the use of Hindu numerals, circa 830. And when the Persians and the Arab world was referring to the Hindu number system, the Hindu wasn't referring to a religion, it was referring to the people who live near the Sindhu River. When the sound S moves to Persia, it becomes an H sound. And so the people near the Sindhu River, the civilization around the Sindhu River, was known, the people in that region were known as Hindus. And so the number system that was coming from that region was called the Hindu number system. And that's why it has that name today. From the Arab world, the Hindu numerals were transmitted to Europe. This happened around the year 1100, after the popularization by Al-Khwarizmi and Al-Kindi. And when it reached Europe, the Europeans thus, because they learned it from the Arabs, they mistakenly called it the Arabic numerals, the Arabic number system, even though the Arabs, of course, called it the Hindu numerals. And so textbooks, even in India, later on then started calling it the Arabic numerals. This is finally being corrected in textbooks around the world over the last several years. So that's the history of zero and how it led to the system of numerals that we use today, the Hindu numerals. Okay, another very important contribution of India was the Bodhayana-Pythagoras theorem, which says that if you have a right triangle and you have sides AB and the long side is C, the hypotenuse, then the famous theorem says that C squared equals A squared plus B squared. This is often known as the Pythagorean theorem, but of course it was also known to other cultures prior to Pythagoras, who lived around 500 BC. In fact, there's no evidence that Pythagoras or the Pythagoreans had a proof of the theorem. It's more of a legend. But the first place that we know of, historically, where the theorem is explicitly stated for a general triangle, in just the way we describe it today, is in Bodhayana Shulba Sutra from around 800 BC. And it's verse number 1.45 from 800 BC. And it says that a rope stretched along the diagonal produces an area which the vertical and horizontal sides make together. There's also a verse 1.48 in the Shulba Sutra, Bodhayana's Shulba Sutra, which also describes not just the theorem, but why the theorem is true. And so a proof is essentially contained in Bodhayana's Shulba Sutra. For the mathematically savvy, if you read verse 1.48, you can actually see why the theorem is true. And this was very exciting to me when I was reading this as a child. That to combine different size squares, you mark out the rectangle from the larger with a side of the smaller. The diagonal of this rectangle is a side of the sum. So if you can unravel that, you actually understand why the theorem is true. And that's it's actually one of the most beautiful proofs out there when you work it out. I want to say a little bit about the contributions of India to the mathematics of language. Painini made a huge contribution in this area, in particular in the theory of generative grammars. So generative grammar is essentially a system of rules that generates exactly those combinations of sounds and words that form grammatical sentences in a given language. And this forms an important concept in linguistics and in computer science, because the given language that we're talking about that we want to generate may be a natural language, but it may also be a computer language. And we would like a way of knowing what are all the valid sentences in that language. The concept of having a large generative grammar, a large-scale generative grammar, was first discovered by Painini, who constructed a huge generative grammar with algebraic rules that govern every aspect of the Sanskrit language. Nothing like that had ever been done before, and nothing like that has ever been done since. A monumental effort and the first large-scale generative grammar. Painini's Ashtadhyayi consists of about 4,000 sutras, over 8 chapters, and it lays down a generative grammar for an entire natural language, namely that of Sanskrit. An absolutely incredible work, and for this reason, Painini is often called the father of linguistics, and of course is the earliest founder of theoretical computer science. One aspect of Painini's work, there's modeling of verb conjugation, of formation of sentences, but even on the smaller word level, there is a whole theory of phonetics that's contained in the work of Painini. And so one small part of what Painini does is the analysis of the phonetics of Sanskrit, which is indeed an analysis of the phonetics of most Indian languages. The phonetics of Sanskrit and most Indian languages is incredibly mathematical. This includes not just Sanskrit and Prakrit, but also Marathi and Telugu and Tamil. The way the phonetics of Indian languages works is incredibly mathematical. And this way that it works is common to the North Indian languages and the South Indian languages and the East and the West. It's quite remarkable. It's very special to Indian languages. And Painini and his predecessors' description of this phonetic structure of Indian languages is truly striking to a mathematician. So what happens in Indian languages is that each phoneme means a fundamental unit of sound, and equivalently each grapheme, there's a one-to-one correspondence with the fundamental sounds of Indian languages and the letters that represent those sounds. Indian languages, most of them are perfectly phonetic. And so each sound, each phoneme in Indian languages that use the Brahmi style script has 2 independent parameters by which it's completely characterized, namely the organ of pronunciation, where in the mouth or the throat, what organ you're using from the mouth to the throat to produce that sound, and then the modulation, the quality of the sound that's being produced from that organ. It turns out that there are 5 organs of pronunciation in Sanskrit. These are the throat, the palate, the roof of the mouth, the teeth, and the lips. And these 5 kinds of sounds are called gutturals, the throat sounds, the palatals, the palate sounds, the cerebrals, which come from the roof of the mouth, the dentals, which use the teeth, and the labials, which use the lips. Those are the 5 organs of speech. And then there are 11 qualities of modulation. I won't go through what each of them means because that would take a while, but there's hard unaspirated, hard aspirated, soft aspirated, and nasal. Those are the qualities for consonants. Then there are the semivowels and the sibilants. And then there are the simple, long, gurna, and vriddhi vowels. These are the 11 kinds of modulation for each of the kinds of organs of speech. And what's amazing in Sanskrit and Tamil and all these Indian languages that use this phonetic system is that if you specify which organ of speech and which modulation, that specifies the sound. It's like a perfect 5 by 11 table. And it roughly looks like this. And most of the sounds of these possible 5 by 11, in other words, 55 possibilities, of these 55 possibilities, 51 actually exist as distinct sounds. So for example, if you're specifying, you want to know what sound comes if you use a guttural sound, if you use the throat and it's hard and unaspirated, you get a ka. But if you take a hard aspirated using the same throat, you get ka. If you do a soft unaspirated coming from the throat, it's ga. If you use a soft aspirated, it becomes gha. And then if you have the nasal guttural nasal, that's nga. And it's amazing that we actually learn the alphabet this way in Indian languages. Ka, ka, ga, gha, nga. And then we move on to the palate. Cha, cha, ja, ja, nya. And then we move on all the way to the labials. Ba, pa, ba, pa, ma. And so the labial, if you use your lips and you make a nasal sound, what sound do you get? if you use the lips and your nose, you get ma, ma. So for example, the labial nasal sound is the ma sound. And it's remarkable to most people who don't grow up with Indian languages that when they hear somebody saying the alphabet in an Indian language, they're amazed that it's a lesson in phonetics. If you think in English, for example, the vowels and the consonants are all mixed up and the organs of speech are going all over the place. But in Indian languages, we actually, when we learn the alphabet, we're actually learning a lesson in phonetics. Ka, ka, ga, ka, nga, throat. Ja, cha, ja, cha, ya, palate, and so on, all the way up to ba, pa, ba, ha, ma, using the lips. So this is a lesson in phonetics that was already written down in Bainani's time. This is how Bainani discusses the whole system of phonetics of the language. And that is then the basis of further operations such as Sandhi. How to combine sounds to make new sounds. So that whole theory of phonetics really created a revolution in modern phonetics when the West learned about this system of phonemes and phonetics of the Indian languages. Okay, so that's the story of how mathematics and language really interacted in ancient times. And I'll say a little bit more about that in a couple of minutes. I want to say something about Aryabhata and his influence on trigonometry. The sine function has its origins, and the cosine function has its origins. These are the fundamental functions of trigonometry. They have the origins in the work Aryabhatiya of Aryabhata. Indeed, both functions, sine and cosine, can be traced back to the functions jya and koti jya, as introduced by Aryabhata in the year 510. So this jya and koti jya, the word jya or jya ardha, meaning half chord, was transliterated from Sanskrit to Arabic when geometric works were being translated from Sanskrit to Arabic, when the geometry works of India were moving to the Arab world. It was transliterated kind of arbitrarily as jibba. Jya became jibba, just as a transliteration, not because of any translation, just transliteration. Similar sounding word. And then when Arabic geometry was moving to Europe, Robert of Chester was translating this Arabic work on geometry, and they saw the word jibba, which came from Aryabhata's jya. And jibba is a meaningless word, but he confused it with the Arabic word jaib, which means bosom. And so the Latin word sinus, he used the Latin word sinus for bosom, and that was used for the half chord function. Series of accidents. And that's how the word became sine. So Aryabhata's jya eventually became the word sine through this interesting etymology, this interesting transition from India to the Arab world to Europe. And now we all use the word sine, but it has its origins in Aryabhatiya. And this is really a testament to the importance of Aryabhata's work on trigonometry, his foundational work on trigonometry that really led to his two functions being the main functions of trigonometry that we now use today. The negative numbers. After recognizing 0 as a number, as I mentioned before, Brahmagupta treated 0 as any other number. But then he realized if you take 0 and subtract 3, that has to be a number too. If 0 and 3 are legitimate numbers and he wants our set of numbers to be closed under subtraction, then minus 3 also has to be a number. And so after recognizing 0 as a number, Brahmagupta was naturally led to defining and recognizing negative numbers as actual numbers and on an equal footing with positive numbers and 0. He used an analogy with fortunes and debts to justify that both are possibilities and both are numbers on an equal footing. The algebraic properties of negative numbers were first formalized and described in Brahmagupta's Brahmaspurta Siddhant in the year 628. So, for example, in Brahmagupta's list of rules that negative numbers satisfy, he explained that just like a positive number times a positive number is positive, Also, a negative number times a positive number is negative, and a negative number times a negative number is positive, and so on. He described the rules of addition, subtraction, and multiplication. Nowadays, we say that the positive whole numbers, together with 0 and the negative numbers, using Brahmagupta's rules for addition and multiplication, form what in modern times we call a ring. And this is now a very important concept in modern algebra, the concept of a ring, but it would not be possible for this ring to exist, to be closed under addition and multiplication, if we hadn't added to our number system on an equal footing the numbers 0 and the negative numbers. So negative numbers also originate in India in the work of Brahmagupta. The introduction of 0 and then the negative numbers to our number system is indeed one of the great leaps forward in the history of mathematics. So when we always remember that 0 came from India, natural extension of that, the negative numbers actually also came from India as well. Brahmagupta did many incredible things. One other thing that Brahmagupta did in the same work, Brahmasputra Siddhant, we all learned in school that the solutions for x of the equation ax squared plus bx plus c equals 0 are given by this quadratic formula, minus b plus or minus square root of b squared minus 4ac over 2a. And while solutions of this quadratic equation had been obtained geometrically, and for specific types of quadratic equations in Greece and in Egypt, it wasn't until the very first explicit statement of this quadratic formula by Brahmagupta that we really had the quadratic formula in its modern form. The first explicit statement of the two solutions for a general quadratic was given by Brahmagupta in 628 in his Brahmasputra Siddhant. And a translation of what he wrote, to the negative of the constant coefficient multiplied by 4 times the coefficient of the square, add the square of the coefficient of the middle term. The square root of this minus the coefficient of the middle term being divided by twice the coefficient of the square is the value. And if you unravel that, you'll see that it's exactly this quadratic formula. Right? You can see to the negative of the constant coefficient, that's minus c, multiplied by 4 times the coefficient of the square, that's a, so that's minus 4ac, there it is. Add the square of the coefficient of the middle term, there it is, add the square. The square root of this, right, minus the coefficient of the middle term, that's this, being divided by twice the coefficient of the square, is the value. So that, in words, is exactly this quadratic formula. Except the way he writes it here is so poetic that you just immediately remember it when you read it in the original Sanskrit. It's very, very beautiful. Other kinds of quadratic equations that Brahmagupta solved include the Brahmagupta-Pell equation, which Brahmagupta, together with the later work of Bhaskara, fully solved the Brahmagupta-Pell equation. That's a quadratic equation that looks like x squared minus ny squared equals plus or minus 1. This equation is of great modern importance in algebraic number theory, and it was first solved in India. It was defined and first solved in India, and its importance is really felt in modern mathematics. Okay, so that's the solution to the quadratic equation, also first written down explicitly in India. There's one other beautiful interaction between mathematics and language that I want to tell you about quickly. As in many modern Indian languages, Sanskrit and Prakrit poetry consists of syllables that are classified as either short or long. In other words, laghu or guru, short or long. It's not just Sanskrit and Prakrit. Modern languages have this dichotomy of their syllables as well, including Marathi and Telugu. And so when poetry is read in Marathi or Telugu, all syllables are either short or long. And what does short or long mean? When pronounced, a short syllable lasts 1 beat of time, and a long syllable lasts 2 beats of time. So a long syllable takes exactly twice as long to say as a short syllable. And a question that arose for ancient poets, a very practical question for a poet: how many rhythms, how many meters can one construct of, say, exactly 8 beats consisting of short and long syllables, where a short syllable takes 1 beat and a long syllable takes 2 beats, right? So 8 beats could be long, 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 or it could be short, 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 or it could be something in between. Short, long, long, right? So short, short, long, long. Short, 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 long, long. So all sorts of things. Short, long, long, short, long. So all sorts of combinations are possible. Poets in ancient India came up with a very ingenious solution to obtaining an answer to this question, which is now part of a huge mathematical and artistic theory. How do you tell how many total ways you can fill 8 beats with just short and long syllables? The solution was given by Virahanka in his work Vrittajati Samuchaya in the year 700. And his elegant solution was as follows. Write down the numbers 1 and 2, and then each subsequent number is obtained by adding the 2 previous numbers. Then the nth number will give the number of rhythms having n beats. So we write down the numbers 1 and 2, and then we keep writing down the sum of the previous 2 numbers. 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 is 13, 8 plus 13 is 21, 13 plus 21 is 34, 21 plus 34 is 55, and so on. And now if we want to know how many rhythms there are having 8 beats, we just go to the 8th number, 1, 2, 3, 4, 5, 6, 7, 8. And I put this in a rectangle because that is the solution for the number of rhythms having 8 beats. There are 34 such rhythms. And that's Virahanka's elegant solution, and the set of numbers that he gets are called the Virahanka numbers, defined by Virahanka in the year 700, or perhaps even earlier. In India, of course, these numbers are known as the Fibonacci numbers, after the Italian mathematician who studied them about 500 years later. I should mention that the Virahanka numbers were also studied after Virahanka by Gopala in the year 1135 and by Hemachandra in the year 1150, again in the context of poetry. And so Fibonacci was not only was Fibonacci the first person to study the Virahanka numbers, but he wasn't the second or the third. At least 3 people, Virahanka, Gopala, and Hemachandra, studied these numbers before Fibonacci. Yet in India, we still call them the Fibonacci numbers. But the above story about poetic meters is a very beautiful and natural way to learn about the Virahanka Fibonacci numbers, because that's the way that they were really first discovered. These numbers were discovered in an artistic, poetic context, which really illustrates the fine line between science and art. And it's just a wonderful lesson to see that interaction between science and art. The story of the Virahanka numbers. A related question that comes up in the same context is, well, suppose we want a meter of 8 syllables where we specify how many laghus and gurus there are. For example, we may ask how many meters of 8 syllables are there consisting of 3 laghus and 5 gurus. And in general, we can ask how many meters are there of n syllables having k laghus and n minus k gurus. Again, another natural question in poetry. And the answer in this case the solution to this problem led Pingala around 300 BC, as well as later writers, Virahamira, Virahanka, and Halayudha. It led them to the discovery of Pingala's Meru Prastara, which is an infinite mountain of numbers consisting of binomial coefficients. Binomial coefficients are the answers to this problem in general. And of course, binomial coefficients now play an extremely important role throughout probability, combinatorics, number theory, and much more. So they're absolutely fundamental to modern mathematics. And Pingala and his successors gave an algorithm to produce the answers to this question in general. But in the year 850, the mathematician Mahavira gave a direct formula for all the binomial coefficients, namely the formula, if you go to the nth row of the Meru Prastara and you take the kth element of that row, that number will be n factorial divided by k factorial times n minus k factorial. We all use this in probability and combinatorics, this formula. We rarely learn that it originated in India with the work of Mahavira, but actually this originates in India as well. In India, of course, Pingala's Meru Prastar is called Pascal's triangle, after the French mathematician Pascal, who lived about 2,000 years after Pingala. And again, Pascal was not the first person to study Pingala's Meru Prastar, and was not even the second or third or fourth or fifth. Yet somehow the name Pascal's triangle has stuck. But hopefully these things will change over time as we learn the correct history. There's a whole theory of error detecting and correcting codes that comes out of the work of Pingala and his predecessors and successors, which I won't get into in detail, but the desire to maintain the integrity of metrical compositions led Pingala around the year 300, and even by his predecessors, led them to certain error detecting and correcting codes, such as Yamatara Jabhana Salaga, that enabled the oral preservation of compositions for centuries without any errors. It's quite a remarkable error correcting and detecting code. It worked brilliantly. We have over 200 compositions in their perfect sequence of longs and shorts, laghus and gurus, that have been preserved orally for thousands of years without any errors because of these brilliant ways of detecting and correcting errors using sutras such as Yamatara Jabhana Salaga. I won't get to talk about it too much today. It is quite an intricate subject, but I've given lots of lectures about it before, and I hope you'll get a chance to look up this remarkable invention of Pingala and his predecessors. Okay, and I'll end today with talking about the first exact formula for pi that was ever known. Madhava's exact formula for pi. So we all learn about pi in school, and pi is a concept that has come up in every culture since ancient times. Over thousands of years, mathematicians from many cultures, including Archimedes, Aryabhata, Changji in China, and others, gave increasingly accurate estimates for this all-important, irrational, transcendental constant, pi, which is the ratio of the length of a circumference of a circle to the diameter of the circle. And pi is about this number here, 3.14159265335846264338462643383751097169393751058209, and so on. So that's the approximate value of pi, but it's not exact. I just said so many digits, and I'm still not exactly saying pi. Pi is just approximately that. And mathematicians over many centuries, many millennia, were getting closer and closer to the value of pi, but we're never exactly reaching it. Because pi, as I said, is irrational, and it's transcendental, which means that there's no way of describing pi in a finite formula, in a small formula, just using whole numbers. So how can we write down pi exactly? The first exact formula for pi was given by Madhava in around the year 1400. And his remarkable formula, if you haven't seen it before, he showed that pi is equal to 4 times 1 minus a third, plus a fifth, minus a seventh, plus a ninth, minus an 11th, plus a 13th, minus a 15th, and so on. So since pi is irrational and transcendental, there's no way to have a finite formula using whole numbers for pi. But Madhava's brilliant idea was to write down an infinite series that gets pi exactly on the nose. And that was the first time that an exact formula for pi was ever given. That means that in theory, if you take this out far enough, you can get pi to an arbitrary number of decimal places. So this is an exact formula for pi, and the first time that was ever achieved. That was done by Madhava. So this is the first and perhaps the simplest and most beautiful exact formula for pi in history, and it has its origins in India. First formula for pi. It was discovered by Madhava in the context of his theory of infinite series. And see Professor Ram Subramaniamji's talk later today on this very topic. But it's this theory of infinite series of Madhava which indeed laid the foundations of calculus that would be discovered by him and the Kerala School of Mathematics. So that's another beautiful chapter in India's contributions to mathematics, calculus and infinite series. So there you have it. These are my favorite 10 contributions of India to mathematics that I feel everyone should know, that all our students in schools should learn. They're all very beautiful, all very fundamental. I hope it'll inspire you to learn more about these, and I hope it'll inspire the students of India to learn this legacy of their country and to be inspired to take mathematics to greater heights. So thank you very much, and I'll stop here. Thanks very much for your attention. Namaskar.
Thank you, Professor Manjul Bhargav. Thank you so much. और अब हमारा आग्रह है प्रोफेसर GS मूर्ति, नेशनल कोऑर्डिनेटर ऑफ इंडियन नॉलेज सिस्टम्स फॉर मिनिस्ट्री ऑफ एजुकेशन एट AICTE to kindly propose vote of thanks. कृपया आभार प्रकट करें.
Before that, I think let's take a few questions if there are any. So, anyone in the audience? Can I have a mic there, please? Let's see if there are any questions online too. Thank you so much, Professor Bhargavaji. Namaste. It was a pleasure interacting with you online, but nice seeing you in person.
Thank you so much for having me.
Thank you so much for having me.
Any
I just
questions?
want to take this opportunity
Sure.
I think
thank the Ministry of Culture.
Ministry of Culture.
there is a question, Professor Bhargava.
Sure.
भार्गव जी नमस्कार. मैं राजीव
नमस्कार.
कुमार. नमस्कार. भार्गव जी आपका बहुत इंटरेस्टिंग लेक्चर था, बहुत जानकारी मिली. मैं एक जनरल मेरा एक आपसे क्वेश्चन है कि जो इतने इंटरेस्टिंग एस्पेक्ट हैं मैथमेटिक्स के, एंशिएंट मैथमेटिक्स के, आप नेशनल एजुकेशन जो पॉलिसी बनी उसके भी एक पार्ट थे. इनको हम अपने स्कूल करिकुलम में इंटरेस्टिंग तरीके से किस तरीके से ला सकते हैं कि जैसे यहाँ पर जो बच्चे भी आए हुए हैं, स्कूल से भी आए हुए हैं, उनको ये सब चीजें जो हम आज बता रहे हैं वो स्कूल लेवल पे ही उनको बहुत क्लियरिटी हो. जैसे बहुत सी सीरीज हैं या फॉर्मूले हैं जो इंडियन ओरिजिन से हमारे आए हैं, बाद में हमने डिफरेंट नाम से उनको अपने करिकुलम में रखा हुआ है. कैसे उसकी जानकारी हम अपने बच्चों तक एक स्कूल लेवल पर ही ला सकते हैं? थोड़ा आपका कुछ सुझाव इस बारे में होगा?
हाँ, मुझे लगता है कि ये जो कहानियां हैं काफी एको आ रही है. ये जो कहानियां हैं जैसे लघु गुरु के बारे में, लघु गुरु से निकलते हैं ये एको बहुत आ रही है. हाँ, तो ये जो कहानियां हैं लघु गुरु, मात्र वृत्त, अक्षर वृत्त, ये बहुत सुंदर कहानियां हैं जिससे विरहांक नंबर्स निकलते हैं, जिससे बाइनोमियल कोएफिशिएंट्स निकलते हैं, जिससे एरर करेक्टिंग कोड्स निकलते हैं, और ये सब कविता के माध्यम से निकलते हैं. तो हम साथ में कविता भी सिखा सकते हैं, साथ में गणित भी सिखा सकते हैं। इससे ज़्यादा सुंदर क्या हो सकता है? और जैसे हम अभी सिखाते हैं, फिबोनाची नंबर्स सिखाते हैं, वो ऐसे सिखाते हैं कि रैबिट्स कैसे मल्टीप्लाई होते हैं। एक वो इंसेस्चुअस स्टोरी है कि रैबिट से बहन भाई से मेट करके कितने प्रोड्यूस कर रहे हैं, बिल्कुल अनरियलिस्टिक है। और हमारे यहाँ जो जिस तरीके से विरहांक नंबर निकले थे, वो इतने सुंदर तरीके से निकले थे कविता के माध्यम से। तो हम ऐसे अगर सिखाएंगे तो बच्चों को तो रुचि आएगी इसमें। तो मुझे लगता है जो कहानियां हैं वो सच तरीके से अगर बताएं तो बच्चों को वैसे ही उसमें रुचि आएगी। पता नहीं मेरी आवाज आ रही है कि नहीं, लेकिन मेरी आवाज आ रही थी?
मेरी आवाज आ रही थी?
Hello, yes.
ठीक
Professor
है।
Manju Bhargav, this was really a fantastic lecture. So I thoroughly enjoyed it. I
Thank
have
you.
one short question to you. This string Yamatara Jabhana Salagam that you have been citing, should it be conceived as a mnemonic which has been coined just for the sake of remembering various ganas? Or would we really take it as a mechanism by which we can do the error correction? How do we understand this?
Yeah, so actually Yamata Rajabhana is not in itself needed for the error correction that was taking place. If the echo could be turned off, it'd be easier.
Mute this mic, please. Can you?
Yeah, thank you. Hi, Ram Subramaniam ji. Yeah, what I was saying is that we don't actually need the word Yamata Rajabhana Salagam in order to carry out the error correction that Pingala had suggested. So Pingala wrote poems about meters in their meters with the code where each triplet was assigned either ya or ma or ta or ra or ja or bha or na or sa or la or ga, right? But we don't actually have to know the word as long as we know that correspondence between these consonants ya, ma, ta, ra, ja and the triples of zeros and ones. As long as we know that correspondence, which was there written in Pingala, then any of the poems that had this encoding in them about each of these meters will survive the years, because we know that when you unravel that coding onto the whole poem, it coincides with the sequence of zeros and ones of the poem. So nowadays we always use Yamata Rajabhana Silaga to memorize that correspondence, but that correspondence is written very clearly in the ancient work of Pingala, and we can just use that as a lookup and then use that to do the error detection correction. And so I don't actually know whether people were always using Yamata Rajabhana Salagam or whether they were just using the encoding that was just written explicitly in Pingala. But either way, it works just as well. But it is just a mnemonic to remember that correspondence. But it's not needed for the error correcting itself. Sorry, it would have been, if I had actually explained the whole process, it would have been easier for the whole audience to understand that answer. But hopefully Ram Subramaniam ji that answered your question.
Hello, Professor Bhargav. This is Anuradha. I just wanted to thank you very much for your fantastic presentation. I was quite intrigued by the aspect of generative mathematics related to language, and the Sanskrit language, of course, in that context, and the other Indian languages with different degrees of precision. And something that I've been working with, and it's fascinating to also understand the extent of mathematics that the mind has to perform in order to decide to make one single sound in the Sanskrit language. So I was wanting to know your take on the fact that when we're trying to promote English, and like a lot of knowledge is happening in English, and language is generally perceived as a language as a means of communication primarily. But this other aspect of language, how do you think that is something that we really need to pay attention to, and how could one make a difference in our education system by focusing on this aspect and what it would do to the individuals who studied in in those languages?
Yes, great question.
Yes, great question.
And a very good point. We often use English and languages generally in a very utilitarian way, but not for the inherent beauty of the languages, of which Indian languages has, just an incredible level of beauty and science in a way that other languages don't. And in India, we have that treasure in Indian languages. And unfortunately, it's not taught in schools. And I think one way to really increase the interest of children in Indian languages is to also emphasize these really poetic and scientific aspects that don't exist in the languages that everyone is trying to learn for utilitarian purposes. So, yeah, I completely agree with you. I think teaching mathematics through more poetry, through the science of Indian languages, through the beautiful legacy that the Indian literature has to offer, I think really can make language learning and related areas like science and mathematics and poetry much more interesting. So I hope in language learning we can bring in these really interesting and beautiful aspects.
There are a few questions from online audience. Can we take one of them, please? You can mute this mic.
Hello, am I audible?
A little bit.
Okay, so I'm Amartya Dutt. Fantastic talk.
Namaste, Amartya ji.
Can you quickly tell us that this Panini's incredible system of the linguistics, how it has impacted algebra or mathematics in the form that we know it, the usual algebra and maths that we associate. How whether there has been any impact? What is your view about that?
Whether the mathematics of Panini has had any impact?
The linguistics. So Panini, what you explained is more linguistics, but the mathematics that is usually understood, what is usually understood as mathematics, as algebra, etc.
Oh, I see.
The linguistics might have influenced mainstream mathematics. Any hints about that? I think it's a big topic, but maybe you could give some hints.
Yeah, well, theoretical computer science is a major area of mathematics, the theory of computation and computability. And theoretical linguistics and generative grammar is a big part of that. When we talk about regular languages in theoretical computer science, we're asking whether we can generate strings using a given set of rules. And Panini is the first example where we are generating strings of letters, of words, using rules. It's a way of thinking that we are proving theorem. If you think of a theorem as being a valid string in the language, we are proving theorems using a given set of rules. And that's exactly what Panini was doing, giving a set of rules in order to deduce correct, valid sentences. So it's at the heart of theoretical computer science, I would say. That is the branch of mathematics that Panini's work really influenced.
So, in some sense, mathematical logic, would you say something about mathematical logic also? Steps in mathematical logic, can it be said that?
Yeah, I mean, it can be thought of as a deductive system. You have a set of rules, you have a set of axioms, and then you have a set of rules, and you're trying to deduce a set of valid statements, which in Panini's case are valid grammatical sentences. So that's right. I mean, it's a deductive system in the language of mathematical logic. Yeah.
Thank you.
And it's the first such that ever existed, such a.
Another question from online, please. We'll have another question from online audience. Mute this mic, please. Is it possible to fix a separate chapter in school textbooks that describe the history of mathematics? This is Dr. Sanjay Mishra asking a question online. Professor Bhargava, please unmute this. Mute this mic.
I think that's very reasonable. Sorry, I was saying I think that's very reasonable to bring the contributions of India to mathematics to students. There are two things one can do. One is to make sure that it's embedded throughout the regular school curriculum. When binomial coefficients come up in teaching probability, that's a natural point to mention the history of binomial coefficients, and in particular, the work of Pingala, Virahanka, Mahavira in that area. So that's a natural. So there are two ways to do it. Either to have just a chapter where we describe all these in one place, but then also to make sure that it's embedded throughout the curriculum when relevant. So those are two things that can be done to bring out these nice Indian stories about the development of mathematics. But I think it's totally reasonable to have a chapter as well where it's all collected in one place for students to learn. But it shouldn't be done at the expense of not saying it also where it's relevant whenever it comes up naturally in the curriculum. Because all the things, for example, that I mentioned today naturally occur in the mathematics curriculum, and yet those true facts are ignored. And there's no reason for that. When it's relevant, bring it up. But then also, sure, it's good to have a separate chapter on Indian mathematics, on the contributions of India to mathematics, on Indian knowledge systems. That's also a nice way to have it all in one place as well.
Thank you so much, Professor Bhargava. Thank you so much for answering patiently the questions that we had from live audience and also online audience. I think it was a wonderful experience for all of us, and also especially the students amongst this audience. Thank you so much for sparing your time. I know it's quite late there, quite late in the night. So thank you so much for sparing that time. And really appreciate it. Thank you so much. So in the interest of time, we'll move ahead now. So again, namaste. Thank you so much, Professor Bhargava. And I would like to thank you so much.
As a token of our immense respect and to honor our guests present here, we would like to present them mementos. आप सभी से निवेदन है, प्रोफेसर के रामासुब्रमण्यन, प्रोफेसर पार्थसारथी मुखोपाध्याय, प्रोफेसर राजीव कुमार and respected Ratnesh Jha ji, please मंच पर आइए. Or I would like to request Professor G.S. Murthy, National Coordinator of Indian Knowledge Systems for Ministry of Culture at AICTE, to kindly present mementos to our guests. Respected Professor K. Ramasubramanian, respected Professor Parthasarthi Mukhopadhyay, respected Professor Rajiv Kumar, respected Shri Ratnesh Jha. आज के कार्यक्रम की यादें हम सभी के हृदय में हमेशा के लिए, बल्कि माथे में कहूंगी कि हमेशा के लिए अंकित हो जाने वाली हैं, क्योंकि ये ज्ञान गंगा है. सबसे पहले प्रोफेसर रिस्पेक्टेड के रामासुब्रमण्यन. प्रोफेसर, आपको पौधा और शॉल से सम्मानित किया गया। प्रोफेसर रिस्पेक्टेड पार्थसारथी मुखोपाध्याय, as a token of our immense respect and to welcome and to honor Professor Rajiv Kumar, respected Rajiv Kumar. Respected Shri Ratnesh Jha, thank you so much, our honorable guests. Thank you, our esteemed guests. Thank you so much. अब मैं निवेदन करूंगी प्रोफेसर GS मूर्ति आपसे कि कृपया आभार प्रकट करें. Kindly propose vote of thanks.
But as they say, a painting, every stroke of brush is important in a painting. And an event like this could not have been possible without the support and hard work of many individuals who are behind the stage. Many of them are not even present here. They're either working outside or coordinating from somewhere else and then trying to make this all happen. So, and the heart and soul of any event is the Vidwans who have come here, the scholars who have come here and are sharing their knowledge. So for that one, I would like to thank all the speakers of today's events and especially Professor Manjul Bhargava ji. And I know that there is a lot of demands on his time, and but still he has made this effort to come here and then connect with our young students and faculty members throughout throughout our country. So I would like to start off by thanking Professor Manjul Bhargava ji, and then behind all of this, the Sutradhara was Professor K. Ramasubramaniam, who has given a lot of things to make sure that we have the stellar speakers who are basically have spent their decades of their lives researching these things as their main thing. So I would like to thank Professor Ramasubramaniam from my heart. And then Professor Parsarthi Mukhopadhyay ji, he has come all the way from Kolkata here. And again, those of you who may be visiting Kolkata, I would definitely suggest that you please go to Kolkata and visit Professor Mukhopadhyay's Museum of Zero. He has created a wonderful museum of zero. And those who cannot go there, there is a video that he has created on this subject, about 40-minute video that has been released last year in December. I would encourage all of you to watch it. And I would like to thank our chief guest, Professor Rajiv Kumarji, who has helped us with all of these setups, and AICTE, who has the machinery of AICTE, has come in and helped us conduct this program. And behind all of this, the inspiration came from the Ministry of Culture. And all of this, as Manjul Bhargava ji was saying, art and mathematics are basically, it was not seen as two different things in India. What better event than to start off a conference on Bharatiya Jnana Parampara, Dhara, Ode to Indian Knowledge Systems, with a partnership between Ministry of Education, Ministry of Culture. So I would say, let this partnership continue, and I would heartfully thank all the people from the Ministry of Culture, Shri Ratnesh ji and Shriyanka ji, and our Secretary Shri Govind ji, and also people from Kalam Research Center, Srijan ji and his team, and everybody all worked. And also I would be failing in my duty if I don't thank Srijit ji and his team, who have conducted this event and basically managing the event, doing everything, making sure that all of you people come on time, and make sure that all of you have facilities to make sure that you can listen, focus on the talk rather than anything else. So with all of that, I would like to thank you all again. And with this, we are looking forward to conducting such conferences based on particular themes in different parts of the country, and which will be again relayed online. So you'll be able to join us either in person, hopefully in person, or online as we go forward. With that, I would like to thank everyone and Sarvam Sri Parabrahmana Arpanamastu. Hari Om.
थैंक यू सो मच प्रोफेसर मूर्ति। आज का ये कार्यक्रम ज्ञान और गर्व दोनों का संगम है। ज्ञान जैसा कि हम लोग सब जान रहे हैं, और गर्व क्योंकि हमारे भारत की जो ज्ञान की धरोहर है, नॉलेज की धरोहर है, वो दोनों ही आज यहाँ पर आकर उसका संगम हो रहा है। सो थैंक यू सो मच। आज ये सारा दिन हमारा डे लॉन्ग सेशन है, बहुत सारे अलग अलग विषयों पर, पीरियड्स पर हम चर्चा करेंगे। May I now request all of you to kindly join us for a cup of tea, and we shall resume the first technical session after half an hour from now. आधे घंटे के बाद हम फिर यहाँ पर इकट्ठे होंगे उसी ज्ञान गंगा में डुबकी लगाने के लिए। और अब हम सबसे पहले जो फर्स्ट टेक्निकल सेशन है उसमें एंशियंट पीरियड की चर्चा करेंगे। थैंक यू सो मच। नमस्कार। We'll be waiting for you after half an hour from now. You all are aware that today we shall cover 3 topics in the forthcoming sessions linked to the different ages and schools: ancient period, classical period and Kerala school. सबसे पहले एंशियंट पीरियड की ओर रुख कर रहे हैं. हमारे बीच प्रोफेसर पार्थसारथी मुखोपाध्याय उपस्थित हैं. Before he talks on the theme zero and decimal place value system, I would give a brief introduction of Professor Mukhopadhyay. Dr. Parthasarathy is a gold medalist in Masters, did his PhD from University of Calcutta. He has been teaching abstract and linear algebra for about 3 decades in Narendrapur Arkin Mission Residential College. He has been researching on the origin of zero and a number for last 15 years and has lectured on this topic in various IITs and other institutions. So he'll be delivering, as I told you, on the topic zero and decimal place value system. I request Professor Parthasarathy to kindly join us.
Thank you very much. A very good morning to everybody. I think it's already good afternoon. Okay. So let us get into business straight away. Today, the topic of lecture, as you can see, the zero and decimal place value system in India. So let me share with you this slide where I'm showing you. I'm quite sure that you are all aware of this number zero in your mathematics curriculum. And have you ever given it a thought that this number is a kind of weird number? It doesn't go by the rules made for others. Everywhere in mathematics, if you just try to understand, you will see that it makes its own rule, not just the number zero, but every zero-like concepts in mathematics, be it a null set, be it a null matrix, be it a null vector, everywhere its rule is different. I prefer to call it the naughty boy of mathematics family. But we can't do without it. And my friends, this number had to be invented at a point of time in human history. Not like other numbers which are called natural numbers. This number is a work of human intellect. And as you have listened to Professor Manjul Bhargava in the morning, that it's widely believed that this was in India, that this number bloomed into its true potential as the true predecessor of the modern mathematical zero. So today, in coming 20-25 minutes that I have, I'd like to push it back further in history with evidence as far as possible to see the origin of this number zero in Indian soil. Have you ever been to this place? This is Gwalior Fort, my friends. If you ever be there, search for this Chaturbuja temple, the temple of Lord Vishnu in that Gwalior Fort. And if you enter the fort, this temple, in one of the walls, you will find this stone inscription. This stone inscription, if you blow up one particular part of it, there you see in Nagari numeral the number 270 written. What is this stone inscription all about? It's a land grant by the then King Mihir Bhoja to this Lord Vishnu temple. And this is actually the Sanskrit transcription of that entire writing there. And there I have marked by red this particular part of our interest, the number 270 in Nagari. If you look at the English translation, the transliteration of that, it says that this is 270 royal hastas. That's measure of the length of the piece of the land. And historically, it is generally accepted as the oldest known stone inscription of the modern zero in human civilization. But if you have noted the time, it's only 9th century. Does it mean that India started using zero in 9th century only? Of course not. So let us see how far can we push it back. If instead of stone inscription, you are ready to accept the copper plates, the charter, land grant charter, the oldest one that we know is from 594 CE, the Sankheda charter in Gujarat. But that's on copper, and somehow some experts are not very pleased with the authenticity of that, though they do not put very strong reason for questioning the authenticity, but they do have their own reservations. And that's not all. Even if you go by the stone inscriptions, there are other candidates much earlier than this Gwalior inscription. And there is a list. The time will not permit me to get into one by one systematically. This is in one of the fantastic article by Professor Michel Danino Padmasri, where you can find the reference to all these prior to this Gwalior inscription, some stone inscription in place value system where 0 is present. Now, if I ask you who invented 0, I know most of you will say Aryabhata, but that's a very unfortunate misinformation. So, before I get into further serious topic, let me share with you this popular joke that is there in social media. You see there Aryabhata, of course, it's an imagination of the sculptor. The joke says one day Aryabhata asked his wife, will you allow me to spend the night out with my friends? And the wife says, accordingly to your calculation. You see, you are a calculator, you are such a great mathematician. So why don't you calculate yourself? What's the probability of my giving consent to this? And it is then Aryabhata invented 0. So everybody laughs at it. But you see, what we find is very unfortunate, that this is complete a piece of misinformation, wrong information. Aryabhata's time, as you can see there, written below the bars there, it's in 5th and 6th century. But we can date back with evidence Indian 0 to at least 700-800 years, if not more, right? The ancient India, the most unfortunate part of it is, if you go back prior to Ashokan period, is all Shruti. There is no written evidence. So always is a question of, interpretation and academic controversy among the, person at the know. So let us see today that I am trying to, how far we can push it back with evidence, right? So when we talk about this ancient India, one must very clearly understand that this is not the present geographical Indian location. It's the entire subcontinent that we refer to. Indian mathematics refers to this entire landmass, right? With reference to that, immediately I can take you 200 years back to this Khmer inscription of 0, which is in Cambodia. And it is 200 years older than the inscription of Gwalior. You can see the timeline there. It's rediscovered by this gentleman, Professor Amir Axel, in only 2013. It was there and it was lost in the Pol Pot regime of Khmer Rouge. And then, after a lifetime search, there's a fantastic book, Finding 0, by Professor Amir Axel. If you're interested, you can check it. Then there you find this, in the Khmer writing, the Shaka era reached the year 605 on the 5th day of the waning moon. And this 605, as you can see there in the screen, that O in the middle, that 0, it's called bold dot 0. You see, it looks different than the modern 0. And my friends, this is how 0 used to look like initially in India. Bold dot. Not just the way you write it now. It was, completely blackened, the whole thing, right? So how far can we push it back? From other references, as I told you, there's not necessarily mathematical references all the time. This is a page from a drama called Vasavadatta by Shubandhu. It's a romantic drama where you find this particular line, allegory, Shunna Vinnava Eva Vilikhitam. It talks about, it's a kind of metaphor. The writer tells that as if God himself, by the chalk of moon, has drawn the stars in the sky like 0 dots. Shunna Vinda Vaiva Vilikhitam. So you see, even in a drama, in that period of time, it's between somewhere between 4th and 5th century. In a drama, it's not a mathematics text. The allegory refers Shunya as a Vindu, the dot mark. And this dot mark 0, as you can see the translation there by Louis Gray, it refers to the point of the form of null sign in Bakshali manuscript. In the morning in the talk of Professor Manjul Bhargav, he just mentioned Bakshali manuscript. So this is Bakshali manuscript, found in 1880 at a place some 80 kilometers of northwest of Peshawar. This Bakshali manuscript, 70 mutilated folio of birch bark. It's an amazing piece of mathematics there. Amazing. You won't believe the level of mathematics you find there, including the, Manjul made a fantastic list, but I, with due respect, can add one from Bakshali. Approximation square root. Akrite slishto krityunam sheshacheda dishanguna tadbarga dalashang slishtang iti shuddhi kritikhaya. And you will be amazed to know that this refers to a formula which you can cook up from this. If you break it up, this Sanskrit, the formula turns out to be exactly the same as now known as Newton-Raphson method for finding approximate roots, which was done by Newton using calculus. And this is the time of Bakshali, of course, much prior to Newton, but exact time frame again is hotly debated. As you can see there, recent carbon dating of this manuscript written in Gotha dialect of Sharda script. Different pages were subjected to radiocarbon dating. It is now kept in Bodleian Library, like many of Indian, things that has been, smuggled out or taken forcibly during the British period. It's in Oxford Bodleian Library. And I think time has come to raise our voice to bring such things back to India. Not just Kohinoor that we bother about. This is much more valuable piece of human intellect than Kohinoor. So this is kept in Bodleian Library, and Bodleian people themselves have put it under the radiocarbon test, and one of the page, as you can see, is in 3rd century, almost contemporary to that Suvandhu document of Vasavadatta. And why this is so important, apart from many other fantastic mathematics, arithmetic mainly, it's replete with these bold dot zero symbols. As you can see, this is one of the page I have taken with due acknowledgement to Bill Castleman. You see there, this particular page, all those numbers have been recalculated. There is a large numbers and numbers written in fractions, numerator by denominator. And all these calculations, not just the formula, every formula was actually supplemented by 4, 5, 6 mathematical problems. It's a kind of problem book with problems with solution, this Bakshali manuscript. And there you find abundant this bold dot zero. And that is why exact time frame of Bakshali manuscript is very important in the history of zero. That when India started writing, this perhaps is the oldest known document regarding the bold dot written zero. But does it mean that India started writing it in only 3rd century? They knew it much earlier. Manjul somehow didn't mention that in the morning talk, but I can take you back further. It's in 3rd century BC. This is one of the page of the document. This is Shutra 29 and Shutra 30. Rupe Shunyam and Di Shunne. You will come to know in much more details, I'm sure, in the talk of Professor Srinivas. Next of Pingala Chanda Sutra. In the 8th chapter of Pingala Chanda Sutra, there are categorical mention of these two, Rupe Shunyam and Di Shunne, into a combinatorial calculation where this Shunya cannot be anything else than the mathematical zero referred to. And this is another point that has been mentioned in the morning by Manjul. The idea of zero in Panini. He told about the structuralist Panini's grammatical structure, the deep structure level of mathematics. There is a rule called Adarshanam Lopaha. This Lopaha, vanishing, the idea was the vanishing of middle morpheme of a number. And he said that's a kind of grammatical ancestor of our modern zero, the placeholder zero. Zero plays two roles in mathematics. One is placeholder, like that which makes difference between 101 and 1001 and 11. When you write them, not when you speak. You see, when you speak, you don't require zero. To say 100, it doesn't require zero. It is required only when you write. So be it very clear that when India started writing, this necessity emerged. Not before that. Not before that, it was a fantastic decimal system. And one can see that such a system cannot thrive without the concept of zero. But there is no written evidence because it was all the way oral tradition. Right? So, this Adarshanam Lopa, there is a fantastic book, Zero in Panini by M.D. Pandit. If you want to go through, it's fairly technical, that will show you that Paninian instrument of grammatical analysis, how it plays a very significant role in the mathematical development. And perhaps mathematicians of that time was, they got their inspiration from this Paninian idea of Lopa to accept zero as a number in its own right. You see, if I go further back, the furthest one that we can trace is perhaps in Gopatha Brahmana. Brahmana is one of the earlier layers of Sanskrit Vedic literature. After the Samhitas, Brahmana, then Aranyaka and Upanishada. So Gopatha Brahmana, you find this Chitram Kham Iti Uktam. Kha happens to be the most common parlance of zero used in ancient India. See, Kha means the sky. the vast, limitless expanse. This is something called Bhuta Shankha. Many other references, equivalent references were made to understand and communicate the idea of zero. Gagana, Ambara, and on and on and on. This is a whole complete dictionary of Bhuta Shankha, not just for zero, for every other numbers, right? So that's the oldest one. And then the last one that you can see here, mentioned by Manjul in the morning talk again, this is Brahmasputa Siddhanto by Brahmagupta, who talks about Dhana Dhanam, Rinam Rinayor, Dhana Rinayor Antaram and Shamaikya, the Dhana and the Rina, as he has pointed out, the positive and the negative. And Brahmagupta first formally utters this principle, keeps it in writing, but that doesn't mean that it was invented right at that point. He just put it down as far as we know. There are many things that are lost in ancient Indian tradition. Thousands of manuscripts are laying here and there over the world, which are yet to be deciphered. There you see this Shamaikya Kham, it tells the positive and negative number, if they are of equal value and they are added, it becomes zero. That's not a placeholder zero, that's a number in its own right. Just like 2 minus 2 equal to 0. It's a number in the same footing as others. And just prior to that, I have mentioned Aryabhata. He didn't invent zero. He used it in his complicated calculations in Katapayadi system. He is enunciating the decimal place value system in his Aryabhatiya. Ekam, Dasacha, Satancha, etc., going up to Kuttar Budancha Brindam, 10 to the power 9. And he is explicitly telling you that Sthanat Sthanam Dasagunam Swat. From one place to other, this is the place value notation. From one place to other, Dasagunam. You have to multiply a place by 10. That's what you do now. The decimal system of place value system of numbers. You see, if you look at this number 0, you may think that how this English word came into being. Just like the word sign was explained today morning by Manjul. It comes from Shunya, Suna Yat, right? And then as a semantic extension, it's actually grammatically, it comes from the verb she, which means, this word is Shunam, which means lack, which means, something hollow, and so on. And from semantic extension, it leads to this idea of nothingness. And as I told you already, and you can see in your screen, that there were several equivalent words. And be very careful to note the last two. Shunya was also represented as Purnya and Ananta. That's the philosophy, that's the backbone of our whole civilization. And this comes into being when you comes to the story of zero. Shunya was also referred to as Purna, as a kind of dichotomy between nothing and everything. The God himself was seen in Indian culture like that. Minuter than the minutest and larger than the largest simultaneously. That was the idea of this number Shunya. And you see, this number later went to Arab in the court of Caliph Al-Mamun in 9th century, and it got translated by Al-Khwarizmi as Sifra, which literally means nothing. So that dual meaning of nothing and everything was lost. That philosophy was lost. It became just a representative of nothing, Sifra. And that was later by this Fibonacci, whom you had again mentioned in the morning talk. In 1202, when he was writing a book, Liber Abaci, the book of numbers, Fibonacci translated it as Zephyrum in Latin, which means very insignificant, light westerly breeze, almost insignificant. You see that nothingness was at the back of his mind. And this word Zephyrum later gradually changed in Europe, in various civilizations, in Venetian dialect. It changed to Zefiro, and then at a point of time, zero in French, zero in Spanish, and zero, the modern word in mathematics. That's the journey. The whole journey, if I get into details, will take more than 1 hour if I have to explain that. So I'm not going to do that, and this is just one piece of interesting information. The first written appearance of the word zero in Europe is only in, as you can see there, 1491, in a Florence book by Filippi Calendri. The book is De Arithmetica Opusculum, 1491, my friends. And you see, if you want to listen to it, if you want to know details of this idea of the number zero, it's not just with the perspective of India. You have to justify another point, that there are so many other great ancient civilizations. What about them? What about their enumeration system? Why didn't they get hold of zero? And if they got hold it, why do I bother about Indian zero only? In what sense Indian zero is considered as the true progenitor of our modern zero? So to know in details, it takes hours. So what I can do, I humbly invite all of you to my gallery. This is Zero Gallery instituted in Kolkata in my institute, Ramakrishna Mission Residential College last year. Anytime you come to Calcutta, you are most welcome to visit this Zero Gallery, where I have tried to put side by side in this permanent panel exhibition the whole history of zero across 5,000 years of human civilization. And that also led to one particular film, Traces of Zero. So nothing that was showed last December in lockdown. There is also a new film, there is how, yeah. This is the 40-minute documentary. I'll just show you 1 minute script of just a snippet of that. Zero. No single mathematical creation has ever been more potent for the general ongo of intelligence and power. In this engaging tour of pictorial history, the journey takes us through the Egyptian hieroglyphs, Inca Babylonian clay tablets, Mayan glyphs, followed by the great Greek civilization, the mighty Roman Empire in the west, whereas we also come across the Chinese rod numerals, the lofty philosophy, embracing the concept of nothingness by the ancient Indian seers, which gradually paved the path for emancipation of zero as a number in its own right. I think lack of time, we can't get into details of that, but this is available in YouTube. It's a 40-minute documentary. And if you want to listen to more formal lecture on it, this is the lecture that I can refer to you, a 1-hour lecture given at IIT Gandhinagar a few years back. The reference is there. You just write my name in YouTube, will come to my name with mathematics, right? And this is the culture. This is the culture, Indian culture, that actually gave rise to this peerless concepts of zero and decimal place value system. If you appreciate the role of zero in mathematics, you must have a place value system. Otherwise, the importance of zero cannot be realized. And both these two are the original contribution of India. I just ask you to read, say, the second one of them. The most of the great discoveries and inventions of which Europe is so proud would have been impossible without a developed system of mathematics. And that in turn would have been impossible if Europe had been shackled by the unwieldy system of Roman numerals. This unknown man who devised the new system, the system is the decimal system. From the world's point of view, after the Buddha, the most important son of India, his achievement, though easily taken for granted, was the work of an analytic mind of first order. Yes, nowadays it's easily taken for granted. We all learn numbers this way. But first one who devised this was, as you can see, this is said by one of the great historian, A.L. Basham, in his book, The Wonder That Was India. And there is Bourbaki, a group of eminent European mathematicians, writing in the book that our actual decimal system, which by the agency of the Arabs is derived from Hindu mathematics, where its use is attested already from the 1st century of our era. It must be noted, moreover, that the conception of zero as a number and not just a simple symbol of separation. That's the placeholder, 101 and 1001. The role as a placeholder, but it's a pure number, not just a simple placeholder. That conception and its introduction into calculation also count amongst the original contribution of the Indians or the Hindus. And you see, when it comes to Roman multiplication, this is like this. It's a very clumsy way of doing things. It's just multiplying 58 by 25, which class 2 students can do easily. But you look at the right hand side. That is to be done if you want to understand by Roman system that you are multiplying this number. So you see, shackles, unwieldy Roman numerals, that's one example of that. You see, if you look at this idea of place value system, again, my question is, how far can we push it back? The furthest that I could find is this reference in one Vedanta Boshumitra in his book on Madhyamak school of Buddhism. He refers to this idea and explains dharma, the state, from one state to other, how it changes. Salakshana dharana the dharma. He is referring to a fantastic, statement is translated here, when in the units position has the value of unit. The marker, when put in the units position, has the value of unit. In the hundreds position, that of 100. In the thousands position, that of 1,000. So this is clear understanding of place value system. And this is in 1st century CE. If you look at the Vedic corpus in Rig Veda, you have more than 3,000 numbers, oral number names in Sanskrit. Look at these number names. They are so beautifully designed grammatically. Look at the number like Sapta Satani Vinsati, 720. Shahasrani Shata Dasa, 1,110. Just, suppress these placeholder names. You see the number in written form pops up. That's the beauty of this Sanskrit number vocabulary. And that's what Datta points out in one of his good articles, that one can conclude that structure of Sanskrit numeral system contains the key to the decimal place value system. You see, this has a polynomial aspect also. Certainly you know about polynomials. And for example, if I take that as an example here, this number here, the polynomial here, 2x cubed plus 2x plus 2. You see, the polynomial can also be represented by a ordered tuple of coefficients. That's what the ring theory that Manjula was talking about in the morning. There the polynomials are represented by these tuples. The fantastic thing is when you want to represent the polynomial as a standard notation, the first one, you just drop one particular term if it is not there. Just like here, the term with x square is absent. You don't write 0x square. You simply write 2x cubed plus 2x plus 2. But when you want to represent it in the corresponding representation as an ordered tuple of coefficients, there you require 0. Just like if I just again go back to the Sahasrani Shata Dasa, they look at this, color coordination, 1,000, 100, 110 and no unit. That's the oral part. And when you come to the written part, it just pops up like 1x cubed, 1x square, 1x and nothing else, but the corresponding numeral, if you want to get out of it, the coefficients, it cannot be just 1, 1, 1. That will lead to a different polynomial. It will be 1, 1, 1, 0. So that's how there is a relationship between this oral Vedic Sanskrit number names and the written decimal place value notation. And this actually paved path for further generalization of polynomial algebra and other base systems like binary. And this was actually recognized by Newton himself. I have given a reference there in that particular book. Newton pointed out that I'm surprised why this didn't occur to anyone else, that these newly introduced doctrine of number can be automatically, it can work for polynomials in algebraic version as well. Why did it happen in India? It happened because of this philosophical backbone. These rules are philosophical statements, Purnamada, Purnamida, etc. It says Purnasya, Purnamadaya, Purnameva Vashishyati. Now, if you say it's philosophy, it's philosophy. Of course, it's not a mathematical rule. But you see, it is paving the path for this mathematical rule to be appreciated. When infinite system, you take infinite number of things out of it. There's an infinite set, you take out a subset of infinite element. What remains is still infinite. The Purna, as I told you, is also Shunya, and you see 0 minus 0 also gives you 0. So philosophically, Indian society was ready to reach at that. As I told you in this Kathopanishad, Anoronyan Mahato Mahyan, minuter than the minutest and larger than the largest, simultaneity. The idea of Maya or void in the Vedanta philosophy, the Abhava in the Noyaic philosophy, Nishkala Shiva, partless emancipation of God Shiva. And even in Mahayana Buddhism doctrine of devoidness, Shunyata, the idea of Nirvana is complete Shunyata, to imbibe the concept of complete Shunyata, Chatushkati Binirmukta, which is considered as the Prajna Paramita, the highest form of knowledge. The society was ready to receive this concept of zero as a number, philosophically. So when mathematicians living in the society proposed that we need to have a numerical symbol representing nothingness, I have a pen, I take it away. How many pens do I have? You say no pen, but that's not the direct answer. Direct answer requires a numeral. I have 0 pens. We don't talk in this language. So till we talked only, oral, we didn't require 0. The point of time when we started writing, 0 was necessary. And here, since I'm running out of time, I'm finishing with this. Will our search ever find anything new?
Where have the rest of evidences gone?
Now.
Will our search ever find anything new? The these questions you have inherited now, and the history of zero continues with you.
When these fantastic things actually originated in India. And here I leave you with this reference book where you can find what I have been talking about till now. This is a supplementary to the Zero Gallery, and this is, of course, incomplete list of reference. Thank you.
Any questions? Yeah. Okay. Just providing the cordless.
I can't hear you. Can somebody give me a microphone? Yes? Right.
At the end. Kindly keep.
Zero? See, my point in relating Purna and Shunna is what we have historically written over there, that I can give you concrete reference where the word Purna is used in Bhaskara, Bhaskaracharya. Rasaguna Purna Mahishama Shaka Nripa Samaye Bhavat Mamatpatti. And if you just decipher this, you will get this number, his time of birth, when you take this Purna as a zero. Right? So metaphorically, what you are talking about, perhaps these are other way of looking at it, interpretation. My point was very simple, that the nomenclature Purna, along with many others, these are called Bhuta Shankha, and they were used simultaneously to maintain the prosodical need. Those time it was always mostly in poetic metrics. So due to the need of prosody, every number had very many names. So equivalent to this was Purna and Ananta as well. The idea, as we perceived it, comes from the philosophy of Indian schools, where this Purna, the God himself, is also considered as Shunna. As I have given a reference of Maitrayana Upanishad, where God is being invoked as Esa Shuddha Shunya Shantaha. So my point is this, that this idea was already there in the society. This is unlike what happened in West. If you look at the Greek society and Greek culture, they also reached this kind of idea of zero and nothingness, but they didn't accept it. They challenged it. They said, how can nothing be represented by something? And with all these kind of conundrums, they stopped it there. They knew it, but they suppressed it. Indian society didn't do it due to this philosophical backbone of India. That's what my point is. I think, sir, we can, since the time is very short, we can talk about it one-to-one personally, right? After the talk, okay? Okay. Okay.
Thank you so much, Dr. Parthasarathi. And the next speaker is Mr. Jean Michael Delia. Mr. Jean Michael Delia is a mathematician and philologist, Sanskrit, Latin, and Greek. Having dedicated his PhD thesis to the Sulba Sutras, his researchers focus also on the astronomical achievements of Savai Jai Singh of Jaipur and on the progressive discovery of Indian astronomy by the European scholars. Today he will be talking about geometry in Sulba Sutras. Mr. Jean Michael Delia. I invite you, sir.
Hello. Topics: History of Mathematics and Science and Civilization of India. And today I will devote this communication to the Shulba Sutras, a topic appertaining to both subjects. We owe to Sen and Bag the complete edition, translation and commentary of the four principal Shulba Sutras, edited by the Indian National Science Academy in 1983. 1 century ahead, in 1875, as you see, the discovery of this kind of text was due to Georges Thibault with his arch article on the Shulva Sutra, and also with his edition with commentary of the Bodhayana Shulva Sutra and the commentary by Dvarkanatha in a periodical called The Pandit, edited in Banaras between 1875 and 1877. Actually, this followed other publications about Indian mathematical works in general. In 1817, Colebrook wrote his algebra with arithmetic and mensuration from the Sanskrit of Brahmagupta and Bhaskara in London. In 1834, Charles Wyche wrote a long article about different Indian mathematical works. And also in 1874, Kern edited the Aryabhatiya with the commentary Bhattadipika of Paramadishvara in London also. Already in the meeting of the Société Asiatique, in Paris on May 1878, Mr. Rodet gives some explanation about the mathematical measures used by the Brahmanists, as he called them, in the construction of their altars. The Sanskrit treatise, which deals with these interesting questions, has been recently published in India, they say, with commentary and English translation. Of course, this alludes to the edition by Thibault some years ago. Actually, Léon Rodet was the first French Sanskritist who interested himself in mathematical Indian works. He wrote 3 articles in the following years, in 78, 79, and 80, 3 long articles about mathematics and especially Indian mathematics. And some of his articles addressed to the content of the Shulba Sutra, as we will see a little bit more later. To this list, I must add the study by Vibhuti Bhushan Datta, The Science of the Shulba, edited in Calcutta in 1932. And if I may, also my own book, I published in Geneva in 2016. And happily my book is in French, but I hope to translate it into English if I can find an editor. Now, about the Shulba Sutra, treatise of the court, there are practical manuals giving the measurements necessary for the construction of the numerous structures needed by the Vedic ritual. By instance, there is a Garapatya, which is a oath altar sphere, which is round and represents the earth. The square is represented by the Hahavaniya, which is an offering fire, which figures the sky, abode of the gods. And there are also some trapezoids called Vedi, offering table, whether with curved sides or with right sides like the Mahavedi above in the figure. This Mahavedi has 2 shronis, that means hips, which in fact are the corners, the western corners, and 2 amsa, that is shoulder, which are the eastern corners. As of an animal looking eastward. Of course, these structures were always disposed symmetrically to the west-east line, called the Prachi line or the Prishtya line. And usually the Mahavedi also bears a large altar or agni made of 1,000 bricks arranged in the shape of a bird of prey called Shenachit. Sienna sheet like here. So you see there are 1,000 bricks arranged in 5 layers of 200 bricks. And you have the figure of one layer here. You can count, but you won't have the time that there are 200 bricks on that layer. No, this Agni must have an area of 7.5 square Purusha when it is constructed for the first time. 8 Purusha and a half in the second time, and 9 Purusha and a half in the third time, as it is prescribed in the second chapter of the Bodhayana Shulba Sutra. That means that the altar is firstly constructed as a squared bird of prey, where you have here the wings, and then you have also the tail and its extension of the tail and also of the wings in order to make 7.5 square Purusha. Of course, every square has 1 Purusha of side. And from this figure, very simple, squared figure, you have to transform into a Sienna sheet with curved wings, as we have seen, or into other shapes like the Rata Chakra Chit, or the Ubayata Progachit, which is a rhombus, or into a Kankachit, which is another bird with legs this time, or into a Kurmachit, which is of course a turtle, and many other forms whose areas must always be the same, that is 7.5 square Purusha for the first construction. So this prescription that all these Agnis have to be of the same area means that the Shulba Sutras must propose some area invariant transformations, like the quadrature of the circle. But since the square is the very basis of everything, let us first explain its construction. So this is the first construction of the square with only circles. So first you trace the east-west line, the Prachi, and then you put a peg here. A peg to which a cord ended by 2 loops can be attached. If you do that, if you attach it by 2 loops, you have this kind of circle. But it can also be attached by only 1 loop, which will give you this kind of circle, or this circle. No, you can draw a straight line through the intersections of these 2 circles in order to put 2 more pegs here and there. And with these 4 pegs as center, you can draw 4 little circles like this. And you will have very easily know the square. So this is the first construction of the square. But I will now show you another construction, which is also more interesting about the content of the Shulba Sutra. And this is this one. Here, you have a first sutra saying Ataparam, means another what? Another construction, Karanam. This is the commentary, of course, which says that you have to add Karanam. So this other construction works this way. You put 2 pegs to begin with, and of course the distance between the 2 pegs is the side of the square. Now, you use a cord with 2 loops at its end, and this cord must be as long as twice the side of the square you want to construct. And in fact, you put a mark in the middle of the cord. So the cord will become like this. So this is a cord double of the side of the square. But of course, you have to think that this cord is only attached to the first peg, that means the left peg, not at the right peg. At the right peg, in a way, there is the mark. No, this is, as say the text, in order to draw the prachi. The prachi is in fact the side of the peg, the side of the square, sorry. next sutra, you have to take the western part of the chord, and on that western part to put a mark here at 3/4 of the length of the side. This is called the Nyanshana, Tanyanshanam, which means that in fact the chord will have to be bent with the help of this mark. Then you have another mark which is made in order to have the shoulder, the amsa. You see, amsartam is written in the text. And you put that mark in the middle of the western part here, the green mark. And then you bend the chord this way. So you bend it by pulling it at the red mark. So that the two lengths you have now in the chord is 3/4 times L and 5/4 times L. When reversing the chord to the right, sorry, I forgot this. Of course, with this length, you will have a right angle in that triangle. Now, when reversing the chord, you can have another corner to the east, another to the northeast, and another to the southwest, so that you can now draw the square. Of course, this construction means that the Shulba Sutra knew Pythagoras' theorem, or rather, it's reciprocal. That is, if three numbers a, b, c satisfy the so-called Pythagoras relations a to the square plus b to the square equals c to the square, then the triangle whose sides have length a, b, and c has a right angle opposed to the side of the length c, which is usually called hypotenuse. For instance, here we had these three lengths, and if you put L equal 4, you have these three numbers, 4, 3, and 5, which are, of course, number A, B, C satisfying the relation a to the square plus b to the square equals c to the square, because 4 to the square is 16, 9 to the square, 3 to the square, sorry, is 9, and 16 plus 9 is 25, which is 5 to the square. In the Shulba Sutras, of course, this property is expressed. But I call it the property of the diagonal and not the Pythagoras theorem, because it's not explained in a triangle, but in a rectangle. So the first sutra, 45, is the chord stretched across a square produced an area of the double size. This is what we call the square case. And the second sutra, 48, the diagonal of an oblong, produced by itself both the areas which the two sides of the oblong produce separately. This is the oblong or rectangle case. So let's say the Pythagoras theorem is separated into two cases, the square and the oblong cases. And the Sutra 48 continues with this, which is a list of different numbers playing the role of A and B in the Pythagoras relation. So you have 4 and 3, 12 and 5, 15 and 8, 7 and 24, 12 and 35, and finally 15 and 36. If you calculate the third side, that's the diagonals, in fact, you find 5. And these three numbers are called Pythagorean triplets. So you have also 12, 5, and 13, 15, 8, and 17 that you can figure like this, so that you can see that the blue square is completed by a figure with a L shape in a way that this figure contains a square number of little square. In this figure, you have 64 little square that you can arrange in a little square of side 8, of course. That's why it works. Then you have 25, 37, and 39. Now you can see that the sutras separate the, let's say, Pythagoras theorem in two cases, the square case and the rectangle case. The square case can be understood very easily with this figure. And this figure is also found in some vases of the Indus civilization, which probably means that the Indus civilization already knew this square case, at least the first case of the theorem. But the second case, the rectangle case, is of course not understandable with a figure. It needs calculation, as we have seen. Now we can have a look also at the wording in Sanskrit. The first sutra, 45, says that bhumim karoti, produce an area. So in the verb karoti, you have implicitly the idea of a square. Same in the Sutra 48, where you have Yat Pratakbhute Kurutas Tat Ubayam Karoti. Again, you have the word, the verb karoti or kurutas, which is another form of the same verb. And implicitly in these words, you have the construction of a square, which is not the case in Greek, at least in Euclid's element. So I will pass this very shortly. That were they remarked that the tetragonon, you know, the last word of the first line, explicitly said that you have to build a square. It's not only a verb here; there is a substantive to say that it's a square. In other texts, like this one by Diogenes Laertius, or this one by Theon of Smyrna, there is only one verb which implicitly says that you have to build a square. So this looks a little bit like the Sanskrit formulation here, but instead of the verb karoti, you have dunatai, which means can. And from karoti, you find karani, producer, in Sanskrit. From dunatai, you find dunamis, and they have the same meaning, which is finally the square root. So there are some parallel to be expressed between some Greek text and some Sanskrit text. About geometry and ritual, you have of course remarked that in the Shulba Sutra, the ritual is always there. We are making geometry, but it's about the ritual. In the Greek text, it's quite different, but you find some traces of a relation between rituals and geometry. In this text, for example, Apollodorus, the calculator, says that Pythagoras sacrificed an hecatomb. Of course, to celebrate his discovery of the theorems. That means that Pythagoras sacrificed, probably ritually, 100 oxes. And there are other texts saying that he sacrificed only one ox, but there is definitely a relation between the ritual and the geometry. Now we will see, of course, the very famous circulator of the square, which seems to be necessary in Indian texts because, as I told you, the aim of the ritual is to put in relation the sky, which is square, and the earth, which is a circle. So the first transformation given by the Shulba Sutra is the circulator of the square. So you begin with a square, you take half of its diagonal that you will turn to put it on the west-east direction, like this. And then with a third of what is outside the square, you will draw a circle, and this circle is supposed to have the same area as the initial square. That's the construction given by the Shulba Sutra. Every Shulba Sutra we know about the transformation of a square into a circle of the same area. But of course, the Shulba Sutra, and this is a characteristic, always give the reverse transformation. That is the quadrature of the circle. And in fact, you find two quadratures in the Bodhayana Shulba Sutra. And I will show you only the second one, which is very easy. You divide the diameter of the circle into 15 parts, and you remove 2. And that is what is called the gross side of the square. The gross side translate Esha Nitya. And Esha Nitya could be cut into Esha Nitya, which means the usual side, or Esha Anitya, which is supported by the commentary, which says Stula instead of Esha Nitya, which means gross, coarse. So that's why Thibaut probably translate this sutra as he did, using gross instead of usual. But as far as the Bodhayana Shulba Sutra has also another quadrature, much accurate than this one, it's possible that the author of the Bodhayana Shulba Sutra could have tried to say that it's the usual side because this quadrature is the one which is found in every Shulba Sutra. So it is usual. It is traditional in a way. Another transformation is very interesting. It's the square into a rectangle. Before that, in the Shulba Sutra, you have the reverse. You have the transformation of a rectangle into a square. Now let's see this one. So you have to transform this square into a rectangle. And the sutra says you can cut it by the diagonal, then cut again 1/2 in 2 parts, and remove the 2 parts in order to build a rectangle, which is of course of the same area as the initial square. The problem is that this transformation is not general enough. Normally, you should be able to transform a square into a rectangle of any breadth you want, like this. For example, you cut it by the breadth of the rectangle, and you have a sutra in the Bodhayana Shulba Sutra, it's the following, saying that you have to place, what is left, that means what is on the right here, elsewhere, but you don't know exactly where. So that Thibaut wrote in his edition that he doesn't venture on a translation of this sutra, as it doesn't clearly appear to what geometrical operation it refers. Happily, and then he also had, moreover, there seems to be a lacuna in the commentary. So that means that he couldn't translate this sutra with the help of the commentary, of course. But happily, I have found in 3 manuscripts from Pune, Tanjore, and Ujjain how to complete this commentary, and I will show you now how it worked with the commentary. You have to extend this right side of the square, then through the point A to draw a diagonal that will cut the extended side on B. And from B, you draw a parallel to the top side of the square that will cut the extended left side of the square, so that this rectangle is the rectangle you wanted, because these 2 figures, the square and the rectangles, have the same area. So after this short overview of the content of the Shulba Sutras, which I hope has given you an idea of their main characteristic, I will leave the field to my colleagues. Of course, there are many more things to say, and that's why I wrote a book about the Bodhayana Shulba Sutra and its commentary. If you want to know more about it, don't hesitate to contact me. Thank you for your attention.
Do we have any questions?
It was a very, very nice presentation. Thanks so much, Jean Michael Dilir. I have one short question to you. You were mentioning about this different kinds of chitis, Kurma chiti, Ratha Chakra chiti, and so on. I was curious to know whether you have a demonstration of all of them or you have a demonstration for a few of them.
J'arrive pas à envoyer.
Is he there or he's not there? He's not there, I think, right? Oh, he's there.
No. Has he gone offline?
No.
Mr. Jean Michael Delia.
No, you don't hear me.
No, you don't hear me. I suppose.
Are you
yes.
audible?
You hear me.
You hear me. Okay.
Can you repeat the question?
Can you repeat the question, Professor Masudana?
Yeah, I had this question, simple question. So earlier I remember you having some physical pieces demonstrating these kinds of chittis that you are explaining with 200 pieces, assembling them together. Do you have for all of them, all the chittis, or do you have for a few of the chittis?
No, in my book I have all
In my book I have all the plans
for all the chittis, of
for
course.
all the chittis, of course.
And of course I translated all the
Of course,
text.
I translated all the text you recommend to me,
so you can see how it
so
works.
you can see how it works.
Is it an answer to the
Is
question?
it an answer to the question?
No, my question was, you had made these physical pieces for children to understand how it is to be.
Yes, sorry, I understand.
Okay, sorry, I understand.
I have
Do you
only
have
one.
for all?
I have only one.
I have only
Do you have for all
I have
the
only
chittis?
the puzzle for
the
the
puzzle for the Shinyatsu.
Yes, correct.
Shinyatsu.
not the other one.
Do you have it
Not
for
the
all
one.
chittis?
Excuse me?
Excuse me?
Do you have it for all chittis or only a few chittis?
No, only the
No,
Shinachi.
only the Shinyatsu.
Okay.
Thank you so much, Mr. Delia. Thank you. So the next speaker is Professor M.D. Srinivas. Professor M.D. Srinivas is a theoretical physicist. He obtained his PhD from the University of Rochester, USA. His research work in theoretical physics has been mainly in the fields of quantum optics and the conceptual and mathematical foundations of quantum mechanics. So may I request Professor M.D. Srinivas to kindly talk about the combinatorics in Pingala's Chanda Shastra.
Thank you very much. It's a great honor to speak in this conference on India's contributions to mathematics through the ages, which is being organized in this on this occasion of 75th year of our independence, Azadi Ka Amrit Mahotsav. I am going to speak on the contributions of Indians to combinatorics, especially of the ancient text of Pingala's Chanda Shastra, which is the text of process. So this is roughly the outline of my talk. Combinatorics is a branch of mathematics which deals with enumeration and counting of combinations of various entities. Such techniques were developed in India in the context of Ayurveda, that's medicine, Chandas, that's prosody, Sangita, music, and of course mathematics, and even in other disciplines such as architecture. I will mainly speak on combinatorics of what are called the syllabic meters. I will explain what it is. In Pingala's Chanda Shastra, which was a text written around 300 BCE. Mainly the combinatory ideas are contained in certain tools known as Prastara, which is making an enumeration of all metrical forms, the prosodial forms of young syllables, then finding out the total number of them, then finding out which prosodial form is in which place in that enumeration that we have made by our rule. Like that, various combinatorial ideas have been discussed in Pingala's Chandas Shastra. I will in the end briefly touch upon combinatorics of Matravritas, what are known as moric meters. I will explain what they are when it comes. This is the larger timeline of development of combinatorics in India. The left column is Chandas, that is prosody, that is the science of meters in poetry. It starts with Pingala around 300 BCE, then comes to Janashreya and Virahanka in 600 of the Common Era. Halayuda, who wrote a commentary on Pingala's sutras in 950. Kedara Bhatta, who wrote a very famous text called Vritta Ratnakara. Gopala, who is a commentator of Virahanka's work. Hemachandra, who wrote works on several subjects, including prosody. Prakrita Pingala is a text in Prakrit. Virahanka's text is also in Prakrit. Then it goes up to Damodara and Narayana Bhatta in 16th century. In music also, there is a continuous history of study of combinatorics. Starts with Bharata's Natya Shastra itself, which also mentions Pingala's ideas. So Bharata postdates Pingala. Parshvadeva, Shangadeva, the author of the very famous text Sangeeta Ratnakara. Simha Bhupala is a commentator of Shangadeva. This music tradition, especially the combinatorics of musical rhythms, goes up to our contemporary period. The Charaka Sushruta Samhitas date back to perhaps 600 BC or earlier. The current versions may be dated to around 300 BCE. The Sushruta Samhita has some combinatorical ideas on the various rasas and how they can be mixed. Varahamihira discusses the combinatorics of perfumes. Brahmagupta's mathematical text has a chapter, astronomical text, Brahmasputa Siddhanta has a chapter on Chandas Chityuttaradhyaya. Sridhara and Mahavira wrote mathematics text where combinatorics is discussed. Bhaskaracharya, the famous author of Lilavati, has the last chapter of his works is on Ankapasha, which is combinatorics. The greatest contributions came from Narayana Pandita, who also wrote a chapter on Ankapasha or combinatorics in his 14th century work, Ganita Kaumudi. Now, before going into discussing what Pingala did, we have to see the basic terminology of Sanskrit or prosody in all Indian languages. A syllable or an akshara is a vowel or a vowel with one or more consonants like ya, shtihi, shra, things like that. These are all syllables. A syllable is lagu if it has a short vowel. Now, even a short syllable will be a guru. Guru is a heavy syllable, lagu is a light syllable. This is the definition of a light syllable, that's a consonant with a short vowel. But even a consonant with a short vowel will have to be considered guru if it is followed by a samyuktakshara, conjunct consonant. I will explain it in a second. An anuswara or a visarga. And all other syllables are heavy. So we will explain this lagu and guru symbolize the classification of syllables, which is at the basis of the science of prosody in this following example. This is the first verse of Kalidasa's Abhigyana Shakuntalam. Ya Srishtis Rashturadhya Bhati Vidhivutam Ya Havir Yacha Hotri. These are the various syllables in this first quarter, first pada of Kalidasa's first verse in Abhigyana Shakuntalam. It has 21 syllables. It's in a meter called Sragdhara. First syllable is Ya. This is a Dirgha, so this is a Guru. Second syllable is Sri. This is a Hrasva, but it is followed by a conjunct consonant Shtihi. Therefore, this is also a Guru. Shtihi, since it has a Visarga, is a Guru. Sra is a conjunct consonant, but it is Hrasva, but it is followed by another conjunct consonant. So, any syllable which is prior to a conjunct consonant is a Guru. Shtu is a Lagu. It's a short syllable. Though it's a conjunct consonant, it is not followed by a conjunct consonant. It is a Lagu. Ra is a Dirgha, Guru. Dya is a Dirgha, it's a Guru. Va, Ti are all Lagu. Vi, Thi, Hu, they are also Lagu. Tam, it's with Anuswara, it's a Guru. Ya is a Guru. So, this Ya Srishtis Rashturadhya Vahati Vidhivutam Ya Havi, Ya Chahotri has 21 syllables and it has this Guru Lagu pattern. Then there are 8 ganas. Every triplet of Lagu and Guru is taken as a gana. Obviously, there are 8 such triplets and they are called Yagana, Ragana, Tagana, Bhagana, Jagana, Sagana, Magana and Nagana. We will not be discussing these ganas later in this talk. This is the verse which defines the ganas. Adi Madhya Vasaneshu Yarata Yanti Lagavam Bhajasa Gauramam Yanti Manautu Guru Lagavam. And this Ragdhara meter is defined by this verse. Nabhnair Yanam Trayena Trimuni Yatiyuta Sragdhara Kirtiteyam Marabhana and 3 yas. With a yati or a pause after every 7 syllables is Ragdhara. And surprisingly or beautifully, this verse itself is also in Ragdhara meter. Now we will straight away jump to Pingala's Chandas Shastra. Pingala is a junior contemporary of Panini. Panini is supposed to have flourished in 500 BC. There are many stories of ancient times where Pingala and Panini are combined together also. Chandas Shastra comprises of 8 chapters. It's in the Sutra style. It has 315 sutras. It has been commented upon by Halayuda in the 10th century and by Yadava Prakasha in the 11th century. The first chapter deals with definitions and the very first sutra, Shvi Stream, defines the Magana. Very interesting mathematical point about Pingala's Chandas Shastra is that it is using what is called Bhuta Sankhya system of numeration. That is, a word such as Vasu, there are 8 Vasus. So you use the word Vasu to mean the number 8. This is used in general in Sanskrit literature to denote numbers. They use what is called the Bhuta Sankhya system. Apart from that, we have what is called the Katapayadi system, for which the earliest works come much later, around 4th century, whereas Pingala's Chandas Shastra of 3rd century BCE already had the Bhuta Sankhya system. Then Pingala goes on to discuss Vedic meters. Like Panini's grammar, Pingala's Chandas Shastra has also both the Vedic meters and the classical meters of Sanskrit. 6th and 7th chapters deal with most of the standard meters of Sanskrit poetry. And it's in the 8th chapter that Pingala discusses these 6 combinatorial tools that I said right at the beginning in the outline, called Prastara, Sankhya, Nashta, Uddishta. We will explain what each of them are and how Pingala does very interesting mathematical study of meters. First is to write down all meters of a particular length. As we see, each metrical form is a sequence of Lagu and Guru, G and L. So it's what can be called by mathematicians as a binary sequence with the 2 kinds of entities in the sequence. A prastara of 1 syllable meters will just look like this. Prastara of 2 syllable meters, there are 4 of them, they are arranged like this. Prastara of 3 syllable meters, there are 8 of them, they are sequentially arranged like this. The rule for sequentially arranging it is given in these 4 sutras. What Pingala says is, form a GL pair, then write that GL pair below itself. Insert on the right G's and L's. Now, this is a recursive rule, then you should keep doing the same thing. So, the 2-syllable prastara is written below itself and the right hand side is filled with G's and L's. To get a 4-syllable prastara, the 3-syllable prastara, these 8 rows are first written twice, one below the other. And then G's and L's are put in the end. So this is Pingala's rule for prastara. So this way, all the 2 to the power n metrical forms of n syllables are ordered in a sequence. The top row is all GGG, the last row is all LLL. There is another rule for prastara which is given in a text called Vritta Ratnakara, which comes in the 10th century. I will not describe this rule in detail, but the way this rule proceeds is, you can be anywhere in prastara, scan from the left, locate the first Guru, and below that write a Lagu, bring down the 2 syllables on the right as they are, whatever syllables are to the right of this Guru. To the left, you put Gurus only. So, for instance, here, LG, LL, the row below that, identify the first guru, put a L below that, bring down these two L's here, fill up the left side with G. Go on till L's are reached. A very important and interesting property of this prastara is its relation with binary representation of numbers. So, if you set G is equal to 0, L is equal to 1, so I have rewritten this prastara of 4 syllables with the G as 0, L as 1 here. Then you take its mirror reflection, that is 1000 becomes 0001, 1100 becomes 0011. Then the binary number that comes here is the binary number of the row minus 1. This 11 is binary representation is 3. 100 in binary representation is 4. That is 5 minus 1. This 1010 in binary representation is 10. And you see that is 11 minus 1. So like this, there is a one-to-one correspondence between prastara, the row number of the prastara, and the binary representation of the associated binary sequence. If we put G is equal to 0, L is equal to 1, it was using this that Pingala constructed various interesting mathematical problems associated with this prastara. The first mathematical problem is computing 2 to the power n. Pingala does it in 4 sutras, and notice that the word shunyam appears, though it appears as a mark only in Pingala's sutra. Pingala is giving a rule for finding the nth power of a number by a much smaller number of operations than merely multiplying the number by itself. If you want to multiply the number by itself n times, you are doing n multiplications, whereas Pingala's algorithm has much smaller number of squarings and multiplications. The rule of Pingala, I have stated here, it is based upon these two, what may be called the power laws, which were very clearly known in Pingala's time to the Indian mathematicians. I will explain Pingala's rule for taking the power with a simple example. The rule starts like this. Supposing you want to calculate 2 to the power 21. You want to know how many rows are there in the prastara of the 21 syllable meters. The first rule is halve the number and mark 2. If the number cannot be halved, deduct 1 and mark 0. 21 cannot be halved, deduct 1 and mark 0. So you have put a mark 0 here. The next rule is proceed like this till you reach 0. So next time you have now 10. 10 can be halved, and so mark 2. So I have put a mark. Now you have 5 here. 5 cannot be halved. Deduct 1 from 5 and then do the halving. Then mark 0. 4 can be halved. Halve it, mark 2. 0, 2, 0, 2. 2 can be halved. Mark 2. 1 cannot be halved. Subtract 1. Mark 0. So this is the sequence of numbers that you get. Sequence of marks. Now you proceed in the reverse. Wherever 0 occurs, you multiply by 2. Wherever 2 occurs, you do a squaring. So 0, 1 into 2. There is a 2, 1 into 2 squared. There is another 2, 1 into 2 squared squared. There is a 0, 1 into 2 squared squared into 2. There is a 2, 1 into 2 squared squared squared. And last one is 0. Finally, you will get 2 to the power 21 is 1 into 2 square of the whole thing into 2 square of the whole thing into 2. So, for 2 to the power 21, Pingala's algorithm involves only 3 squarings and 2 multiplications and not 21, but it's a very optimal algorithm for finding the square of a number. And this algorithm was used for summing geometric series in later Indian texts such as Mahavira's Ganita Sangra, etc. Pingala's rule also, there are 2 sutras which tell you the sum of a geometric series like this. 1 plus 2 plus 2 squared plus 2 to the power n is 2 to the power n minus 1 minus 1. This formula also appears in Pingala's Chanda Sutra. Now there are 2 algorithms needed. One is, you know this prastara for, if you are thinking of 4 syllable meters, these are the 16 rows. Now suppose you don't want to write down all the 16 and I ask you the question, what is the seventh row? Or I ask you the question, what is the row in which GLLG appears? So the first question, GLLG appears. What is the row? Is called the ranking in modern computer science and mathematics or combinatorics. It is called Uddishta. And supposing the question is, what is the seventh row? That is called Nashta. That means you have already written the Prastara, but somehow it is lost. You just tell me the seventh row. Pingala gives algorithms for both these calculations, for standard procedures for both this, unranking and ranking as it is called in today's combinatorics. And he gives them basically based upon the relation that we noted earlier between the row number in the Prastara and the binary representation of that number. So I will just explain Pingala's algorithm for Uddishta. The Nashta algorithm is similar to the Sankhya algorithm, so I will not explain it in detail. The Uddishta algorithm is that you are given a metrical form, tell me which row it appears. So for that, Pingala's algorithm is in two sutras, and it can be translated like this. Pratilomaganam dvidladhyam tato gyekam jakhyat. Start with number 1, double it when L is encountered, double it and reduce by 1 when a G is encountered. So you scan the pattern from the right. There is another alternative algorithm. I will come back to it after 1 minute, but let me do an example for this. Supposing I want to find out what is the row number for the pattern LG in 4-syllable Prastara. So we start with 1. Since a G appears, nothing needs to be done. You have to come till the first L. Now you have a L here. You have to multiply by 2. Then there is a G. When we find a G in the middle, we multiply the previous number by 2 and subtract 1. Finally, you have a L. You multiply by 2. So it occurs in the 6th row. We can go back and check that it actually occurs in the LG occurs in the 6th row of the Prastara. There is another method given by Kedara Bhatta, which is more transparently related to binary representation. So I will tell you. It says place 1 on the top of the leftmost syllable of the given metrical pattern. Double it at each step while moving right. Sum the numbers above L and add 1 to obtain the row number. So let us do the same example. LG. Put 1 above the first Laghu or Guru, whatever it is. Double it at each step. 1 into 2, 2 squared, 2 cubed. Add the numbers above the Laghus. That is 1 and 2 square are added. To the entire thing, add 1 more, you get 6. So these are the two algorithms by which you can immediately find out the pattern LG is in the 6th row of the Prastara. This is a small Prastara, 4-syllable, but if you have Prastara of 21 syllables like Srabdara, where it will actually in the Prastara can be found out very easily by these kinds of algorithms. The last rule given by Pingala was a very interesting rule. How many metrical patterns are there of n syllables which contain R gurus, where R is any integer, 1, 2, 3, 4, etc. up to n? The same question can be posed. How many metrical patterns are there in a meter of n syllables which have R laghus, for instance? Pingala gives this answer in just 1 line, and various earlier sutras have to be used to understand this. The explanation is provided by Halayuga, the 10th century commentator, who calls, Pingala asks you to construct a Meru Prastara. Halayuga calls that tabular form as Meru Prastara. So I will explain the Meru of Halayuga. You start with one cell with 1. Below that one cell, you write 2 cells which overlap with the first cell. Similarly, below that 2 cells, you write 3 cells which overlap with the cells above. Similarly, you write 4 cells. Now, the rule for filling each of them is any number is filled by the sum of the 2 numbers above it. That is the meaning of Pare Purnam. And so 3 occurs here, it is sum of 1 and 2. 4 occurs here, it is sum of 3 and 1. 6 occurs here, it is sum of 3 and 3. As you can see, these are the well-known binomial coefficients. And in fact, this triangle became very famous. It was rediscovered in Islamic mathematics in 10th century, in China around 13th century, and in Europe first by Stiefel, and then a treatise was written on it by Pascal. So it is today called the Pascal triangle based upon his treatise. And this relation, each number is sum of the two numbers above, is nothing but this relation between the binomial recurrence relation between the binomial coefficient. That is at the heart of Pingala's Meru. There is a later version of this Meru that Varahamihira constructed. He was trying to work out from 16 different perfumes, if 4 perfumes are selected, how many variations are possible, and that is 16C4, that is 1820. Varahamihira asks you to construct a Meru like this, which is a rotation of Pingala's Meru. This 1, 1, 1, 1, 1, 1, 2, 3, 4, 5. So this 1, 2, 3, 4, 5 is the first row of Varahamihira, first column of Varahamihira's Meru. It says in the first column you put the integers. In the second column you put the sum of integers. So 3 is 1 plus 2, 6 is 1 plus 2 plus 3, 10 is 1 plus 2 plus 3 plus 4. And in the next column you write the sum of the previous sums. 1 plus 3 is 4, 1 plus 3 plus 6 is 10. These are what are well known as triangular numbers. Now Varahamihira says NCR can be found out going to the nth column and the rth row in it. And this construction of Varahamihira is based upon just the extension of the Pingala's. If you go on recursively replace this n minus 1 CR by the same rule, you will get this summation. This is a well-known rule. This was first discovered in Europe by Fermat, but this is the rule at the heart of Varahamihira's Meru. It was explicitly stated as Vara Sankalita formula, repeated summation formula by Narayana Pandita in his Ganita Kaumudi, which I mentioned. Now, this is a very interesting Meru, as you can see. It's a very simple way of calculating. Every time you don't need to sum everything. 35 is obtained by summing just 10 and 50, the previous 20 and 50, the previous entry and the previous one. 70 is 35 plus 35, 210 is 126 plus 84. Today we know this formula, NCR is n factorial by n minus r factorial into r factorial. This was first mentioned in the Patiganita of Sridhara and in the Ganita Sara Sangraha of Mahavira. I will not say much about Matra Vrittas, I think the time is running short. I will tell you the central point. You assign value 1 to Laghu and 2 to Guru. Roughly sort of the time it may take to pronounce a light syllable and a heavy syllable. Then LG, this metrical pattern will have 8 matras. In music it is called matra kalas. So these are called moric meters. A matra in Latin is called a mora. So Pingala is very briefly touched upon them, but the first work to give it in detail is the work called Vritta Jati Samuchaya Virahamka, written in 600. It is in Prakrita. Its commentary I mentioned was written by Gopala in 11th century. It discusses both the Prastara and the Sankhya, Virahamka's work. I will quickly tell you what are the Prastaras of Matra Vrittas. They proceed on the same rule, the way Vrittaratnakara rule proceeded. There are 2 ways of constructing. You construct first the Matra Prastara for 1 matra and 2 matras, then put them one below the other. This L is put here, this GLL is put here. On the right side you put a G for this, L for this. Similarly, 4 matra prastara is constructed by putting a 2 matra prastara here, a 3 matra prastara here, put 2 G's on the right side, 3 L's on the right side. Similarly, 5 matra prastara can be constructed from 3 matra prastara and 4 matra prastara. So it was this thing that Virahamka noticed. So he said the number of rows in the prastara of all those metrical forms corresponding to a given matra is the sum of the number of rows in the metrical forms corresponding to the 1 matra below and 2 matras below. So Sn is Sn minus 1 plus Sn minus 2. You can immediately recognize, given that S1 is 1, and S2 is 2, that you get the sequence of numbers 1, 1, 2, 1 plus 2, 3, 2 plus 3, 5, 3 plus 5, 8. Today we know these numbers as Fibonacci numbers, and these were originally discussed by Virahanka and later explicitly written down by Gopala. Virahanka gave the rule for all these prastaras, which you read in you. Today we know that many properties of Matra Vrittas are dependent on this Virahanka Fibonacci numbers. There is a very interesting work called Ganita Kaumudi in 14th century, which deals extensively with combinations, combinatorics. And here is a praise of this work by Donald Knuth, who says that it anticipated developments of the rest of the world by several hundred years. It's indeed true. Every result in Narayan Pandita on combinatorics has to be discovered in 17th, 18th and 19th century later mathematicians. Here is a verse of Bhaskara Srilavati and a verse of Ganita Kaumudi on combinatorics, which says that this is a very interesting branch of mathematics, which does not involve calculations using multiplications or divisions, squares or cubes as in astronomy, etc. But it is very tough, and therefore a mathematician who is conceited is bound to fall while solving such problems. Only good mathematicians can handle Anka Bhasha or combinatorics. This was indeed a glorious subject which has had a glorious history in Indian mathematics. These are some of the references for the discussion of history of combinatorics in India from Pingala to modern times. Thank you very much for your patience. I'll be happy to answer any of
Any questions? Do we have any questions? I don't think there's any question or queries. Professor N.P. Srinivas, thank you so much.
Thank you.
Thank you. आप सभी से अब हम निवेदन करते हैं कि कृपया भोजन पर पधारें और 2:15 यानी 2:15 पर हम यहाँ पर दोबारा से आएंगे. We shall resume the post lunch session at 2:15 sharp. Thank you.
And then you can leave.
The important contributions made by Indian mathematicians. An organization called Sanskrit Promotion Foundation has been dedicating itself to document some of these things which can be accessible to school children. They have come up with a text which is titled as A Primer to Bharatiya Ganitam. A Primer to Bharatiya Ganitam. So this is something which can be very easily understood by people who are in the elementary level. So class 6 plus. So this is how it has been designed. So these books are nicely written. So I have surveyed this book. So this is something which you would like to have a look at it outside. There are two versions they have brought out. One is Sanskrit version, the other is English version. So Sanskrit version, only Sanskrit lovers may go for, but at least this English version, which is a short thing, so you can please have a look at it, and there is lot of things which you have heard today, which you will find in this book, and you will be delighted to read them more thoroughly. So you are welcome to have a look at it. So that is what I was requested to announce here. You want to say something? Thank you.
एक्चुअली इस पुस्तक का प्राइस है 500 रुपया, लेकिन आज हम 10% डिस्काउंट में दे रहे हैं, तो 450 में हम दे रहे हैं। और हमारा जो वेबसाइट है learnsanskrit.online, उसमें अगर आप रजिस्ट्रेशन करेंगे तो इसके लिए जो वीडियो हमने बनाया है वो भी आप देख सकते हैं। तो इसके लिए हम वीकली क्लासेस भी चलाते हैं। अब जो क्लास चल रहा है वो अप्रैल अंत तक चलेगा, उसके बाद दूसरा चक्र जो है वो मई महीने से शुरू होगा। थैंक यू।
I am Amartya Kumar Datta from Indian Statistical Institute, Kolkata. Professionally, I am an algebraist and I'll be speaking on some landmarks in Indian algebra. In fact, just this Monday, my former student, Professor Neena Gupta, was given Ramanujan Prize. I am Amartya Kumar Datta from Indian Statistical Institute, Kolkata. Professionally, I am an algebraist and I'll be speaking on some landmarks in Indian algebra. In fact, just this Monday, my former student, Professor Neena Gupta, was given Ramanujan Prize from Italy. And I am Amartya Kumar Datta from Indian Statistical Institute, Kolkata. Professionally, I am an algebraist and I'll be speaking on some landmarks in Indian algebra. In fact, just this month,
स्थान ग्रहण करें।
ऐतिहासिक, कितना गौरवशाली
Welcome back after the lunch. This session will cover classical period, and before we invite Professor Amartya Kumar Datta, I would like to give a brief introduction of Professor Datta. आज वो हमारे साथ ऑनलाइन जुड़ रहे हैं. Mr. Amartya Kumar Datta is a professor of mathematics at the Indian Statistical Institute, Kolkata. For the past 2 decades, Professor Datta has also been regularly delivering lectures and writing articles on topics in history of science, especially on ancient Indian mathematics. Today, he will be delivering the lecture on some landmarks in Indian algebra. Over to Professor Datta.
Dr. Kumar Datta from Indian Statistical Institute, Kolkata. I am professionally I am an algebraist and from Indian Statistical Institute, Kolkata. Some landmarks in Indian algebra. Professional. Just this Monday, my former student Indian algebra. In fact, just Ramanujan Prize. This Monday, my former student Professor Neena Gupta was given Ramanujan Prize from Italy, and her work is in the interface of algebra and algebraic geometry. It was so touching that she was given the prize in honor, named after the great Indian mathematician Ramanujan, and she was getting the prize from Italy, where the subject of algebraic geometry was born. And her subject and her area involves algebra and algebraic geometry, and algebra was born in India. So I'll mention some landmarks. Before I begin, in 20th century, India
had a great algebraist, Sriram Abhyankar. And he had a mathematical poem. The first initial lines were, polynomials and power series, may they forever rule the world. So these polynomials and power series, they are very central to modern algebra, algebraic geometry, and in fact, much of mathematics. Why I am mentioning this is that what was behind this concept of polynomials, how did it come about? No, signal, it's not. So this inspiration for the algebra of polynomials, it came from decimal expansion. So decimal expansion, we tend to think of it as a part of arithmetic, but this is an algebraic concept. And in the oral form, it goes back to the Vedic Samhitas. Now, why I am saying that this is an algebraic concept? In fact, it was the inspiration behind the algebra of polynomials. In Europe, one mathematician who is associated with polynomials and power series is Isaac Newton. Now, just see what Newton has to say. Since the operation of computing, you remember decimal system was introduced in Europe just before Newton. Since the operation of computing in numbers and with variables are closely similar, I was amazed that it has occurred to no one to fit the doctrine recently established for decimal numbers. That means the decimal system and the arithmetic. By the way, the entire modern arithmetic that we do, the rules of addition, subtraction, multiplication, division, taking square root, cube root, all these things are essentially of Indian origin, and their character is algebraic. So what Newton is saying is that to fit the doctrine recently established for decimal numbers to variables, that means polynomials, especially since the way is open to most striking consequences. For since this doctrine in species has the same relationship to algebra that the doctrine in decimal numbers has to common arithmetic, the operations of addition, subtraction, multiplication, division, and root extraction may be easily learned from the latter. So Newton in 17th century makes a very clear acknowledgement that the polynomial arithmetic can be straight away taken from the arithmetic with the decimal system. And therefore it is no wonder that 1000 years before Newton, Brahmagupta had defined the algebra of polynomials, which we will see. And in the later lectures, we will also see the power series expansions in the work of Madhavacharya in 14th century. Now, I had shown the picture of Professor Abhyankar. Abhyankar, in an autobiographical article on his work, just see how he poetically puts the thing that about his, those days they had to journey by ship in the early 50s. My journey from India to the United States, he had done his graduate studies in Harvard University. Parallel the march of algebraic discoveries from India through Arabia to Europe in ancient times. So his ship went from Bombay to Arabia to Europe, and in fact first to Italy and then to US. So embarking from the Bombay Pier, my boat took the same path by which algebra had traveled from India to Europe via Arabia, where it acquired its current name. Now, so when we say that algebra was born in India, we have to be clear about what aspect of algebra we are talking about. So I make three distinctions. One is proto-algebra, which is very ancient. So by proto-algebra, I mean that algebra not in the form in which we are normally associate with it, the algebra that is introduced in school. So, but it is algebraic in substance, though not in external form. So let us call that proto-algebra. And then we have the classical algebra, the algebra that we see in school. And then there is abstract algebra, which is done at a level much beyond the usual school algebra. And we see, so this I'm calling it proto-modern abstract algebra in ancient Indian mathematics. So here, abstract algebra, the language, the external form is not there, but the essence is there, the substance is there. So we will see these three parts. So proto-algebra, as I already indicated, that there's the algebraic ideas in the decimal system and arithmetic algorithms, which are really ancient, which go back to the Vedic time, may not be the written notation, but at least in the oral form. The other is the Sulva Sutras, in which there have been talks earlier. So there, in the geometric constructions, you see geometric expressions of algebraic formulae like the ones which are displayed on screen. And the point is that at that time, probably algebra in the symbolic form, in the high school form, was not there. But that is the greatness of the Sulva savants, or those of the Vedic era, those Vedic savants who had invented these constructions, that they had invented mathematics, algebraic in spirit and substance, much before the genesis of formal algebra. So that doesn't make them lesser, that makes them even greater as algebraists, that even without the facilities of formal algebra, they had conceived of algebraic results in geometric form. So to give a quick example, that the construction, draw square n times the square of a square of side A, which essentially means that you have to construct root NA. So the Sulva construction is that you draw a triangle whose base is n minus 1 times A. So bisect it, and then you take your compass and draw n plus 1 times A by 2. And complete the isosceles triangle in which each of these sides is n plus 1 A by 2. And then they say that this is the required side. So what they're using here is n plus 1 A by 2 whole square minus n minus 1 A by 2 whole square is NA whole square, NA square. So, in fact, this diagram is a geometric representation of the algebra formula. So, this is sometimes called geometric algebra. Let me skip the next one. So, now we come to algebra in the form that we know it. So, what is called classical algebra, or what Professor Abhyankar would call high school algebra. So, Brahmagupta in early 7th century had laid a firm foundation for algebra in the form that we know it in chapter 18 of his treatise magnum opus Brahmashputa Siddhanta. And Fields medalist David Mumford, in a personal communication, had told me that it seems clear to me, had written to me, it seems clear to me that Brahmagupta is the key person in the creation of algebra as we know it. Now we'll just expound on Professor Mumford's statement. So the use of, let us see that what is our definition of algebra right now. So we are moving away from the Sulva geometric algebra. So use of symbols, letters of the alphabet to denote unknowns, and equations are the foundations of the science of algebra. So this is a definition which Datta and Singh has given in their preface to History of Mathematics. And as you know, that use of symbols and equations were great steps for rapid progress of mathematics. Now let us look at it one by one. So the foundations of algebra, one is the symbols for unknowns. Brahmagupta, in the text which I mentioned, prescribes use of varna. He used the word varna, and varna has both the meanings, letters of alphabet as well as colors, as symbols for different unknowns. This is the first time there are symbols for different unknowns. And this commentator illustrates, so there was, for the first variable, there was an ancient term, yavat tavat. So what they do is, they take the first letter, ya, yavat tavat, so take the first letter, ya. And after that, introduce colors. So for instance, kalaka, take the first letter, ka. So ka denotes one of the variables. Similarly, nilaka, so ni. So like that, the list goes on, and I'm just giving you your X, Y, Z. So ya is the Indian symbol for X, and ka for Y, and ni for Z. I'll add one more thing for the foundations of algebra, the use of zero and negatives. And in Felix Klein, the great geometer, he had in his book on mathematics education emphasized that how extraordinarily difficult it is that when in principle, when negative numbers are introduced, here for the first time we meet the transition from concrete to formal mathematics, and it needs a high order of ability in abstraction. Now, again in Brahmagupta, we find an elaborate exposition of the algebra of positive numbers, negative numbers, and zero. That is, so first of all, zero, there is this zero as a place marker, that is much more ancient. But zero as integer in algebra, this is unique contribution from India, and this is something we see for the first time in Brahmagupta. Zero as an integer on par with positive and negative numbers. And it is defined as a minus a, zero. So that clarity was a profound step. And all the rules of operations with numbers, positive numbers, negative numbers, and zero, treating all on the same footing is given. There are whole lot of rules. I'm just giving samples, like minus into plus is minus, minus into minus is plus, a into zero is zero for every number a, and so on. So here you see the dormant modern abstract algebraist in Brahmagupta, that in retrospect, he had conceptualized integers as a ring with zero as the additive identity. That is what his work amounts to saying. He didn't, of course, use the word ring. Then there is this, apart from symbols, the foundation of algebra involves formation of equations. So already in Bakshali manuscript, which many historians of mathematics date to 300 AD, around 300 AD, but some have a different point of view, some say 7th century. Let's not get into that debate. There are examples of equations there. But what we definitely know is Brahmagupta in text is 628. There he teaches about formation of equations, which is illustrated by his commentator with an example. Now, 10x minus 8 equal to x square plus 1. How Indians would represent it, how Brahmagupta would represent it is, so Ya is a symbol for x and Va is square, Vargas. So this is, Ya Va is x square, Ya is x, and this is the constant coefficient. So you write this 10x minus 8, so the coefficient of x square is 0, coefficient of x is 10, and the coefficient of the constant, it is 8. The dot above represents the symbol for minus. So 8 dot means minus 8. Now instead of equality, left hand side equal to right hand side. So what they do is that there is no symbol for equality. So they, they write one below the other. So x square plus 1 is written here. So x square 1, x coefficient is 0 and 1 is here. And you will see, now you may feel uncomfortable. No, this is not what we were taught. But this is actually quite convenient for your operation, that this left hand side and right hand side. So when you kind of clear, try to do clearance, there is a bit of a mental work needed. And here, this tabular arrangement of the equation makes it much more convenient actually. So similarly, 197 minus 1644y minus z equal to 6302. So you have this Ya is x, Ka is y, and Ni is z, and this is constant. So 197, 164 with a dot for then 1 with a dot. And similarly, the right hand side, this 6302, everything is 0 and there is 6302. So this is how equations are represented. Then next is the preparation of equations. Now, so I think there is some LaTeX problem has occurred, so that has disappeared, doesn't matter. So the equations are processed in the same way that we do now. Then equations are classified. So the point I'm trying to say is that what that classification is not important, but they have a name for equations, Samikarana, and they classify like equation in one variable, quadratic equation, equation in several unknowns. So there are various terms for that. Now, just as Brahmagupta defined, that is, gave the ring structure of integers, he actually also gave the ring structure of polynomials. He, in retrospect, Brahmagupta defined the structure of the polynomial ring in several variables. He teaches how to add, subtract, and multiply polynomials in several variables. So, like add, so he says add and subtract squares, add and subtract cubes, fourth powers, etc. of the same variable. So, like 5x squared plus 6x squared would be 11x squared, 2y cubed plus 7y cubed will 9 cube. But others you leave it as it is, like 5x squared plus 2x cubed, just leave it as it is, or 5x squared plus 7y squared, leave it as it is. Then the product of two unknowns is a square, product of three is a cube, etc., etc. Product of five things is fifth power. And product of different unknowns is a separate term called bhavitaka, like xy. And then operations are done on them as before. So the summary is that he is teaching the algebra of polynomials. So all this is in 628. Then quadratic equations. So that, of course, Aryabhata already had given the formula for the that is that minus b plus minus root over b square minus 4c, but not in the form which we have seen. Their a, b, c are quantities in specific situations, like problems on arithmetic progression or problems of interest. He doesn't give it abstractly, and Brahmagupta gives the formula abstractly. That means for arbitrary ABC. And he uses the term madhyaharana, elimination of the middle. Sridharacharya describes a method of completing the square, which is of course implicit in Brahmagupta. He doesn't elaborate, but it's implicit. And Bhaskaracharya, but Sridhar's text is lost, but Bhaskaracharya quotes the Sridharacharya method. And this is a profound idea with far-reaching significance. In fact, Professor Abhyankar talks about this resolution of singularities. The basic thing is this completing something, analogous to the completing the square. And the other point to note is that thanks to the use of negative numbers, Indians gave a unified treatment that we see now. For a long time in Europe, three different cases were studied separately. Like, these equations were treated separate. This ABC were all supposed to be positive. In India, you have uniform treatment. Then there is the solution of quadratic equations, simultaneous quadratic equations with applications in astronomy. Then Gaussian method of elimination for solving linear equations in several unknowns. Integers, now this is very hard problem, finding integer solutions of equations. This is rarely taught in high school, even now. And these things were done by Aryabhata, that he had solved linear equations. That means found integer solutions of equations with integer coefficients, and equivalently solve the problem of simultaneous remainders, which now goes by the Chinese remainder theorem, but it is there in Aryabhata in 499. And all this work was initiated in Europe in early 17th century. This is incidentally a fundamental step in cryptography, and Indians had applied it very effectively in astronomy. Then there is the great work by Indians on the solution of equations of the form nx squared plus 1 equal to y squared, where n is a fixed integer. This was initiated by Brahmagupta, completed by Jayadev, and in Europe it was initiated 1000 years after Brahmagupta by Fermat. Now, the other thing to be noted is that in Brahmagupta, we see the recognition of algebra as a distinct discipline, because sometimes we will see that people talk about, Aryabhata doing algebra, then why Brahmagupta is thought of as the creator. Because there is there is a clear recognition of the subject as a distinct discipline. There are individual algebraic results before Brahmagupta. So for the first time, there is a separate section on algebra. And at the beginning, algebra is presented as a distinct and powerful branch of mathematics. Its core topics are listed at the beginning, that what constitutes algebra: symbols, operations with zero, negative and positives, equations. All these things are enunciated. I am not giving the full list. And he emphasizes the indispensability and power of the subject algebra. No, it's not just mathematics, focusing on algebra. And at the end of the chapter, he highlights 3 features of algebraic research. Of course, in the language of the era, gives an incentive for the delight and glory of algebra. So this intrinsic emphasizes intrinsic mathematical importance, the internal compulsion for the research. The way Ramanujan, for example, conducted his research out of the realization of the mathematical importance, and then generation of new research and also applications. All these things are emphasized at the end of the chapter. Thus, in school, we see various series, AP, GP, all these things are there. I mean, this is even before Brahmagupta, but not in the form of symbols in terms of words. AP series, sum of squares, sum of cubes, GP, even infinite GP in Nilkantha. Then you see roots of binomial sorts are given. There's been already lectures on combinatorics in India, and so I'm not emphasizing, but there are many results, like number of permutations of n things, of which n1 of one type, n2 of another type, etc. Harder problems are also described. Bhaskaracharya takes a bold step of introducing infinity in mathematics and defining rules of interactions with usual numbers. Infinity plus x is infinity and infinity minus x is infinity. The idea of... Now we come to the climax, the proto-modern abstract algebra, what we call. Brahmagupta not only laid the foundation for classical algebra, he introduced principle of composition, which is the essence of modern abstract algebra. So composition means combination of 2 mathematical objects of a certain type to produce a third object of the same type, like composition of 2 solutions of a given equation to produce a third solution of the same equation. So let me tell what Brahmagupta's composition law is. The context is solution of the equation nx square plus 1 equal to y square, which, as I told you, that would be taken up by Fermat 1000 years after Brahmagupta. Now, the point is that he looks at the more general equation, nx square plus z equal to y square, and observes that if x1, y1, z1 and x2, y2, z2 are solutions of this equation, then so is the cross product x1, y2 plus x2, y1, nx1, x2 plus y1, y2 and z1, z2. In other words, he is constructing a binary operation, and this had a name in ancient India called bhavna. Bhavna is the Indian term for composition in Indian mathematics. x1, y1, z1 composed x2, y2, z2 is x1, y2 plus x2, y1, nx1, x2 plus y1, y2, z1, z2. And this sophisticated idea of constructing suitable composition laws on abstractly defined unknown elements is a central theme in modern mathematics research, mind you, not studies, research. Now, the enormity of this innovation, think of it this way. Look at the various steps of algebra. The classical algebra is something which is done in HS, higher secondary, that formation and solution of polynomial equations using symbols for unknown. Modern algebra, so this classical algebra had simplified mathematics, and modern algebra gives you conceptual insights. There are 3 layers as the students progress. In BSc Maths, they study abstract structures like groups, rings. In MSc, they learn how to associate abstract structures to mathematical objects, like to a polynomial, with a polynomial, associate a group. And then as they go even further, and that only a few people go, I mean those who are into algebra or number theory, they learn to construct binary composition on important set. For example, constructing an addition law on points of an elliptic curve. Brahmagupta had created number one, which we had seen. Now he bypasses this and soars to the top layer of modern algebra, that constructing binary composition. And his composition law Bhavna is a principle pervading entire modern algebra and number theory. Now I had one example to illustrate his composition law, but I suspect that I may be running out of time. So let me skip the example. You can see it in my articles. So just to give you a feeling that where Brahmagupta's law lives. There is a book, research monograph of 1990. There is a cover page. Look at its table of contents. The chapter 5 is titled Also Sprak Brahmagupta. That means Thus Spake Brahmagupta. So that is page 54. You have seen this. Page 54. What is in page 54? This is a chapter title, Also Sprak Brahmagupta. And then the Brahmagupta's Sanskrit verses which give his composition law, that is quoted here. Because the foundation of this chapter 5 is Lemma 5.1. And the next result, 5.2, was discovered in 1965, as late as 1965. So you see where Brahmagupta lives. So just one more slide on the inspiring legacy of Brahmagupta's Bhavna. When Manjul Bhargav, our keynote speaker, received the Cole Prize, he acknowledged the ideas in his work. So he acknowledged that in his work, he has taken ideas which go back to, this is his list, Brahmagupta, Gauss, Dirichlet, Eisenstein, Dedekind, and later mathematicians. Don't you see Brahmagupta is an odd man out here? All other mathematicians are from 19th century and Brahmagupta is tagged there. So this is where his work lives. And in a talk on Ramanujan on National Mathematical Day in 2020, he had made a remark that what Brahmagupta did around 600 just blows your mind. Indeed, there's a mathematics magazine for students, which is titled as Bhavna. It started in January 2017. You know, Manjul got Fields Medal in 2014. So this was, on the one hand, a tribute to the profound work of Brahmagupta. One thing I missed, that Brahmagupta's rule can be stated as an identity, and Euler had rediscovered it and he called it a theorem of capital importance and a most elegant theorem. And as you can see that this is a very important identity in subsequent algebra and number theory. It is crucial ingredient in one of the theorems of Legendre. Now this was generalized by Gauss, and he gave a composition of binary quadratic forms, which is regarded as one of Gauss's deepest discoveries. And Manjul Bhargav became famous 200 years after Gauss. He gave higher composition laws, simplifying and generalizing Gauss's theory, and that made him, that has made him a legend. Now, what I was saying is that so this Bhavna, this Brahmagupta's composition laws, Bhavna, the concept, it connects one of the most glorious achievements of Indian mathematics of far off times with one of the most celebrated achievements of a mathematician of Indian origin in contemporary mathematics. And we hope that this Bhavna may it inspire more and more profound. Bhavna also means thoughts. May it inspire more and more profound bhavna in the
Any questions? Thank you so much, Professor Datta. Thank you so much. हमारे अगले स्पीकर हैं Clemency Jane Montel. Clemency Jane Montel holds Doctor of Philosophy in the History of Mathematics, Brown University. She has worked as Vice President of the International Commission for the History of Ancient and Medieval Astronomy and has played key roles in core organizing committees for over a dozen conferences and symposiums. Today, she will be talking about Jyotpatti, trigonometry in India. Welcome, Clemency Jane Montel. Clemency Jane Montel. Clemency Jane Montel.
Thank you very much for that kind invitation. Let me just share my screen. Oops. Okay, can everybody see that? So I'm going to talk about trigonometry in India from Aryabhatta to Bhaskara. Indeed, in 1150, at the age of 36, a mathematical scholar who's arguably one of India's most illustrious scientists wrote the Siddhanta Shiromani. This astronomical treatise, otherwise known as the Crest of Siddhantas, was written with close to 1,000 verses long, covers topics in astronomy, from calendrics to eclipses, from planetary perturbations to star conjunctions. And in it, Bhaskara introduced very many ingenious and incredible technical results, some of which weren't formalized many centuries later with the development of calculus. In fact, the Siddhanta Shiromani is often, and the four texts that go with it, is often dubbed a universal canon of the mathematical sciences in India. These four texts contain a work on algebra and on arithmetic. That is the well-known Lilavati, which still delights skilled children today, a Karana, known as the Karana Kutuhala, and the aforementioned Siddhanta Shiromani. Now, Bhaskara knew at the heart of astronomy was a technique which was prevalent today in mathematics called trigonometry. And what he did is that he pulled out trigonometry, otherwise had been inserted deep in the heart of astronomical chapters. He pulled it out into his own chapter and called it Jyotpatti, a Sanskrit compound with Jya, meaning a sign, and Utpatti, meaning generation. And with that, he had his own chapter and a very interesting mathematical exploration of these signs. Now, of course, Bhaskara was not shy about the importance and the prevalence of trigonometry in astronomy. And one of the opening verses in his treatment of trigonometry in the Siddhanta Shiromani is a verse which goes as follows. And of course, as many of you know, Bhaskara is known not only for his supreme technical acumen, but also his brilliance as a poet. So the verse about trigonometry and its prevalence in astronomy goes like this. Pato yata tantubir udpatiryak Rupari nibado tratataiva golaha. Do koti jiva bir amum pravuktum jotpatti meva pratamam pravakshe. So in this is this beautiful Sanskrit verse that reads as follows. Just as fabric, or pata, is made of the warp and weft of threads, so too is the study of spherics, and for this he uses the word gola here, is crisscrossed with sines and cosines. Therefore, he says, I will firstly narrate the Jyotpatti, or generation of signs, to elaborate on this. So this beautiful verse, including this metaphor, I think can be understood in two different ways. And the first way we can understand it, of course, is, as many of you know, of course, Indian fabric is synonymous with one of the very amazing industries on the subcontinent. Warp and weft of threads, of course, are these crisscrosses here that we see in this diagram. And of course, the idea of them being absolutely essential to be woven together in this particular way, to be absolutely prevalent and all over the fabric that we see. And indeed, if we look at astronomy, and not to dwell too much on the technical details, we do see here, just like the warp and weft and threads are prevalent throughout fabric, so too sines and cosines are everywhere in astronomy. So for instance, geometrical models which involve spheres and great circles, and of course their stereographic projections of circles and arcs and straight lines and their perpendiculars, were used to model everything in the heavens to be able to make accurate predictions about celestial phenomena. So no less than ascensional differences, which have a fairly complex makeup and spherical trigonometry. Indeed, you can see embedded in some of the key results that we're looking to compute in astronomy, such as ascensional differences, to tell the arc of the ecliptic or the apparent path of the sun, or the zodiacal circle that's rising above the horizon, or the ascendant, the lagna, is embedded in computing this is a woven conglomeration of sines and cosines. Indeed, in this sort of fairly simplified model of planetary longitudes, the epicyclic corrections that we see, these orbital corrections to correct the mean position to the true, which is based on the distance of the mean planet from the so-called apogee, indeed is based on the relationship between two sines. And indeed, another example is, of course, when we're timekeeping, we're trying to figure out the zenith distance of the sun and the shadow, when we're telling the time and figuring out where noon is. Of course, even more, you can see the prevalence of sines and cosines through here. So this is indeed what Bhaskara's beautiful metaphor about the warp and the weft was relaying to. But even more than that, of course, the warp and the weft derive their strength from their perpendicular nature. And so too, I think Bhaskara was hinting at the sine and the cosine that we see when we look at the more geometrical imagination or rendering of the sorts of things we are trying to model in astronomy, such as the basic problem in trigonometry, which is for a given angle, or as our Indian predecessors would say, for a given arc, what is the straight line segment that's associated with that arc? And in fact, by the early first millennium, Indian trigonometry had evolved quite significantly from Hellenistic origins, from chords to half chords. And the reason that this was so important is given, I think, in a beautiful verse by Nityananda, much, much later, of course, to say, why did the Indian scholars discover or see the efficiency and the beauty of this half chord over the chord? Nityananda says in this half verse, this is because in astronomical models, the position of the planet lying at the tip of the half chord, situated perpendicular to the central line intersecting the chord, is computed using this measure. So in astronomy, when you're looking for elevations and things, this half chord was of the greatest importance and much more useful in many ways than the full chord, particularly because it had at its essence right-angled triangles, which even further made computation of it much easier. So you can see here the warp, the weft analysis, we have the R sign, which corresponds to half the chord of double the arc, some like to say in modern terms, and the perpendicular amount cosine of the arc, so the warp and the weft, and this is clearly what Bhaskara had in mind with his beautiful analogy. Now, so much for the warp and the weft, but for very early thinkers, they had to develop technical terminology for these line segments and these arcs. And when astronomers looked carefully at diagrams such as the one I have here, they saw something that reminded them very strongly, it seems, of a bow and an arrow. And if you look at that quite carefully, you'll be able to see it too. Indeed, here we might imagine that this arc all the way along here, BDC, is equal to the bow. And then we see associated with it is the bowstring here. So the bow is called chapa in Sanskrit, And the bowstring, or jar, a word in Sanskrit, is the chord here, or half, and jarda, the compound with ada meaning half, is half the bowstring or the sign. And so words like this seemingly came from this very visual analogy of these mathematical principles. The last one I'll just point your attention to is the shudder, the arrow, which is this small arc in here, ED, which is known as the versed sign, perhaps a more archaic trigonometric element, but one which was incredibly foundational to Indian trigonometry. You might like to think of it as the radius of the circle minus the cosine here, which is AE, the versed sign. With this bowstring, we actually get a beautiful etymological journey right from the Sanskrit word to the modern term that we have today in surprising and quite interesting ways. So if you take the Sanskrit jar, which means bowstring, or a synonym of it in Sanskrit, jiva, which was often used, Arabic scholars transliterated this Sanskrit word. The V becomes B, as often happens from Indo-European languages to Semitic language, and they transliterated, so letter for letter, transliterated the word to get the Arabic al-jaib, so which already had a meaning. In Arabic, it means a bay or a pocket, sort of a geographical feature, or a fold or a cavity. Interestingly enough, when Latin scholars came along to look at these Arabic texts and discover this terminology that Arab scholars had used for it, they said, we're going to translate this term, and the Latin word for bay or pocket or cavity is literally sinus, just like the cavity in your nose, and they used the word sinus, from whence we get our term sign today. And so from this long etymological journey, we can in fact trace the word sign right back to the original Sanskrit word. So with this in mind, clearly astronomers needed efficient and accurate means to compute trigonometry, and the mathematicians got to work by providing half chords and other line segments that they could use geometrical identities of polygons inscribed in circles to be able to find out these half chords or these line segments. From these, they constructed tables of signs in circles that they gave various values of radius. So unlike our modern sign, which is essentially on a unity radius, they computed their signs for various values of r, which is why we always call it, particularly in the Indian context, r sign. So it's a scaled form of the modern sign function. And not only that, but to find values of sign that had not been tabulated, various interpolation schemes were put into use. Some were linear, just a standard way we use today, but some scholars came up with very ingenious techniques to determine non-tabulated values, and we'll look at these. So these sort of desiderata led to many brilliant discoveries and results from the middle of the first millennium and well into the second, and we'll just delve into some of those right now. So perhaps the first sign table that we get appears in Viramahira's Panchasiddhantika in the beginning of the 6th century. And Viramahira sets out some basic geometrical relations of basic polygons inscribed in a sphere to determine key sign values. And in fact, you don't need very much to be able to build yourself a sign table. So for instance, in order to determine the sign of 30 degrees, he inscribes a hexagon and in a circle. We all know that, of course, the lovely property of hexagons inscribed in a circle is that the radius, of course, is equal to the length of the sides. So in fact, the half chord of a 30-degree arc is just equal to the radius over 2. Likewise, for the R sign of 45 degrees, using similar reasoning, we can actually determine, of course, this side of the triangle here for a 45-degree arc along here will be just using the Pythagorean theorem, will be equivalent to the radius divided by the square root of 2. And likewise, you can find the R sign of 60 degrees, and of course the R sign of 90, or a quadrant, is just equal to nothing but the radius itself. So with those few relations and one more key relation, and using his radius R equals 120, he produces the sign table for the first quadrant with 24 sign values. And the extra special identity that he needs, of course, is the so-called half-angle formula, which he articulates beautifully in verse. And so that means that what he can do is start with something he knows, such as the sine of 30 degrees, and find the sine of 15 degrees, and then in turn the sine of 7.5 degrees, and then in turn half of that, the sine of 3 3/4 degrees. And likewise from the sine of 45 degrees, which he found, he can use the half-angle formula to find all the others, thus producing a sine table with 24 values, with a maximum value here of 120, in other words, the radius. What's really beautiful about this is not only does he tell us a little bit about the geometry of how to construct the sine table, but he presents the sine table in versified form. And he uses a very interesting technique known as Bhuta Sankhya, or the word numeral, object numeral system of numeration, where everyday objects or objects that have significance, which have a number behind them, are used to, for that number itself to make it more memorable. And so we see here, we'll just pick out a few. I won't spend time reading the verse, but we've got here, we've got the signs, so the jars, we've got swara, titis. So he's just going through here the first significant figure here, 7, 15, and there are 15 titis, and then we've got Vimshati, Sahita plus Guna, so that's 23, plus Shiva, so that gives us 11 or 31, and then Triti, which gives us our 38 here, and so forth and so on. So it's beautifully encoded in verse, so it's memorable, and the astronomer can have in their mind at all times a sine table on handy for when they're needing to use it within astronomy. Aryabhata, at about the same time, comes up with a similar looking table, but with some different techniques and some different numerical values for it. Aryabhata, in fact, gives a sine table with 24 values as well for arc multiples of 3 degrees, 3 3/4 degrees. But his tabulated values are in fact sine differences. And there's various theories on why this might be the case. But of course, as you can see, the sine differences decrease in value, and therefore there are less digits to have to encode in verse, which might explain one reason as to why he encoded these sine differences. However, as well as having the geometric approach to establishing these sine values, or these sines different values, Aryabhata, again in a verse, provides an ingenious recursive algorithm to produce successive sine differences, which is incredibly, and it doesn't actually tell the reader or exactly how he discovered it, but there have been some very convincing hypotheses on exactly the relationship between this. So essentially what the problem boils down to, of course, is finding these half chords here. So you imagine you've got arc P0, P1, P0, P2, and we've got 24 of those arcs, and their corresponding half chords here, P1, N1, P2, N2, P3, all the way up to P24 and 0 here. So it's finding these lists here, all these differences between the two, which is of course what Aryabhata has tabulated. And essentially the recursive algorithm produces the very next difference from the previous difference and the ratio of the corresponding sine value over the very first sine. And this has often been called a discrete form of the harmonic equation. So it's actually, there's some fairly sophisticated mathematics that underpins this particular relationship. So it's a different way of producing a sine table via its sine differences via a recursive relationship. Interestingly enough, just like Varamahira had, Aryabhata encodes his numerical values in a very interesting, unusual system of numeration, which is based on assigning various Sanskrit letters to numbers. And if you give this, I've given this, try and give this to any learned Sanskrit pundit to read, and it won't be long before they trip over, because these really words, mucky, bucky, pucky, ducky, etc., lucky, are really quite a mouthful to say, and don't make any sense at all, and are even quite dissonant when you listen to them. So I'm not sure how memorable this verse would have been, but of course it's become memorable, so famous, because of its distinctiveness. And so here it is, it's just an entire verse which is basically encoded numerals, which give you at the end kalad dajar, the signed differences in minutes of arc, and there they are there, 225, 224, etc., and so forth and so on. Nobody picked up on Aryabhata's system of numeration. I think perhaps there's a reason for that. Brahmagupta, as we've heard of lots of today, wrote, of course, a big work, the Brahmasputa Siddhanta, but he also wrote a Karana text, which is a much smaller, abbreviated, sort of a handy, ready reckoner type work, which produces algorithms which are approximations or usually very ingenious with some very clever mathematics behind them to simplify procedures for the astronomer. His sign table in this Karana text, the Kanda Kardika, is very abbreviated. It reads Trim Shat Sanavara Sendu Jinatiti Vishaya. So that's the sign table in just a handful of syllables. We'll have a look exactly what that means in a minute. But as you can see, it only has 6 values. So Trim Shat is the Sanskrit for 30, Sanava of +9. So we get our first sign difference, 39, by 6. So that is our rasa. And by 1, Indu, the moon, gives us our 31. And then we've got Jinna, or saints, Titi, that we saw before, 15, and 5, Vishaya. So again, this Bhuta Sankhya system or word numeral system. And as you see, Brahmagupta 2 is giving you these sign differences rather than the signs themselves. And again, a reason might be sign differences, of course, are very useful immediately for interpolation purposes, but indeed the digits, of course, are getting smaller. So there's actually less to encode, which is even more memorable. So Trimshat Sanavara Sendu Jinatiti Vishaya is the sign table. But when you're balancing this brevity of what you have to memorize, you're sacrificing in precision. So, so what you need is some fairly suitable interpolation algorithm to find non-tabulated sign values. Another note there, just like we've seen, the radius is also small. The idea being in a Karana text, smaller numbers are easy to compute. So Brahmagupta's is a very interesting 150 there for the quadrant. Now, so Brahmagupta doesn't disappoint. He gives us, in fact, 2 interpolation algorithms. One is a linear approach, which is just, straightforward first order interpolation, which you're all familiar with. And it basically says he presents this in the second part of this verse after the Trimshat Sanavara Sendu. So he tells you to take the sum of the previous verse differences with the proportional part of the current difference. So it's just linear interpolation. So for instance, if you were to take the sine of 24 degrees, which of course is, somewhere in here, you just take the first sign difference and the proportional part of the second, which is 36, to get 60.6. But Brahmagupta doesn't stop there and in fact gives us a higher order approach. It's a little more complicated and it takes an entire verse in Aryamita to be able to express it. I won't read it here, but you can just see sort of the detail behind it. Interestingly enough, if we use modern symbolic notation to be able to get put down in symbolic form the formula that Brahmagupta presents in his verse, we in fact here see it's a second order interpolation formula, which is essentially equivalent to the much later Stirling's finite difference formula, which is well known as a modern interpolation technique. So just for interest, if you take the same problem, sine of 24 degrees, you'll get the sine of the sum differences again, and this other bit here, which is indeed gives us a value which is much closer to the actual value of the sine of 24 degrees. So an ingenious formula that's come out from trying to determine non-tabulated signs, which are tabulated for relatively large arc lengths, such that joining them up with straight lines, of course, is okay, but less good than a second order approach. The idea of approximating sign was put forth too, or furthered by Bhaskara I in his Mahabhaskariya, which was written in about the beginning of the 7th century, the great work of Bhaskara. Now, Bhaskara gave this famous rational approximation to the sign. In fact, it's not just a quadratic approximation, it's in fact a ratio of 2 quadratic functions. And many subsequent astronomers actually used this and embedded it within their formulas that involved sines and cosines to avoid having to use directly these sign tables altogether. It's a very clever way of giving very precise results. How exactly he found it, again, there have been some wonderful reconstructions by modern scholarship, many of which are very convincing. But if we just, compare Bhaskara 1's rational approximation to the sign as follows with the modern sign function in red here, you'll see it's stunningly accurate for values of sign. And in fact, even if you blew up this and looked closely, you'll find it's only out by a very, very small amount. So a really stunning result by aspirations to, I think, looking at computing these sign values when tabulating sign values were becoming more cumbersome to remember. So in that context, we see Bhaskara's Jot Party at the beginning of the second millennium. And what's interesting about Bhaskara 2, as I insinuated at the start, is that trigonometry before Bhaskara was always embedded within astronomical content, usually in chapter 2 when we were looking at planetary corrections, orbital corrections to find true longitudes and velocities of the planet. Bhaskara, realizing the potential and mathematical interest in its own sake, pulls out the work on trigonometry and gives its own chapter, calling it Jot Party. It's the first real distinctive treatment that we see of trigonometry as a mathematical subject in its own right. And what he does is gives a range of formulae, some of which are equivalent for determining a whole group of sign values, not just the traditional 24. So very quickly, and Bhaskara is very proud of his achievement, saying, I declare by means of arithmetic these fully accurate signs, using this lovely Sanskrit term, which doesn't get used very often, parisputani here. So in addition, so what's his claim for these fully accurate signs? So in addition to the traditional relations for signs, and that half-angle formula, Bhaskara is the first one to give a exact formula for the sign of 18 and 36. And when he combines this with really what is his pièce de résistance in his work, the sum and difference formula, which is the first time we see it in India here, you can actually produce a sign table with 30 values. And just very quickly, from sign of 30, you can find the sign of 15 by using this half-angle formula, and then take the difference with the sign of 18 to find the sign of 3 degrees, and you can just elaborate from there to get a sign table of 30 values. But Bhaskara doesn't finish there. In fact, using this sum and difference formula we see on the bottom, he actually gives a range of further elaborations, which indeed he is incredibly proud about too. These are all variations on a theme, if you like, from the sign of sums and difference formulas. Some, of course, as he tells us, actually are very, very interesting approximations and avoid having to use square roots, which many practitioners at the time said are cumbersome to compute and can be inaccurate. So essentially, we can see Bhaskara's interest in trigonometry is not just providing astronomers with a sign table from which they can compute their algorithms, but actually exploring the very relations and fundamental principles and connections in trigonometry itself with some of these rules here in beautiful ways. So Bhaskara really set the scene in the beginning of the second millennium for trigonometry to be continued to be developed in interest with extensive numerical tables that we see in later authors. The Kerala school developments with Madhava in the 14th century, who develops infinite series for trigonometric quantities, interesting approaches to the sign of 1 degree that scholars were experimenting with, and more ingenious rules and relations for spherical trigonometry to ever be able to capture astronomical phenomenon. So there we have it, trigonometry in India. It's beautiful development, full of ingenious rules and techniques. Thank you very much.
Two, three questions. We have 2-3 questions, Doctor.
Yes.
These are the live questions. Yeah.
Will you ask the questions? Are they in the chat?
Yeah. Just a sec.
I have one quick question. if you were to compare the values that are given by Aryabhata with those that have been presented by Ptolemy, so how far are they accurate? Will you be able to highlight something on that?
Yes, so I haven't looked at that. Can we just turn the other thing off? Otherwise, I hear myself echoing. Ptolemy had some interesting approximations that he made. Particularly, he was dealing with a chord table for one, and he had an approximation where he essentially squeezed the chord of 1 degree or half a degree between two values. It's quite close to Bhaskara's approximation sine of 60 parts as well, but I haven't looked at the direct comparison between Ptolemy's chord table and its accuracy with Aryabhata's, but it would be a very interesting project. Of course, many of the values are found using geometry, so they're analytically exact.
Thank you, Dr. Clemency Jane Monroe. Thank you so much.
Can I make a remark?
Oh, yeah, Professor Ramesh Sriram to say something.
It's good that it's a good lecture by Clemency ji. She was commenting about the second order interpolation formula of Brahmagupta, and it appears in Siddhanta Shiromani also, Grahaganita, not Jyotpati. It comes in Grahaganita Bhaskara. And what is interesting is he gives a nice derivation of that, explanation of that, using what is known as law of proportionality. You may not completely agree with it. I mean, there may be some loose ends, but it is very interesting in a way of getting the second order interpolation formula, essentially a second order Taylor series. Yeah. Thank you.
Thank you very much for this excellent point, Professor Sriram. Indeed, when I opened with the Siddhanta Shiromani, I wanted to make note of the fact that it's such an incredibly dense and complicated and brilliant work that only some of the best minds in India are working on it, and that would be you and your group. So we're really looking forward to hearing further about it. Yeah, as many have commented, a lot of the derivations or clues as to how these brilliant results were actually discovered are often not explained by the original authors themselves. Sometimes we find it in commentaries, and indeed in Bhaskara himself writing his Vatsana Bhashya, he writes a commentary on his own work, so we get glimpses in ways as what you said absolutely give us a clue into the way in which this rule was actually derived and understood. So thank you very much.
Thank you. Our next speaker is Professor Avinash Sathai. He is working in algebra and algebraic geometry. He also has worked in Sanskrit in fields of philosophy, history of Indian mathematics, and Indology. He will be talking about indeterminate equations in Indian algebra.
I'm talking about linear and quadratic equations over integers in Indian algebra. I am Avinash Sathai, Emeritus Professor of Mathematics at University of Kentucky, and today is February 25th, 2022. It is well established that the invention of the decimal number system was made in India, and later it was adopted by Arab scholars and eventually adopted by Western mathematicians. I, however, note that in Indian mathematics, the integers are indeed displayed in the decimal system, but fractions are often displayed as ratios of integers, such that the denominators are suitably chosen integers which are kept as small as possible. This is in contrast with the usual idea of using powers of 10 as the denominator. This practice helps in keeping the calculation simpler and more accurate, and we don't have to fight with the numerical errors in computations with the usual decimal system. As a consequence, Indian mathematics is often based on number theory rather than the usual calculation of real numbers. We discussed two famous theorems in Indian mathematics to illustrate this. And whoops, okay. Sorry, this is the bottom of the screen goes out for me. Shall I stop and do it again? I mean, go to the next page. Let us start with this page now. The first part of the two theorems that I am talking about is called Kuttaka. We discuss the solution of an equation of the form ax minus by equal to c, where a, b, c are integers, and we seek possible integer values of x comma y. We also want to determine all possible such solutions, even though the solution set is infinite. The first manuscript describing the solution technique appears in the famous work Aryabhatiya of Aryabhata in 499 CE. Thereafter, it is a standard feature of almost all algebra books in ancient Indian mathematics. Indeed, Brahmagupta in his major work Brahmasputa Siddhanta in 7th century praises the topic in these words: Prayena yatah prashna kuttakara drutena shakyante jnatum vakshyami tatah kuttakaram sah prashnaihi. This means, since usually the questions in astronomy cannot be resolved without the Kuttaka process, I will describe the Kuttaka together with related questions. Brahmagupta devotes most of the chapter 18 to questions based on Kuttaka. In many questions, he adds an inspiration to the student by stating that a truly knowledgeable mathematician is the one who can solve this problem within an year. The Indian astronomy postulates first kalpa, which is a long period of time, and determines the number of revolutions performed by planets around the Earth in a kalpa. Here, the revolutions are counted on an average. The fictitious planet, which uses exactly the corresponding number of revolutions, is called the corresponding mean planet. We will discuss the use of suitable fractions for preserving accuracy and ease of calculations below. So, now this page and the next page are going to have some complicated mathematics, so please bear with me. As stated above, we are trying to find a complete solution to ax minus by equal to c, where a, b, c are integers, and we are looking for integer solutions. We begin by breaking the equation into a new equation, where a and b are smaller. Specifically, we divide a by b and find the remainder r. So we write a equal to bq plus r. This breaking is called Kuttaka. From the word kut, root kut means pounding or pulverizing. Now, I have done this substitution and shown various simplification stages. It's only the last one that we need to pay attention to. The new equation becomes rx1 minus by1 equal to c, where we have renamed x1 as x and y1 as y minus qx. So notice that the two coefficients r and b are smaller than the original coefficients a and b. Thus, the new equation has smaller coefficients, and the original solutions can be recovered from the new ones by this substitution. Thus, we reduce the original problem to smaller coefficients and until the last equation is easily solvable. So now we set up an example of a sizable equation needed in astronomy. This problem comes from Bhaskara 1, his book on Laghu Bhaskariya around 600 CE. The equation that you finally get to solve is this huge equation, this 36641 divided by something times x minus y equal to this number 24 over that same denominator. Now, if you ask a modern student to solve this equation, he will promptly convert it to a decimal number using a 10-digit precision. And as you can see very well, that this equation is rather difficult to solve. We'll have lots of numerical problems. And in particular, this number for most calculations would be treated as a zero. I mean, so it will destroy the original sense of the equation. So we can, as one can easily see, that any further work is unwieldy and likely to cause numerical errors. A Kuttaka student, however, will multiply by this denominator and write down this new equation, so 36641x minus this big number times y equal to 24. Now, even though these numbers are huge, there is no additional numerical problem now because it's over integers. Then I'm just writing down the answers. I'm not going to go through the steps, of course, but the answers seem to be x equal to this number 346688814 plus this other number times t. And what is t? I will explain it in a minute. And y is 32202 plus some t. So let's give the meanings of what these numbers are. So the 24 in the original equation is called the residue of number of revolutions of Saturn. This means Saturn has completed 24 divided by this number, that much revolution, in the current cycle. X denotes the number of days elapsed from the beginning of the current epoch, and Y denotes the number of completed revolutions. So once the revolutions are complete, so it's saying it's gone through some 32,000 revolutions, and at the end, this is the revolution that it has gone through. The parameter t is simply a non-negative integer. It can be arbitrarily chosen, but the value t equal to 0 gives the minimum values of x and y. So now I want to switch over to the second theorem. The Chakravala is the simple generalization of the linear equation for Kuttaka. Consider an equation of the form ax squared minus by squared equal to c. The old one was ax minus by equal to c. After some manipulation, this reduces to the problem raised by Brahmagupta himself in the same chapter on Kuttaka, namely, so he doesn't use a, b, he uses a c, of course. So assume that n is a positive integer, which is not a square. Determine all solutions of the equation x squared minus ny squared equal to 1. This is called the Chakravala equation, where again we seek to determine all integer values for x and y. This problem turned out to be a much harder problem, and it was completely solved by Bhaskaracharya in his book on algebra entitled Bijaganita in the 12th century. During the intervening 500 years since Brahmagupta, various mathematicians in India attempted to make progress on this problem. One important name in that list of mathematicians is called Jayadeva. Very little is known about him. He was in the 10th century, and his all works are lost except for a brief description of his attempt in a commentary on a different work. His ideas were evidently close to the final solution by Bhaskaracharya, but he was unable to finish the needed inductive steps. In fact, Bhaskaracharya gives credit to several earlier mathematicians and only claims a credit for himself for finishing their work. Unfortunately, Jayadev is not on that list. In the Western world, the problem itself was unknown until 1656 CE, when Fermat formulated the same problem as a challenge to fellow mathematicians. Specifically, he asked for solutions to the equation x squared minus 61y squared equal to 1. It's interesting to note that Bhaskaracharya had shown the solution to the same problem, same equation, and many others in his treatise. He also used the Brahmagupta's theorem described below. So, Fermat's challenge led to the intervention of the theory of continued fractions by Brunker and Wallis. Finally, a complete solution was found by Lagrange in his appendix to Euler's book. In the Western world, the equation is named as Pell's equation, who only introduced its proof in his book, but Euler credited it to him and it has stuck. Continued fractions have been very useful in different parts of mathematics, even though they are not taught in a regular mathematics curriculum. It was shown much later by Selenius in 1975 that the steps adopted by Bhaskaracharya give a shorter sequence of the usual continued fractions, and his paper also reports on Jayadev's work as far as it is available through the commentary. I have recently made some changes, some modifications to make the Bhaskaracharya process more efficient. The Chakravala process only needs use of pairs xy which are just x comma 1, simply means y. You can always take y equal to 1 for developing the answer, together with a process called Bhavana, which is a multiplication process, and this simplifies the work and produces the compact answers. So we write our answer as a sequence, and then if you want the final integer value, you can calculate it. Now, I found out that determining all C for which n comma C problem has a solution is equivalent to n comma 1 solution, that means our Chakravala solution, with the current results in number theory. However, the number theory solutions are rather complicated. I, with my student Stuart Wong, just jumped. Okay, I, with my student Jason Wong, have found a way of answering this question by using Bhaskaracharya's own process, and we use Iyengar's proof of the Chakravala result in the process itself. And I cannot go down enough. Okay. Well, let me just say from memory. So we use Iyengar's proof for the Chakravala process, and from that we gave a complete solution to the NC problem, which C's have a solution. Brahmagupta, so now I am coming back to Brahmagupta's theory. He considered a more general question, namely the NC problem. And this problem asks us to solve the equation x squared minus ny squared equal to C, and that's the generalized Chakravala equation. Here C is some non-zero integer, and we seek to find integer solutions. In this context, he established the famous formula called Bhavana. It says that given two solutions of the generalized Chakravala equation, so one solution is called S1, which has components x1, y1, c1. S2 is similarly x2, y2, c2. Their product, denoted by S equal to S1 star S2, is also a solution of the same equation, where S is given as x, y, c, and the formula for x is simply the product of the x's plus n times product of the y's, and y is the cross products of x1, y2 plus x2, y1, and c is just the product of c1, c2, the two numbers here. And so, note that we have intentionally left our n out of this definition to shorten the display. The first step it is clear that what's going on here? Okay. So the first step of solution is the case where C1 and C2 are both -1. Then the product x, y, 1, then the product becomes x, y, 1 and the Chakravala, what I don't see here is it's the product of xy1 with itself, and where c1 and c2 are -1, both -1, and then the product gives me the xy1, that's the s, has 1 as its last number, and that means the Chakravala problem is solved. It's immediately obvious that we don't hope to find such C1, C2 for our chosen n. It is also easy to see that the product is only likely to increase the absolute value of C, and thus we will never reach the desired 1 by just multiplying. However, if x1 and x1 y2 plus x2 y1, that's the y value, is divisible by C1, then the last two entries, y and C1, C2 are both divisible by C1. It is easy to show that then x is also divisible by C1, and Brahmagupta notes that since x, y are both divisible by C1, we get a new triple, x over C1, y over C1, c over C1 squared. Thus, using the new triple, we get a reduction in the value of C. It's no longer just C, the product, but it's divided by C1 squared. This process of bhavana, followed by the reduction process, I propose to call it vibhavana. That's a variation of the bhavana. As an illustration, we prove one of the first theorems of Brahmagupta. It says that if we have S1 as x1, y1, 2, and then we take the vibhavana of S1 star S1, then it is a solution of Chakravala. To see this, you just write S1 equal to S1, and that each one is x1, y1, 2, and then S1 star S2. I am just asserting that it becomes x, 2x1, y1, and 2 times 2, and we do the division for the first x and we do the division, and then as asserted above, x is then automatically divisible by 2, and the solution is x over 2, x1, y1, 1. So that's the success. So what Brahmagupta did is found the first few solutions, and later on it turned out that for the final answer, it's enough to take multiples of x1 or x11 something, and you don't need the different value for y. Then when you multiply, the product of the c's gets bigger, but we use the y1 so that it gets divisible by the first c1, the final answer. And so you go up and again come down. Unfortunately, that's not it. Unfortunately, when people attempted it earlier, they found out that these new numbers that you keep on getting are not necessarily just going up or going down. And that's where Bhaskaracharya came in, and he showed that eventually, if you choose your numbers carefully, in other words, choose as minimum as possible, then it will reach that one. And I guess that's where I will stop. Thank you.
थैंक यू प्रोफेसर सथाए। आइए अब लास्ट टेक्निकल सेशन की ओर चलते हैं, कंट्रीब्यूशंस ऑफ केरला स्कूल। इसके पहले कि मैं प्रोफेसर के राम सुब्रमण्यन को आमंत्रित करूं, उनके बारे में जरूर कुछ बताना चाहूंगी। Professor Rama Subramanian is the Institute Chair Professor at the Cell for Indian Science and Technology in Sanskrit Department of HSS, IIT Bombay. He was conferred the title Vidvat Pravar in Advaita Vedanta for completing rigorous examinations for 14 seminars by Sringeri Sharda Peetham. For his profound work in bringing out Sanskrit text of math and astronomy, KKSU has bestowed prestigious award. Today he will be delivering the lecture on Madhava's infinite series for pi.
Namaste. I thank the organizers for giving me this opportunity to speak on the Madhava's infinite series for pi. Before I proceed further, to introduce you to who Madhava was or the series that he has presented, I just wanted to draw your attention to the problem itself. The problem is essentially to try to find the relation between the circumference and the diameter of a circle. This is all at constant, as all of us know. That ratio of C by D is what is called pi. And the name pi actually comes only in the 18th century. Some people ascribe it to Euler, whereas certain others ascribe it to William Jones. Whoever it is, but the point is, so that peripherion is the term, and that in Greek symbol. So if you write, you will have that pi notation appearing as the first alphabet, and that seems to be the origin of that. So that apart, if you just see the history, so before Aryabhata, so you can see, so it starts with Babylonian, and then we have a few other things I have left out. Then we have Sulvakaras, and the table tells you the kind of accuracies to which it have been determined. Aryabhata in the 5th century gives a value which is correct to 4 decimal places. But in the books which narrate the evolution of pi, In fact, there are several books which have been authored, and the pi is described as the most mysterious number also. Anyway, so if you look at the narrative, you will see that they list this Babylonian and they list a few other things, but after Aryabhata, usually you find a jump. The jump from 5th century to 16th century is something which is quite interesting to note. So Madhava is in 14th century. The question is, why is this omission? Is it due to ignorance? Possibly. But then research indicates that it is not necessarily due to ignorance. We will touch upon it a little later. What is the series that I am talking about? So here is the verse of Madhava. Vyase vadihi nihate rupahrite vyasasagarabhihate trisharadi vishama sankhya bhaktam rinam swam prithak kramat kuryat. This is the verse that actually presents the series. The series which you find below. In fact, during his keynote address, Professor Manjul Bhargava was also alluding to this beautiful series. So here the word Vyasa represents diameter and the word Paridhi refers to the circumference. Rupa is 1. Vyase Varidhi Nihate. Varidhi represents number 4 in Bhuta Sankhya. So you multiply 4 times the diameter. Rupa Hrute divide by 1. Then Vyasa Sagarabhihate is essentially once again 4 times D. And then it says in the later half, Trisharadi Vishama Sankhya Bhaktam. You keep dividing by all the odd numbers. 3 is 3, Shara is 5, Vishama Sankhya is odd numbers. So what you find here in the series is essentially the unit fractions of all the odd numbers, but then they are placed one plus the other minus, alternating sign. This is a really beautiful series, and this is the series which actually for the first time gives the exact representation for pi. So it is irrational number, and therefore you cannot write it as ratio of 2. It is also a transcendental number, but this series, which was found in 14th century, more or less does not appear. In the recent time, of course, things have changed, but if you look at the books on history, so many of them do not carry this. Who is this Madhava? Madhava, who gave this series, the verse which I quoted earlier, is something which has been quoted as the verse of Madhava by later authors in the Kerala tradition. So who are the astronomers? So here you find the lineage, which is rare to find. So we have more or less got who are the subsequent students of those teachers. So this is not a comprehensive list, but it nevertheless represents Madhava. We have then Parameshwara. Then we have Nilakantha Somyaji, so who has authored very important works, Tantra Sangraha and Aryabhatiya Bhashya. I will be quoting something from the Aryabhatiya Bhashya a little later on the same topic, pi. Then we have Jyeshtadeva, the celebrated author of the famous text Yukti Bhasha. Yukti Bhasha, incidentally, is also described as the first textbook on calculus, of late. So many people have done serious research on that, and they believe that this is something which is worthy of being described as the first textbook on calculus. Why? Because the calculus as a subject we know is something which got developed much later, 3 centuries later, but this is something which is much ahead of that, two centuries later, something like that. Now you see, we have the origins of that. See, what one has to understand is, this Jyeshtadeva in his Yukti Bhasha, he says, I am essentially elaborating the techniques which have been employed by the earlier mathematicians and astronomers. And that's why, though we place him in 16th century, all that he explains is something which he has got from the earliers. So that is how he says. In fact, this is written as a commentary to Tantra Sangraha. So therefore, this goes much earlier, and we believe that most of the techniques have been shared by Madhava over a period of time. We don't know exactly what got developed at which stage. But the results of Madhava are really striking. So then we have Shankara Variyar, who has written certain important commentaries. I don't elaborate on that. Pudumana Somayaji, and then we have Achyuta Pisharadi. The signal achievements of Kerala mathematicians, there are a few others, but these are most well known. So first one, as you see, is basically the infinite series for sine function, which will be elaborated by the next speaker, Professor Sriram. Then we have Grignani's Leibniz series, as it is called, the quotation mark. It is actually the Madhava series which I was mentioning to you, which was found almost 3 centuries before. Then we also have a verse which is nicely presenting the derivative of sine inverse function, which I will not elaborate. These are some remarkable results. Many of you may be curious to know, how did Madhava arrive at this infinite series? It looks like a very, very simple, right? Very charming series. In the right hand side, 1 by 3, 1 by 5, 1 by 7, 1 by 11. You put all the numbers, it goes up to infinity. So alternating one, you add all the positives, you subtract all the negatives, you will get pi. It looks like, how did he arrive at it? So it's not too difficult for us to understand. If you want to know how it was arrived by Newton, Leibniz, etc. So later, so that may be a little more complicated, whereas the derivation which is presented here is much simpler. Even from a pedagogical viewpoint, this is something which is remarkable. What lies at the basis of this is essentially two facts. Identifying the similar triangles. See, so in fact, identifying similar triangles, you get profound results. So one of them I'll just show you right away. And then you have a certain nice way of summing up things. So these are two things which lie behind the derivation of the series. Let us go through this. See, in this diagram, you will see that I have taken one quadrant of a circle. Correct? One quadrant of a circle, and I have drawn a square around that. All that you do is, see, this quadrant of a circle is, suppose C is the circumference of the circle, then the quadrant is basically 3 by 4. Now, what you have done here is to just take C by 8 and then you map it to the top line. So the top line P0 to Pn in the right hand side. So you see, I don't know whether this pointer, you are able to see, right? So basically what we do is, so this is divided into n parts. So this is 1/8 of this, C by 8. So you divide this into n parts, n is going to be large. Now you consider basically so the line that actually goes from O to any of these points, so you are dividing it into n parts. So any line that you draw from here is basically called a karna. Why is it called karna? Karna is hypotenuse, as it was introduced earlier. So this is a right angle triangle. O, P0, Pi are going to be right angle triangles, and you conceive of n right angle triangles. So this is how, so you can think of, so if there are n divisions, so you can just think of it to be n right angle triangles. Now you consider just some ith part, Pi and Pi minus 1. So this is Ai minus 1, this is B. So you just think of the intersection of this karna with the circumference. This is Ai minus 1, this is Ai. You consider two consecutive karnas, and then those points are called Ai minus 1 and Ai. You drop a perpendicular from Ai minus 1 onto this line OPI, and that intersects at B, and that intersects at C. You can straight away see that OAI minus 1B and OPI minus 1C are two similar triangles. Okay. Now you conceive of one more similar triangle. So then you form this relation. So this you can very easily see. So you are going to play with these two relations. That is all. Then you will get your very interesting result. Okay. So what you get is, you are going to see what I'll just tell you. I'll take you to one second. The technique is basically to get an expression for Ai minus 1b. Ai minus 1b, so when the number of points is going to be increased, what will happen is, this segment will keep on shrinking and they will become very close to each other. And thereby you will say that this segment can be treated same as the arc itself. This is the technique. Okay, so you are primarily going to get an expression for a minus 1b, which is an exact expression, and then you are going to sum it up. So this is the principle behind it. So you get an expression for this. Let us forget this. So the argument that is going to be presented here is paridhi khandasya ardhajya paridhyamsha eva. Paridhi is circumference. Paridhi khanda is basically a part of it. Tasya ardhajya means the chord length. So the chord length of corresponding to a segment of the circumference is essentially same as the segment itself. This is the argument that is being given. Okay, this is very simple. The argument is straightforward. So he says that this is what it is. So this is what in modern parlance one can call it as local approximation by linear functions. Okay, so that is all it is. So then it is a little algebraic manipulation which we are going to do. So what is being done is, so here you see you are going to get an expression for the circumference, 1/8 of the circumference, right? C by 8. That is what we showed in the diagram. So the expression turns out to be something like this. Okay, these are karnas. So since the karnas are too close to each other, right? So you can call it as K1, K2 as K1 square or K2 square. So this is a standard thing which we do. So if they are too close to each other, you can either approximate to this limit or to the other limit. So anyway, some discussion is taking place on that also. I will not get into that now. And assume that you are going to call it as K1 square, K2 square and to Kn square. Then essentially what you have to do is C by T. There is no approximation till now. You just see. So you have just taken similar triangles, you got this result, right? So you have to basically find a way to sum this. So the Kerala mathematicians found an ingenious way, and they did some algebraic trick which boils down to what one may call as binomial expansion today. So you are going to play with a little bit of algebra, and finally what you will get is, so you will get an expression like this. Don't be worried that there are too many notations, but it is essentially boiling. If you pull this r by n out, what you will see is essentially 1 square plus 2 square plus and so on plus n square. So 1 power 4 plus 2 power 4 and so on n power 4. So they call it as Ekad Ekottara Varga Sankalita. Varga Sankalita is sum of squares. Ekadi Ekottara. Then you have to find out Varga Varga Sankalita and so on. So this is what it boils down to. So without getting into more mathematics, I'll just take you to the final result. So here, Kerala astronomers knew this result. So this is an ingenious way of arriving at this. So they say that sum of the, so I power k means 1 square plus 2 square, you can put anything, right? So k goes from 1 to n. So this is essentially the discrete version of what you today call as, see, integral x dx is, so x to the 2 by 2, right? Integral x to the n is x to the n plus 1 by n plus 1. So this is essentially the discrete version. So they have got this result, and thereby you get this beautiful series which was given by Madhava, which is ascribed to Madhava rather. Vyase Varijinihate Rupahrite Vyasa Sagaradhihate Trisharadi Vishama Sankhya Bhaktam Rinam Swam Pruthakramat Kuryat. Okay. Okay. I have spent about 15 minutes now. So the last 8-9 minutes, I'll just move on to something which is far more interesting than this. This series that we had is a terribly slowly converging series. If at all you have to use this series to find out the value of pi, you may have to calculate million terms even to get the accuracy of Aryabhata, 4 digits. So one will not be able to make use of this series for evaluating pi, though it may be a very beautiful result. So what do we do with this? We have got a nice result. What for? I mean, for the sake of fun, I mean, you can have, but if at all you want to use it, how do you use it? That is the question. So they have found another ingenious way, and that method they call it as Antya Samskara. Okay. So Antya Samskara, which is normally done to human beings, is done for the series also. Okay. So they say that you can terminate the series at any number that you want. All that you had was all the odd numbers, right? If at all you want to find, how will you find? You have to evaluate 1 by 7. You have to evaluate 1 by 9. You have to evaluate 1 by 11. You should get the values to 8 decimal place, 9 decimal place, right? The division has to be done. Then you have to sum all this, then you have to subtract all this. Who will be able to do? It is humanly impossible. Okay? So Madhava has thought about, and then he felt that this is absolutely boring. So they have a nice term in Sanskrit, Jamita. Okay? So Jamita ho jayegi, isliye usko chhod denge. Okay, we will leave this, we will find a different way. So that's what seems to have been done. So make an estimate of the, so you just sum up to something and then you just evaluate what is going to be the contribution of the remaining terms. So that is a nice technique which they have evolved to get this. I am not going to get into the details of the mathematics as far as this is concerned, but I just want to tell you this is a brilliant analysis which has been done. Okay. So here, even if you just consider 20 terms in the series, so you will be able to get a pi value by employing this technique. You will be able to get a pi value which is correct to 8, 9 decimal places. It's not a simple thing, really remarkable. The verses go like this: Yat sankhayatra harane nivritta hritistu jamitaya. I told you, no? Jamitaya hritihi nivritta. That fellow abandoned. I will not do any more. Then he says, Tasya urdhvagata ya samasankhya taddalam gunonte syat. See, it translates to this. So suppose you stop this at number P. Urdhvagata sankhya means P plus 1. Samasankhya. See, P is an odd number. All the denominators are odd numbers. So P plus 1 is going to be even number. That's why Samasankhya, P plus 1. Taddalam means half of it. So he just says, this expression he gives you P plus 1 by 2 and the denominator Tadvargo Rupayutaha. Rupayuta means plus 1, Haraha and so on. So then he finally says, if you do the samskara, what you will get is far more accurate result. See, labdha paridhihi sukshmaha. Sukshmaha means more accurate. Okay, bahukritvo haranatoti sukshmasyat. Even if you were to keep on dividing and finding the sums, this will be far more accurate. How do you know that it is going to be accurate? This is an interesting discussion which is presented in the text. So we don't have time. I'll just tell you, Katham punar muhur vishama sankhya haranena asannatvam. How can you say that this is going to be much more closer? It is an interesting discussion. And I'll just tell you that the argument goes like this. It's a very simple argument, but very crucial argument. I'll just tell you. Suppose you have a series like this and you terminate at some point. Okay. This is the correction term. 1 by AP minus 2 is the Antya Samskara term, let us say. Then he says, you consider one more term. Suppose you stopped at, let us say, 21. Then you go up to 23 in the denominator and then you apply the correction term. Right? So if the correction term were to actually make an estimate of the original series, then the difference of these two should be almost 0. Right? If you have made an estimate of the remainder, you make an estimate at some other term, this difference should be 0, right? This is a simple argument with which they go. So then this has to be sort of 1 by P. Okay? This should be same result. This is what it says. See, Yadi tulyau bhavataha tarihi samskaraha sukshmaha iti nirniyatam. You yourself decide. Very nice argument. So then basically they try to do something and you will do some error estimations. Okay, you cannot make it same. You make some error estimate. You try to minimize the error. And what do you have? So you have something like this. So if you do the samskaras, then you just consider 20 terms in the series. Okay, up to say 40. Okay, 1 by 41 kind of a thing. So there are two orders in which you can do the samskara, and in the first order with 20 terms you will get up to 8 decimal places, 9 decimal places accurate, and in the second order you will almost get to 12 decimal place accurate. This is remarkable result which they have found. And so here is a manuscript, so which actually shows in Malayalam Lipi, see, one of the series like this, you see, Samapancha Hatayaha. See, once you do this correction term, you can further manipulate and express the same series in a different form. See, you express the same series in a different form, you see. But here what you notice is in the denominator you get all powers of 5, 7 to the 5. So as you move, so this is, you just incorporate those correction terms into the series itself and produce different brilliant series. So this is just to show you that this series is represented by the Samapanchahatayaha, Ya Rupad Yayujaha. See, Ayuja means odd number. Yuja is even number. Ayujaha. Okay. Ayujaha Chaturghana Mula Yutaha. You multiply all the odd numbers by 4. So this is the, then Tabhi Shodasha Gunita, see 16 times D, Vyasat, Prithagahrite Vishamayute. Vishamayuti means you sum all the odd numbers, sum all the even numbers, subtract one from the other. So this is how the series is presented. What is the nature of pi? So this has been nicely discussed by Nilakantha. He says, Parghivyasayo Sankhya Sambandha Pradarshitaha. So he discusses the verse of Aryabhata wherein he has used the term asanna. Asanna means something which is close by. Okay. Why did Aryabhata say asanna? Why not give the correct value? This is a question that he poses. You give some rational approximation, then why do you say so? So this is an interesting question, and he basically goes to argue and then say, see, this can be taken like this, right? After all, you have some thread. Okay. So this thread, suppose you divide into 5 parts. So you get some remainder. You make it into 25 parts. You may get some remainder. Right? But if you make it into 2500 parts, a small thread, you will not get remainder, right? Almost it will be same. Something like that. So if you make the unit of measurement very small, then it should be possible for you to represent one, see, in terms of the other, in integer itself, right? This is the question. So why is it not possible if you keep on reducing? So that's the question that he poses. So he says, see, so Mahanta Madhvanam Gatvapi, even if you keep on reducing the unit of measurement, it will be almost impossible for you. See, he says, Alpavayavatvam eva labhyam. He categorically says. So there will be some remainder. Niravayavatvam kvapi na labhyam. So this is what is incommensurability of the circumference and the diameter. This is a very interesting argument which is being presented in Aryabhatiya Bhashya. Now the last part of my lecture. I just wanted to tell you, because many of you would not have seen, this is like a slideshow, a few manuscripts. So how they are sort of maintained. So there are some manuscripts which are looking very nice like this. Okay. So something like this. So you will be able to see in various libraries how tightly they are written. You just notice. So it's not an easy thing to work on manuscripts. So the handwriting will vary. So now you see the third manuscript. This is all the equation. So in fact, so Amartya in his lecture was trying to explain, right, how the equations were represented, Yava, etc. So this is how you will see. So the lines, etc. are basically, if you just look at, see, he says, Bhu, Varga, Varga, this dot, he was saying, right, this is negative things. So this is one of the Kerala manuscripts, which is in Malayalam Lipi. So myself and a couple of students, we used to sort of work on this. So the point I wanted to drive in was, so doing serious history of science is not an easy job. Even to decipher something from the manuscript and then present it is one tough thing. Then interpreting is a second level of thing. So it could be fascinating, but it could be really, really challenging and time consuming. Okay. Deciphering is a problem, content is a problem. Then, hi, what happened? Okay. So the point I wanted to convey was, it has come back, very good. So it is a rewarding experience once you reach the light at the end of the tunnel. So it takes years sometimes. This is the last but one slide. So Donald Knuth, as all of us know, is a remarkable computer scientist who wrote the text, The Art of Computing. Okay? They are like Bibles, real fantastic texts. So he once says, In one of his talks, he says, my major failing as a teacher was I wasn't able to get a single one of my 28 PhD students to realize what a thrill it was to work with the source material. So that is one gets thrill, but it's a challenging thing. So the last part is there are so many things which have been, these are the various other modifications of the series. But then the reason I posed this question, right? Could it be due to ignorance or could it be due to something else? We find that it is not necessarily out of ignorance. So this, when the series was first brought to the attention of the Western scholarship by Charles Wish, people could not digest the fact that this thing has been done here. And therefore, people have been saying, see, indeed the pretensions of Hindus to such knowledge of geometry is too ridiculous to deserve refutation. So this is the kind of statement that has been made when this series, this Kerala work was presented. So the conclusion is, just a couple of points. So we have this interesting verse in Malavikagni Mitram, Puranamityeva, na sadhu sarvam, na chapi kavyam, navamityavadyam, santah parikshya, anyatarad bhajante, mudhah parapratyaya neva buddhi. So the point is we should not just simply abandon that this has been done 8 centuries ago, we have gone far ahead in science and technology, so that doesn't make much sense. So one has to really look into that. So one also has to be very, very careful. So praising something beyond what it deserves is counterproductive. Completely dismissing is far more counterproductive. So what one has to do is one has to just look into it. So as such. So this, based on my own experience of working in history of science for several years, at least a couple of decades, I must tell you that it is a rewarding experience. It is certainly not obsolete. As many of us who have been teaching modern mathematics, we realize that there is something which is far more. What is interesting is the simple and intuitive ways in which some of the results have been arrived at by the ancients are truly astonishing. I just gave you one example of pi, and then there are several other results which can be highlighted. Even if there are better methods for understanding something, looking into the ancient provides us certain very useful insights. I can tell you out of my own experience, and it greatly facilitates understanding the development of the subject. So we would be doing considerable harm to our children if, while framing mathematics curriculum, so for which we have an opportunity now, if we do not pay attention to highlight any of them in the impressionable age. This is very important, and the teachers have to be properly trained for that. Making unverifiable claims or exaggerated claims is certainly unscientific. But what is scientific about suppressing or making uninformed statements or blind rejection? Okay, thank you for your attention. So my time of almost 30 minutes is over, 29 minutes. I think we should just proceed with the other talks.
Thank you so much, Professor Ramasubramanian. And our next guest speaker will be Professor M.S. Sriram.
Good evening.
He is the president of the Professor K.P. Sarma Research Foundation, Chennai, an organization devoted to Indic studies, and also the president of the Indian Society for History of Mathematics. He has been working in the field of Indian astronomy and mathematics for nearly 30 years. Currently, he is working on Siddhanta Shiromani, the major work of the great Bhaskaracharya. May I invite Mr. Professor M.S. Sriram to talk about the subject Calculus of Trigonometric Functions.
So I'm Sriram. I'm talking about calculus of the trigonometric functions. And Professor Ramasubramanian would have talked about the infinite series for pi. So now I will be talking about the trigonometric functions, how their calculus was handled. So the main thing is, that the important thing was the non-uniform motion of planets in astronomy. Okay, that is where there was a need for trigonometry. So trigonometry arose in the context of astronomy. Okay, here there is a figure in which O is the observer and C is a point which is at a distance r from small r from it in a direction of apogee. Okay, so now the planet moves uniformly in a circle of radius r, capital R, with center at C, not at O. So it is not move uniformly with respect to O. The longitude with respect to C is theta 0, gamma Cp, so which is moving, changing uniformly. Whereas true longitude is theta, is gamma OP, which is not changing uniformly, it's non-uniform motion. Okay, so now we can show that theta is approximately equal to theta 0 minus sine inverse r by r sin m, where m is theta 0 minus theta a. So which is for small r by capital R, it is theta 0 minus r by r sin m. So this is the expression for the longitude as seen by an observer on the earth at O. So the trigonometric sine function comes. So these are sine function etc. made their appearance in astronomy. Yeah. So now in an approximation, you can theta is theta t, I write it as theta t, true longitude, then theta t is theta 0 minus r by r sin m in an approximation. Now in a modern way, if you take the derivative of this, you get d theta, theta t by dt, d theta 0 by theta t minus r by r cos m dm by dt. Now Bhaskara in 12th century, Bhaskaracharya gives the same relation though expressed differently. Here d theta t by dt is the true rate of motion called sputa gati, and d theta 0 by dt is the mean rate of motion called madhyama gati, and dm by dt is the kendra gati. So he expressed it in terms of a sloka, and in fact he calls the true rate of motion as the tatkalika gati, instantaneous velocity. Bhaskara essentially states that the derivative of function is the sine function is the cosine function. Actually, it had been discussed by Manjulacharya and Munjala even in 10th century, but more precise formulation by Bhaskara. So, though not fully developed, the idea of derivative, instantaneous velocity, etc. were discussed by Bhaskara 5 centuries earlier than in Europe. And integration methods were also described by Bhaskara in his Siddhanta Shiromani, his great work, and it was developed further in Kerala School of Astronomy and Mathematics. For instance, by calculus area integration, they obtained the area of a sphere or the volume of a sphere. So now we will discuss the infinite series for sine and cosine functions. In Ganita Yukti Bhasha of Jyeshta Deva and Mahajyanayana Prakaraha of an unknown author. So infinite series for pi and also sine and cosine functions ascribed to Madhava by later astronomer mathematicians of the Kerala school. Now is Ganita Yukti Bhasha. So essentially it's the rationales of mathematics, okay, of Jyeshta Deva gives detailed derivation of all the infinite series. Now this book is translated by K.V. Sharma and explanatory notes by Ramasubramaniam, Srinivas and Sriram, that is myself. Now K.V. Sharma also noticed a manuscript named Mahajyanayana Prakaraha, which describes the infinite series for sine and cosine functions and also gives upapatti or derivation of the thing. He ascribed the authorship to Madhava, but David Gold and David Pingree edited and translated this, but did not provide any explanation. Now Raja Rajeshwari, a PhD scholar in Chennai, and myself have provided the explanation based on the upapatti in the manuscript. Now this it is very similar to the upapatti in Ganita Yukti Bhasha, but somewhat briefer, and both derivations are based on the iterative solution of discrete version of the integral equations Sin theta is integral cos theta d theta is theta minus integral of 1 minus cos theta prime. And 1 minus cos theta is integral of sin theta, 0 to theta. So discrete versions of this. So now before we proceed, we have to know certain results which are there in ancient text, even Aryabhatiya. So which is in 499 AD, he gives the sum of first n integers. So j is equal to 1 to n, he gives it as n into n plus 1 by 2. So now we have the sum of sums or second sum. So that is this r into r plus 1 divided by 2, and that you sum from r is equal to 1 to n. Okay. So that is essentially you will get n into n plus 1 into n plus 2 divided by 2 into 3. So these are the double sum. Okay. So in Ganita Kaumudi, a text of 1356, scholar Narayana Pandita, a mathematician, generalized this to kth sum. Okay, so the kth sum of these integers defined as above, that is n into n plus 1 etc. up to n plus k divided by 1 into 2 into 3 up to k plus 1. So the denominator is k plus 1 factorial, as you will know. For large n, this becomes n to the power of k plus 1 divided by 1 into 2 into 3 into k plus 1. This plays a crucial role in the infinite series expansion of sine and cosine functions. Now, the author is Mahajyanayana Prakara, around 16th century you can say. So he gives the sloka for the infinite series expansion, Nihatya Chapa Vargena, Chapam Tat Phalani Cha, Hare Samula Yugvargayi, Tijya Vargayi, Hatai Krama, etc. So what he is saying is, r sin theta is r theta, you write it like that. Then below it, you multiply it by this, by the square of that, and divide by 2 squared plus 2 and r square. So now in the next, below that you write the previous result multiplied again by r theta square divided by 4 squared plus 4. So like that. So this is the series as given in the left hand side. So modern notation, sin theta is theta minus theta cubed factorial 3 plus theta to the power of 5 factorial 5, etc. So it is, it's very interesting how he gets this. He gets a coupled equations for r sin theta and shara r into 1 minus cos theta. So he says Nihatya Chapa Vargena Ityadina Ishta Chapasya Jaine Kidrushu Upapatti. What is the proof, for the statement? Tat Pradarsanaya, for demonstrating that result, Vrutta Malikya, a circle is drawn, and Matru Pitru Rekancha Kurya. Let the east, west, and north, south direction be marked. So we'll go to the figure is there in the next slide. So ES is a quadrant and EC, okay? EC is an arc, okay? Arc which is equal to capital R into theta, where theta is that angle and R is the radius of the circle. Now this is divided into n equal portions. Okay, EC is EC1 plus C1 C2 plus etc. etc. Where each of them EC1 is equal to C1 C2 etc. etc. is R theta divided by n, which I write as alpha. And partially EC is Cj, up to Cj if you take, it is R theta j, it is j into alpha. Now you draw Cj, Pj parallel to OS, okay, parallel to OS. So that will be the bhuja of theta j. Cj, Pj is R sin theta j, it is R sin alpha j. Now Cn is C and Pn is P, and Cn, Pn and Cp is equal to R sin theta. So Bj, so the bhuja of the arc up to Cj, ECj, so that is R sin alpha j, and similarly Koti is Cj, Tj or cos alpha j. Okay, so now you also consider the midpoint of the arc bit Cj plus 1. See, Cj plus 1 is a small bit of this, small part of this. 1 by nth part actually. So then you take the bhuja of the midpoint. So mj plus 1, qj plus 1. So it is R sine of alpha into j plus of. So similarly, Koti of this of arc EMJ plus 1. Now you also consider Bhuja Khanda and Koti Khanda. See, Bhuja Khanda is the difference of R sines of the successive R sines. So Bj plus 1 minus Bj. So that is Cj plus 1f in the figure. Similarly, Koti Khanda is Kj minus Kj plus 1 is Cjf. Now, Samastajya of arc bit Cj plus 1 is the full chord of Cj plus 1. Okay, that is for very small arc, it is equal to arc itself. Then author says very crucially that the two right triangles Cj plus 1 FCj, so that's a small triangle, and OQJ plus 1 MJ plus 1 are similar. Tatra tat kshetradvayasya tulyakarat nirnayaha. The two geometrical figures are similar. Okay, so he explains why it is so, because OMJ plus 1 is perpendicular to CJ plus 1 and CJ plus 1 F is perpendicular to TJF. Okay, it is very easy to see if you draw the figure. So then because of the similarity of the triangle, see CJ plus 1 F, you see that is the small triangle part divided by CJ plus 1, so that is in the small triangle. In the big triangle, OQJ plus 1 divided by OMJ plus 1, they are equal. Now CJ plus 1 F is a Bhuja Khanda, okay, and OQJ plus 1 is the Koti at midpoint, and CJ plus 1 is a chord which is essentially alpha, and OMJ plus 1 is equal to R. So you get Bj plus 1 minus Bj, the Bhuja Khanda, the R sign difference is alpha into Kj plus 1, Kj plus half, K of J plus half by R. And similarly, Koti Khanda is alpha of Bj plus half by R. So, tadanim tasya chapakandasya samastajyam bhujakotibhyam prutak nihatya trijya dve api vibhajya labdhe koti kandaha bhujakandam bhavataha. That is what he says. So now this R sin theta is Cp, so it is Bn minus B0. Now this is written as sum of the R, this thing, Bhuja Khandas. The whole Bhuja is written as the sum of the Bhuja Khandas. So Bn minus Bfn minus 1 plus Bfn minus 1 minus Bfn minus 2 plus etc. plus Bf1 minus B0. So it is written as the sum of the Bhuja Khandas. So, and similarly, using the relation Bj plus 1 minus Bj is alpha into Kj, K of J plus half by R. So he says Jiva is alpha by R into sum of this K at J plus half. So in the words of the author, when the arc is multiplied by the sum of cotijas proceeding from the midpoint of all the arcs and divided by radius R, what results is the Jiva. Jiva or Jya is the sin theta or sin theta. So we have Cp, R is R sin theta. So Cp is R, corresponds to arc EC. The bhuja of that is R sin theta, is alpha by R into sum of these cotis and midpoints. And similarly, Shara is actually R minus R cos theta, it is EP in the figure. It is alpha by R into sum of the bhujas at midpoints. Okay. Now Sj plus half is R minus Kj plus half. So you get R sin theta is alpha by R, and take the sum of R minus S of J plus half for J is equal to 0 to N minus 1. So the bhuja is written as a sum of the R minus S kind of a thing. So R sin theta is R theta minus sum of the sharas into alpha by R. So this is nothing but the discrete version of R theta minus integral 0 to theta R into 1 minus cos theta prime d theta prime. So essentially alpha by R plays the role of d theta prime. Similarly, S is equal to R into 1 minus cos theta is alpha by R into sum of the bhujas at midpoint. So it is the discrete version of r into 1 minus cos theta is equal to integral 0 to theta r into 1 minus sin theta prime d theta prime. Yeah. So you have r sin theta is r theta minus r alpha by r, sigma is j plus half. Okay. And r into 1 minus cos theta Shara is alpha by r into sum of the b of j plus half. So the author uses an ingenious iterative technique to solve these equations and obtain the infinite series. So these iterative techniques were there even from a long time, in Indian astronomy and mathematics, even from 6th, 7th centuries. 6th, 7th centuries. So in the first approximation, you take the charas to be 0. So r sin theta is just r theta. You know that is true when theta is small. But here it is the first step for arbitrary theta, and s is 0. 1 minute. Now in the second approximation, s, which is a sum of bhujas, okay, and the bhujas are taken to be arcs themselves. So s is equal to r into 1 minus cos theta is alpha by r into sigma of bj plus half, which is approximately equal to alpha by r sum of the arc ecj plus half. So and that is close to r ecj. So this is s is alpha by r into sum of the arcs. So that can be, now arc is j alpha, arc ecj j into alpha. So it reduces to sum of j, sum of integers 0 into n minus 1. So you get Shara is for large n alpha squared n squared by 2r. So that is equal to r theta square by 2r. So the Shara is s is equal to r into 1 minus cos theta is equal to r theta squared divided by 2r. At this stage, this is the result. So we have used sigma of j is close to n squared by 2 for large n, and is the integral discrete equivalent of integral x dx is x squared by 2. Okay. So here he has given how he described this when the arcs from the beginning of the desired arc to the ending points of the arc bits are summed over and multiplied by the arc bit, half the space of the desired arc is obtained, and whatever appears in the deficiency of the excess will get eliminated, just as the tail of a frog's new offspring. So this is an interesting comparison he makes, but that is for very large n. So this is the result. So the next result is now r sin theta is r theta minus sum of these sharas. Now the sharas now here is not 0, but they are equal to, we have got it equal to sum of this r plus half alpha. Okay, the sum of that. So r sin theta is r theta minus, you see, r sin theta is r theta minus sum of the shara, and shara itself is sum. Okay, so you will get a double sum like this as displayed. So it is sigma sigma of r, second sum of r, which is n into n minus 1 into n plus 1 by 1 into 2 into 3. And in the large n limit, this can be replaced by n cube. So then using alpha n is equal to r theta, r sin theta is at this stage is r theta minus alpha cube n cube divided by r squared into 1 into 2 into 3. So that is r theta minus r theta whole cube by r squared into 1 into 2 into 3. Yeah. So he describes this. This is not what we have interpreted. Okay, we have just written down whatever the author said in modern language. That is all. We have not, made any interpretation. So he says that Kotijyan Antarabhutahi Sharakandam Hatva Trijaya Vibhajya Labdam Istajya Istachapad Vishodhya Shishtam Istachapajya Bhavati. Okay, so like that he goes on. So essentially what I showed in words. So what we find is, at this stage, r is equal to s is equal to r into 1 minus cos theta is equal to r theta squared divided by 1 into 2, and r sin theta is r theta minus r theta whole cube by R square or into 1 into 2 into 3. See, because they always talked in terms of arcs, not angles, arcs and distances, right? So that is why you get these factors of R. So using S is equal to, so next stage is described in detail, okay? So now you see, you plug this form of the jar in the expression for the Shara, so then you will get, if you do that, so then Bj is this, J alpha minus J alpha whole cubed by this. So when you do this, if you are summing J cube, J is equal to 0 to n minus 1, you will get n to the power of 4. And when it is multiplied by alpha to the power of 4, it will become r theta to the power of 4. So in the next step, Shara becomes these two terms, r theta whole squared by 2r minus r theta to the power of 4, r cubed into 1 into 2 into 3 into 4. So now you take r sin theta is r theta minus alpha by r into sum of the Sharas. Now Shara itself is Sj is this, it involves the fourth power of j. So when you put this here, okay, and sum it over, so sum of j to the power of 4, j is equal to 0 to n minus 1, it will become n to the power of 4. So alpha to the power of 5, n to the power of 5, alpha to the power of 5, n to the power of 5. So in the next step, you will get r sin theta is this. So you keep repeating this, So you do the Shara, then do the Bhuja using the Shara, and then in the next step, use the find the Shara using this Bhuja. So like that you are doing iteratively. So then he says that Yevam Uttarottara Palani Nyayani. Bring out the results in the same manner. So the author notes that n squared plus n is n into n plus 1 and states the series for r sin theta and r into 1 minus cos theta in the modern form, apart from, of course, the appearance of r. Okay, so r sin theta is equal to r theta minus r theta whole cube by r cube into 1 into 2 into 3, sorry, it must be r square. And next term is r theta to the power of 5 by r to the power of 4, etc. So it will be factorial 5 will be there in the denominator. Similarly, the Shara r into 1 minus cos theta is this, the expression. And of course, if you take r cos theta, you will get, you get cos theta is equal to 1 minus theta squared by factorial 2 plus theta to the power of 4 by factorial 4 and so on. So this is how it is done, in an iterative fashion. You find the Shara and the Jia, okay, sin theta and this thing. So then he will also tell, you see, how the r sin theta is calculated for any theta, using some mnemonics, Vidwan, Tunnabala and all that. So ready-made expressions are there, tables are there for finding the r sin theta for any value of theta. So this is the how it is infinite series is derived. This is the calculus. Calculus ideas are given, used. It is large and limit and so on. So as you can see, this is essentially similar techniques as the infinite series for pi. Only thing is that in pi, what you use is sigma n to the power of k, okay, sigma j to the power of k, for j is equal to 1 to n, it will be n to the power of k plus 1 by k plus 1. So here it is, the sum of sums. So you get factorial k and all that, like this. So this is how things were handled using the Shlokas to express scientific results. So this is how it is, many more results are there, integration results are there in Yukti Bhasha and other texts. Second Taylor series expression are there. So this is how calculus was done using, the Sanskrit language, casting in terms of shlokas and giving upapattis or proofs, okay, for each of them. So thank you.
Thank you. Professor Sriram. Our next guest speaker is Professor Sri Krishna Gopal Rao Dani. He is a professor of mathematics at the Center for Excellence in Basic Sciences, Mumbai. He was also the Chairman Commission for Development of Exchange of International Mathematical Union for the period 2007-10. Professor Dani was awarded the Shanti Swarup Bhatnagar Prize in 1990 and World Academy of Science Prize in 2007. He will be talking on pioneering historians of Indian mathematics.
Hello, good afternoon, everyone. Thank you for the introduction. And okay, let me begin by sharing my slides. Yeah. Now, all through the day, you have heard many talks on various aspects of history of ancient Indian mathematics, from all the way from Silva Sutras to until the Kerala mathematics and all. Now, an integral part of study of history of mathematics is the historians who actually bring out the material. I mean, some of this was emphasized by some of the speakers, but I'd like to emphasize more. History is always a developing theme. I mean, what we would have known as history in the last century would be quite different from the profile that you would see today, and maybe after some decades, the pattern would again change and so on. So a lot depends on what the sources are and how much effort is put in to disseminate them, incorporate them into the body of history of mathematics as such. So in this process, the people who contribute, the historians, make a big difference. So now I'm of course here going to concentrate on history of Indian mathematics. So the yeah. So in the 19th century, many Europeans, mathematicians and otherwise also got interested in the study of ancient Indian mathematics. Many of the topics that you heard about today are covered in that. So Shilpa Sutras, George Thibault was mentioned by Professor Dalir in his talk. There's also Burke, who worked on the Apastamba Shilpa Sutra. Then the Siddhanta Astronomy, on which we had various talks. There's the well-known book of Colebrook. There's also other people among the names that you see on the screen. Rode was mentioned again in Professor Dalil's talk. There's also a few other names. There's J.R.K., who is known for somewhat his critical comments on various things, and Lancelot Wilkinson. Then there are also the Kerala mathematics, Charles Bish and others, some of which was recalled by Professor Ramasubramanian. Then there are also general historians who laid some emphasis on the Indian mathematics. There's Moritz Cantor, David Eugene Smith, for instance. It's also known for his forward to Ganita Sara Sangraha of Mahaviracharya, that was edited by Rangacharya in 1912, so early 20th century. Florin Kayori is also one of the in that. Soon enough, many Indians were also were to make a dent in the activity, and they were to participate in that. And that's the part that we are going to talk about here. One of the earliest names is Bapudev Shastri. He is one of the very prominent early figures. It's a native of Nagpur. And he was brought. Lancelot Wilkinson was an officer of the East India Company. He spotted him at on his visit during in Nagpur, and was quite impressed with him, and brought him to Sihor, where actually the East India Company was running a school in the modern style. But actually, unlike many other Britishers, Lancelot Wilkinson was someone who believed that the education system in India should be Sanskrit based, or based in the native laws, and that's how he was trying to work it out. And Sihor School was one of his sort of major efforts, and where he himself also taught. So Wilkinson is seen to be full of praise for the ability of Bapudev Shastri, and raves about how quickly and well he could absorb Euler's book on algebra, which was kind of the standard of the at that time in some way. And he also comments on how Bapudev Shastri could blend the traditional works, especially the work of, especially from Bhaskaracharya, with modern learning. I mean, so one should sort of keep in mind that at that time, Bhaskaracharya's work, I mean, the Siddhanta Shiromani and the more pure mathematical parts of it incorporated in Lilavati and Bijaganita were kind of the flag bearers of the mainstream learning in the traditional setup. And yeah, so Wilkinson is commenting about Bapudev Shastri being able to blend the traditional knowledge into the modern learning, and in fact, that was sort of one of Wilkinson's principal interests as well. Now, Bapudev Shastri got an appointment in the Banaras Government College, which later became the Sampurnananda Sanskrit Vishwavidyalaya, and he rose to eminence as interpreter of Sanskrit astronomical texts. I mean, they're not. I mean, so, though of course some of the things had been translated and edited and so on, a lot more needed to be done. And Bapudev Shastri was kind of instrumental in starting this activity. I'm going to say a little more about that. Among his recognitions, in 1887, he was awarded the title Mahamahopadhyaya by the then British government. Now, here is a picture which one can see online of Bapudev Shastri, and here the noticeable thing about it is the globe here. So there are some aspects of this picture that's more difficult to understand. I don't comment about that. But anyway, there it is. So, and it is from 1870. That is something that can keep in mind. Now, among Bapudev Shastri wrote many books in Sanskrit. Sanskrit was the medium of instruction at the scholarly discourse in India at that time. I mean, at this point, it might sort of seem difficult to imagine, but I mean, already in the 19th century, Sanskrit was something that to keep in mind. Sanskrit was the kind of language of scholarly exchanges, and so on. So now, while some of these works were expositions of modern mathematics in Sanskrit, and these included Euclidean geometry in the name being used as Rekha Ganita, and trigonometry, that is trigonometry. Others were a blend of methods from the Siddhanta tradition of Aryabhata, Brahmagupta, and Bhaskara, and so on, especially from Bhaskaracharya, and with the modern approach. Is known for his translation of the Surya Siddhanta into English, and publication of a corrected version of the English translation of Siddhanta Shiromani. This was prepared by Wilkinson. I have noted here in parenthesis that Wilkinson died in 1841 prematurely at just the age of 36. and that work was completed by Bapudev Shastri. Now, Bapudev Shastri is also known for his commentaries on Lilavati and the other parts of Siddhanta Shiromani. I think both Ganita and Gola chapters. There's probably some confusion about whether all of this was done, but there's a good deal of good part of Siddhanta Shiromani was translated by him. The second person that I'll come to is Sudhakar Dwivedi. He is, I think, is a sort of more mature phase in this development, following the work of Sudhakar Dwivedi. I mean, so following the work of Bapudev Shastri, about whom I mentioned the last few minutes. Now, yeah. So Sudhakar Dwivedi studied in the Banaras Sanskrit College, Banaras, the seat of learning at that time. They under the tutelage of Pandit Devakrishna, professor of Jyotisha. So Jyotisha was the key holder of the knowledge of mathematics, for instance, even as late as the 19th century. He also had the benefit of knowledge, knowing Bapudev Shastri, who was also taught in the same in that college. In 1883, Sudhakar Dwivedi was appointed chief librarian of the college. Now, this was a big boon because the library, Saraswati Bhavan, which was very rich in manuscripts, and this provided him a great opportunity to for the scholarly pursuits, and he made good use of it, and very beneficial for their activity as a whole. Now, Sudhakar Dwivedi wrote many books. This is not only, I'm not talking only about Indian mathematics, but also introducing modern mathematics in Sanskrit. So, and later in Hindi. So the development was that Sanskrit gradually gave way to Hindi, especially in the, perhaps mainly in the in North India, and gradually Hindi began to get currency as the medium of scholarly medium of higher learning, so to speak. So and so some of his books, initial books, are in Sanskrit, later ones, and are in Hindi. So there's notably a book on differential calculus in Hindi, which appeared in 1886. This book I noted here. Book, of course, it cannot be compared with in terms of standard with modern books of calculus, but I think it gave a very good exposition of the subject. He was, I mean, I mentioned the transition from Sanskrit to Hindi, and Sudhakar Dwivedi was himself an enthusiast for in promoting Hindi, and did a good deal to propagate it. So he was also conferred the title Mahamahoopadhyaya, and that was in 87. I think that was around when the title was distributed, and was appointed professor of mathematics and astronomy at the Government Sanskrit College upon retirement of Bapudev Shastri. So he succeeded Bapudev Shastri not only academically in some sense, but even in terms of administrative leadership and so on. So which established some continuity in the process. Now, here is a picture of Sudhakar Dwivedi, fairly well known. Yeah. The works of Sudhakar Dwivedi. Now, you would have Panchasiddhantika of Varahamira is a well-known book in the Siddhanta tradition. Don't recall if it was mentioned in some of the lectures today, but it is something very important. And So currently the principal, one of the early sources is a book by Siddhant Dwivedi and George Thibault. This book is much cited and sort of still a basis to some extent in the study of that segment of the tradition. So this was reprinted in Lahore in 1930 and again in 1968 at Varanasi. Dwivedi also had his own edition with commentary and called Prakshika and with English tradition. The Panchasiddhantika is a treatise. I mentioned its importance. This is it's dated from 575 CE. Note that this is sort of a little before Brahmagupta and the Bhaskara the first. So it's on mathematical astronomy, and it summarizes 5 earlier astronomical treatises, the origins of which are now lost. We know about the earlier works only through Panchasiddhantika. The 5 Siddhantas are Surya Siddhanta, Romaka Siddhanta, Paulusha Siddhanta, Vishishta Siddhanta, and Paitama Siddhanta. And the book is not simply an explanation, it's a kind of critical appreciation of the knowledge contained in these works. It's a blend of astronomy in the Vedic tradition from the Vedanga Jyotisha and also anti-Hellenistic astronomy, which had major influence on India at that time. The book of Dwivedi and Thibault contains, this I already said, contains a critical review of the work and has been much cited. Yeah. Another notable work is Ganaka Tarangini. Now, this is a unique book. It's in Sanskrit on the lives and works of Indian astronomers and mathematicians. It was composed in 1890. And first appeared in serialized form in the monthly journal called Pandit. Pandit happens to be have been a major journal at that time, especially in the ancient India related works of various subjects. The papers of Thibault and Shilva Sutra, for instance, also appeared in Pandit. There have been, okay, so going back to Ganaka Tarangini, there have been many posthumous editions of this, including recently, and I think it's probably still available in print. There are, the book has 73 biographical sketches, and these are listed alphabetically and, listed chronologically. That is the oldest first and so on. Starting with Aryabhatta. Aryabhatta, is from 476 CE, which corresponds to 398 from the Shaka era, including also the 73 figure includes also Bapudev Shastri, and Bapudev Shastri is not the last one. There are also a couple of more names, related names coming into the picture. So the sketches usually they are some of them are short, maybe a paragraph, not a full page, not a page, but some of them go into a few pages. The description proceeds systematically in 3 parts. So the details about birth and family background, etc. So then some highlights of the work, and finally a short review of the work, including brief comments on the merits and shortcomings, the special points about the work, etc. I not brought in many comments on that. I think it's probably better to look at it in the original. There are However, so there are some notable omissions in that, which is somewhat difficult to explain. It's, and that is the Bhaskara the first. Then Mahavira and Narayana Pandita also are not mentioned. And somehow this may have something to do with the overall knowledge about these works. Some of these works mentioned in North India. I mean, there's a sort of North Indian base involved here, and some of the omissions may have to do with that aspect. So and also the name of Madhava is also missing. There is not included in the write-up here, but there is the name Parameshwara occurs, but it's kind of in a sort of very vague way, and I mean without enough detail, etc. Okay, so apart from Ganakatarangini, in terms of general history, also Sudhakar Dwivedi has contributed an interesting work. Now, this book is in Hindi. This is Ganit Ka Itihas, Pehla Baab Patiganit is the title. I think the second part didn't appear. It's the only one that we have. I mean, second or later parts didn't appear. Now, this is an interesting book. This is available online. You can search for it and look at it. So, it's inspired and based on his lectures at the Banaras Government College, which he was teaching. The book is a kind of comprehensive history and in approach, not in detail. So the book begins with numerals and modes of reckoning in various ancient cultures, apart from the various Indian traditions. Includes also from Egypt, Babylonia, Rome, Tibet, and also the Arabs, etc. You can see that he has somewhat poor opinion about the Arabs, which will probably be viewed critically in our time, but that's how it seems to have been at that time in India. The book then goes on to a variety of arithmetical concepts, series summation, first finite series, logarithms, etc. These are descriptions are brief, limiting to whether and how the topic is dealt with by various authors, and some key observations. So various important results and problems have been highlighted in some book. So Fermat's last theorem, for instance, is mentioned. The works of Euler, Lagrange, Kumar are recorded. There are also references to various ancient scriptures, and the style is quite interesting. It's chatty, and though it's somewhat patchy. I mean, like in casual conversation, it sort of moves on from one to another thing in some patchy style narrative. However, but makes quite an interesting reading. I strongly recommend to reading it to all the audience. So, in the later part of, I am continuing with the same Ganit Ka Itihas. In the later part, over 40 pages are devoted to a listing of well over 100 mathematical and related personalities. Now, this is not meant to be a list of mathematical personalities. It is the listing of all the people that have figured in the earlier part of the book. So, and brief biographical details are included in various cases. Now, interestingly, the first entry happens to be Khalifa Abbasidi al-Mansur. His name you must have come across. It was during his reign that conference was arranged where there was a delegation from Sindh which took the work of Brahmagupta and with its dissemination at the conference was sort of instrumental in the Indian mathematics getting into the Arab studies. Then it also the entries also include things names like Aristotle, King Ashoka for certain contexts about Then Albert Dürer, Cardan. There's a story about about his having committed suicide, which struck about. Which is why I put this exclamation mark. But then from other Indian names, the Jagannath Pandit, you would have heard of. Tulsidas features in some way. Narayan Pandit is mentioned. About Newton, Trivedi says, संसार संसार में सबसे बड़े पंडित गिने जाते हैं. So, on Plato, the author states, गणित पढ़ाने के लिए स्कूल बनाने के यही आदि पुरुष was the first person to bring up an institution purely for mathematics. गणित पढ़ाने के लिए. So there is also one Madhavacharya mentioned, but he is not clearly not the one from Sangamagaram. Okay. Apart from these biographical works, there's another and perhaps more important work, more important contribution of Sudhakar Dwivedi is translating and editing of various ancient works, which has sort of built up a treasure for later people to follow. So there's listed here that I don't think I need to read all this. So this starts from say Lilavati and Bejaganita of Bhaskaracharya. I also included the period of that work. So the Siddhanta Tattva Viveka of Kamalakara is one of the very important works. One of from the later part of the Siddhanta tradition. So I think around that point it sort of matched the works of Bhaskaracharya in appeal. So the Siddhanta Tattva Viveka was one of the very important works to be used for. Then another important one I would highlight is this Trishatika of Sridhara. Sridhara is one of the people, enigmatic scholars in some way. There's been a lot of confusion about his period and also whether he was Jaina or Hindu and so on. And now the controversy seems to have sort of settled, and he's supposed to be from about the 8th century and from the Jaina tradition. And this Trishatika is one of the other than Mahaviracharya's the Ganita Sara Sangraha that was mentioned, the works of Sridhara, there are two, Trishatika and Patiganita is the other one. And the edition of Trishatika was brought out by Sudhakar Dwivedi. Then this includes Brahmasputa Siddhanta of Brahmagupta, then Surya Siddhanta, Vedanga Jyotisha, and so on. There's a whole lot of work he seemed to have done. This continue all through his career in that respect. Let me move on to the last person I want to talk about, and this is Vibhuti Bhushan Datta. He is probably more familiar to everybody because of his two books, source book, which serve as source books in the for ancient Indian mathematics. Vibhuti Bhushan Datta, he was born in a poor family in Chittagong district, now in Bangladesh. He did his BSc in 1912 and MSc in 1914 in Presidency College. He received DSc from the University of Calcutta in 1920 for his work on hydrodynamics. So it's in a way he was sort of mainstream pure mathematician, mainstream applied mathematician, to turn to history. Actually, I have not noted here for want of fear of losing time, but his teacher, Ganesh Prasad, was also greatly interested in history, and he himself wrote books on history. So I'll not go into that. And Ganesh Prasad, it was under the influence of Ganesh Prasad, two people took to history of mathematics. So, and one is of course Vibhuti Bhushan Datta, and the other one is in mind is the co-author of Vibhuti Bhushan Datta, Adesh Narayan Singh. Both were students of Ganesh Prasad. So, and so after his equivalent, DSc in applied mathematics, he devoted himself to history of mathematics. And something more, he had an ascetic orientation all through. From the childhood himself, he was kind of spiritually oriented, is what is said. And then even in terms of accepting the professorship, he was kind of unwilling, but was persuaded because they could not find anybody, etc. And but in 1929, he resigned from the post to pursue philosophy and religion. So, and along the way, of course, he was working in history, especially of mathematics, which I'll talk about a bit. Now, Swami Vidyaranya, this is not another person. It's the as I said, after he. Okay, so we'll come to. It's the same person we are talking about, and I'll come to that detail as we go on. So later again, he was persuaded by, after resignation, he was again persuaded by Ganesh Prasad to return to academics, and in 1931, by special invitation, he delivered what were called leadership lectures at the Kolkata University. These lectures were later materialized into the book on the science of the Shulba, which was mentioned in the talk of Sudali this morning. So it's one of the references that sort of canonical references to the area. Soon after 1933, he finally retired from the university and went wandering around, living on charity of others and so on. And in 1938, he became a sannyasi. And that's when he took the name Swami Vidyaranya. By this time, in 1930, he had, of course, acquired a great reputation as an authority on history of ancient Indian mathematics. He is well known for the two works which I alluded to. So, jointly with Adesh Narayan Singh, they named History of Hindu Mathematics source book. Now, so here I think I'll take this occasion to explain something, though it is mentioned as history of Hindu mathematics. It's sort of it includes also the mathematics from the Jainas and so on. So often somehow we tend to conflate Hindu and Jaina mathematics, but the Jaina mathematics has its own identity, which also needs to be sustained. And though today in today's talks there is not much reference, I would strongly recommend to people to get to know more about Jaina mathematics as well. This of course included, some of it is included in this, and there is also some other works of Datta, but there is also more to it, which I will not have the time to say. So, but I just want to emphasize this aspect. This work, it was earlier in two separate volumes, but later it's now more or less it's a 2-volume book. It continues to be a basic reference in history of Indian mathematics is an authoritative account on arithmetic and algebra. Okay, so many of the things that that we talked today, there's a good amount of literature available in this two-volume book. Apart from the two-volume works, he had also a manuscript on geometry and trigonometry, which, however, remained unpublished for over 40 years. In fact, sometime I think it was sort of lost track of, and people were trying to look for it. But it turned out that Krupashankar Shukla, K.S. Shukla, could get access, got access to that. Maybe had access for it over a long time. The exact circumstances are not quite clear, but finally the end of the story is, of that is that work was published by Krupashankar Shukla in a series of papers in the name of as Datta's work, of course, in the Indian Journal of History of Mathematics. So aside from the books and the book in new format, so to speak, Datta wrote a large number of papers. So writing papers in the history of mathematics was not a very standard practice even by that time, but Datta does have a large number of papers, over 40 papers I counted. And so during the period from his short career, because after 47, I think he more or less left the work. Having become a sannyasi. So during 25 to 47, there are 40 papers, and including some of them during the sannyasi phase. The papers are published in many renowned journals at the time, and at least I tried to use them here. Their names will not be familiar, may not be familiar in any case. Especially like to mention two papers which have had a very foundational and important role in and are still widely referred to. So one is on the Bakshali manuscript, which figured in some of the talks today. And there's a very detailed paper on Bakshali manuscript. And another work which I want to emphasize is a paper on the Jaina School of Mathematics. Now, on the Jaina School of Mathematics, unfortunately, there's not too much literature as yet, at least in the systematic form that we now would recognize as a work on history of mathematics. And this turns out to be one of the crucial papers for reference. So with that, let me thank you for your attention.
धन्यवाद प्रोफेसर दानी। और अब हमारा आग्रह है प्रोफेसर के रामसुब्रमण्यन आपसे कि कृपया आज के डिलिब्रेशंस को कंक्लूड करें और आभार प्रकट करें।
Professor Dani. Professor Dani. This is MD Srinivas. I just had a small comment. This was on Parameshwara's name appearing in Ganaka Tarangini and other Kerala mathematicians not appearing. This perhaps due to the fact that Ruskan had edited Aryabhatiya with Parameshwara's commentary in 1874, Hedgekan, and so that was available in that publication of Aryabhatiya with Parameshwara's commentary was available. Therefore, Sudhakar Dwivedi knew about Parameshwara.
Sudhakar Dwivedi does mention Parameshwara, but in kind of half-heartedly in some way, I think. I don't remember now exactly, but Madhava is not mentioned.
Yes. Madhava was not known.
And other other people, Jeshtadeva and so on.
Yes. They are not known, but Parameshwara's commentary on Aryabhatiya was already in print at that time. So,
yeah, I'll have to check.
1874. That's 1874. Yeah, just that.
Yeah. But do you agree that it has somehow has to do with lack of knowledge about developments in the south for the scholars in the north?
Yes. I think after 15th century, scholars in the north are not in touch with the southern.
So that's it's sort of reflected in that. That's what I'm commenting.
It was a wonderful lecture. Thank you.
Interesting.
Friends, I have been requested, for the benefit of those who could not attend fully, to summarize the events that happened today and the kind of messages that were delivered by various speakers. So the event today started with a brilliant address by Professor Manjul Bhargava. Manjul Bhargava started with the remark that there is a dire need today for all of us to look into the textbooks that are being taught, in the schools. So the first statement that he made was that we should try to decolonize. So this is the kind of punch mark with which he started his keynote address today. He also added his own personal experience as to how he was able to gain some knowledge regarding Indian mathematics from his own grandfather. He used the word Nanaji. So unse hum Sanskrit mein hi sikhe the. So this is what he started with. And then he listed out 10 important things which have been found by Indians which should find a place in the school curriculum. So this is the beyond zero, what are the things? In fact, he put it in a humorous way that there are many t-shirts carrying the message, India's contribution is zero. Then he also said, we always knew we were good for nothing. So these are two interesting remarks that one finds in the t-shirts. It has a certain pun, but anyway, so he started with this. So what is it that we know beyond zero? See, India's contribution may be zero, but there is something which is beyond zero. So he listed out 10 topics. For the benefit of those, I'll just very quickly name them. So he said the numeral system. Then he said Bodhayana's theorem. Then the mathematics of language. This he has been always mentioning, I found, even in 2014 when he was introduced soon after the Fields Medal, he was mentioning Panini as the first person about whom the people should know. As a mathematician, he lists Panini. So later also he clarified why he calls him a mathematical genius as well, though he worked in linguistics. Then he talked about sine function. So he spoke about the negative numbers, which has been described by Brahmagupta. Then solution to quadratic equation, binomial coefficients, then Pascal's triangle, as we call today. So in fact, he does not want to call it by the name. So he uses Virahanka. So these are certain interesting things which we find. And then he finally listed this Madhava series for pi also. So these are 10 topics on which about for 35 to 40 minutes. So he discussed on each of them. And he said that this Brahmagupta's contribution has been really remarkable. So as a mathematician who is par excellence, in fact this was even highlighted by Amartya during his talk, So he listed the connections between, sort of nicely brought out by a few points, how one can connect music and mathematics. So this is something which is a very favorable topic, so on which he has delivered a few other lectures as well. So this was a brilliant summary of the major contributions that can be brought to school level and sometimes up to college level. Okay, so all of them should find a very important place in our teaching curriculum. So this is what he was saying. Then during the questionnaire session also there were a few questions regarding how do you distinguish between this language and Sanskrit language. So he said English is just a utilitarian language and Sanskrit has its own beauty. In fact, he was trying to justify how one should start appreciating this language. So this was in short what Professor Manjul Bhargav covered in his keynote address. Then we had a very interesting talk on zero and decimal place value system with a lot of enthusiasm by Professor Parthasarathi Mukhopadhyaya. So he actually started with the inscriptions, so which cannot be by any means dated either forward or backward, right? So these inscriptions are very solid. So from 9th century, how do we go backward and where do we find the earliest evidences? He took back us to the Brahmanas. So slowly he moved from 9th century and took back to Brahmanas whose dates cannot be very precisely fixed by anybody. So anyway, so there are thousands of manuscripts which have to be gleaned by us. So we have not very thoroughly studied. Some of them are documented, some of them are lost. Thousands have got lost also. So this was an interesting talk highlighting how dealing with mathematics has been made exceedingly easy by the formulation of the decimal place value system. This was very effectively conveyed by Parthasarathi Mukhopadhyaya. Then we had, so this was the first talk in the ancient period. The second talk was delivered from Brussels by Jean-Michel Delire. Jean-Michel, so that's how they say, Jean-Michel Delire. So anyway, so this is how I know his pronunciation. So he spoke on this Shulva Sutras. This was a brilliant presentation, very, very systematic, to highlight how certain important constructions have been made by the Shulvakaras. This was a very nicely animated show, which he tried to do with a lot of pains. So he started with the list of scholars who have studied the Shulva Sutra till then, and he has spent decades in studying the Shulva Sutras. So he was expert, well-known expert. I had the occasion to see. I don't think there is anything like this even in India today. Once I went to Brussels and I was so amused to see the kind of play things that he has created based on the Shulva Sutras. Children were playing. That is why I asked this question also. So it was a very interesting presentation. And he also brought out the distinction between Bhumim Karoti, Tadubhayam Karoti. So it was a nice phrase which he picked up from the Bodhayana Shulva Sutras, how he presents this very, very important fundamental theorem on geometry, which goes by the name Pythagorean theorem. So how has it been presented in the Bodhayana Shulva Sutra a few centuries before, in terms of square, in terms of rectangle. He also showed how one actually transforms a certain geometrical object into another geometrical object. This was a very nice presentation. So with various lines coming up on the screen. So it is a thing which one has to really see and appreciate the details which he presented. Then the third talk in the ancient period was by Professor M.D. Srinivas. Professor M.D. Srinivas made a very, very scholarly presentation. So started with the list of texts that are available which deal with this topic on prosody, Chandas Shastra. So there are a class of texts which have been exclusively devoted to the study of Chandas Shastra presented. There are a few other texts which have to do with arts, music, etc., they also deal with Chanda Shastra, like Natya Shastra and so on. There are a few mathematical texts which also deal with this Chanda Shastra. So he made a distinction between them, and he highlighted the mathematical aspects which appear when one tries to find out what is known as prastara. See, prastara, nashta. So there are certain things which are very, very interesting, which will be really nice for school children to learn. So these were connected with what are today called as ranking and unranking algorithms, which people study in computer science. So how the binomial coefficients appear, how the binary number system came up, and how these concepts are fundamental in today's computer age. So all this was nicely brought out by Professor Srinivas. He also made an interesting observation how Donald Knuth sort of praises the work of Narayana Pandita, about which there was a discussion even in the previous talk by Dr. Dani, Professor Dani, last talk. Then this ancient period is over. So in the classical age, there were again 3 talks. The first was by Amartya Datta. Then we had Clemency Montel from New Zealand. Then we had Professor Avinash Sathye, who was from US. So the first talk by Amartya Datta was primarily focusing on highlighting the contributions made by Indian algebraists. So he basically classified the contributions into 3 periods. The first one, he said, it is proto-algebra, so which has to do with very ancient texts. Then he said, so we have the classical algebra or the high school algebra. And then he said the third part, he said it is sort of proto-modern abstract algebra. Okay, so this is what he said. So he highlighted major things that have to be known. So how the notion of the notations that we use today, X, Y, Z, so appear in those texts. So yavat, tavat. So they use the varnas, kalaka, nilaka, and so on and so forth. And he also pointed out that this may be completely new to you, and this may sound quite strange also. But then he also pointed out wherever it was possible that this could also have an advantage. The way they wrote. So today we are used to something, and therefore that may look somewhat odd. But that in its own right, if you approach, that has its own advantage. So all those things were nicely pointed out by Professor Amartya Datta. Then Clemency Montel, who was from New Zealand, so she came live, and she made a presentation on trigonometry in India. So she started with Bhaskara's beautiful verse highlighting the importance of the sine function. So the sine function, so as it is, Tatoyatha Tantubhihi, see, as this fabric, so is crisscrossed with the threads, so too the science of computation that we find in astronomical texts is crisscrossed with sine function. So he gave some beautiful similes. She went to how it has been tabulated by Aryabhata, how it has been tabulated by Brahmagupta, and in Brahmagupta, since he presents only a few values, how he tried to improve the interpolation techniques, the second order interpolation. So all those things were nicely explained by Clemency Montel. In fact, she has this very interesting phrase. So listing all the 6 values, the sign differences, Trimshat Sanava Rasendu Jinatithi Vishayaha. That is all. If you know these numbers, Trimshat. So Trimshat, you take it as base. Trimshat Sanava Rasendu. Sa means you add. Sanava is 39, Rasa Indu. Jinatithi Vishaya, that's all. If you know this phrase, then you know the entire sign table. So she is very fond of this, and she nicely elaborated how with these 6 values you will be able to construct the entire sign table. Whatever be the sign value, you can work out. So this is an interesting thing that she did. And then we had So she actually came up to Nityananda. So that is a very interesting thing. Then we had the presentation of Professor Avinash Sathe. So he, as I mentioned, is from US, University of Kentucky. So he made a presentation on how the Indians have come up with ingenious solutions to handle indeterminate equations of first order and second order. So indeterminate equation of first order, it was first attempted by Aryabhata, and then he sort of went on to Brahmagupta. So Brahmagupta, he actually quoted one or two interesting verses. See how Brahmagupta makes it very interesting by inviting the participant. In fact, he is saying, Kurvan avatsarat ganakaha. See, inspiring. So if you do even in 1 year, I will accept you as a mathematician. So those kinds of phrases he was trying to highlight. So though his was a little technical talk, so he also presented very interesting examples from the text itself as to how they were keen to solve certain problems, to illustrating how they were keen to solve certain problems in astronomy. This kind of techniques got developed. So the Chakravala algorithm was pointed out. Then he went on to say that today, see, though it is called Bhavana, today myself and my student Wang, so we are, so Jason Wang, so he has been working on to improve upon the efficiency of the algorithm which has been developed by Brahmagupta, and then we have Jayadeva, and then we have Bhaskara, and now he has done something which I have not looked into. So he says that he is far more efficient, and therefore he has called it as Vibhavana. Okay, so this is an advance in the technique. So this completes the discussion in the classical age. Okay. So 3 speakers were there. Then there were 2 talks which were focusing on the contributions of Kerala mathematicians. The first one was delivered by Ram Subramaniam, and then it was on the Madhava's infinite series for pi. So how the series is exceedingly important in the development of mathematics. So this was highlighted, and how it has been beautifully codified in the form of verses, and the derivation of the series was also presented. So in a very, very simple manner, how by taking fundamental principles in geometry and certain tricks, so they were able to arrive at this most fascinating result in analysis, as they call today. Today this topic is called mathematical analysis. So it's a very, very interesting thing. Then we had the talk by Professor Sriram. Professor Sriram primarily focused on the derivation of the infinite series for sine function. So the earlier talk was of the derivation of the infinite series for pi. So this talk was primarily focused on the derivation of the infinite series for sine function. So he tried to present initially the mathematical tools that have been developed by them, and then how those tools have been applied by the Kerala mathematicians to successively arrive at the terms in a recursive manner. So he nicely showed the diagrams. So it might have been, those who have not done enough mathematics might have been little complicated, but all the slides were presented in great detail, so that anyone, who makes an attempt, it doesn't require super brilliance or great training in mathematics, but a desire to know how these simple techniques can lead to very complex results. So if you take at the history of mathematics, the way the sine series was arrived at in the Western world almost 3 centuries later is very different from the way these people have approached this problem. So it has to do with simple geometry, close observation, observing similar triangles. So the principle is more or less same. This is true even from the time of Aryabhata. So the Aryabhata's recursive relation of sine function so also makes use of this, and then they make use of it further, they develop and they come up with the infinite series expression. Aryabhatta used it for arriving at the recursive relation for sine function. So this completes more or less three important phases of the contributions that have been made by Indians. One is the ancient period, so before 500 AD, then something like 500 AD to 1300. So we had these contributions, and then the Kerala mathematicians starting from 14th century to 17th century. This is what was covered. One major mathematician, so whom was referred to in a couple of talks, was this Narayana Pandita. So that is something which is remarkable. His work is called Ganita Kaumudi. So that is very, very important. Many of the people mentioned his name. So Professor Srinivas was mentioning, and even Professor Dani was mentioning. So that is something which we could not cover. So that is a very, very important thing. There are very interesting and impressive results in that. One another topic on which Indians have done some remarkable work, which was also not touched upon due to paucity of time, was regarding the cyclic quadrilaterals. So this is there in various texts, starting even from Brahmagupta and so on, Brahmagupta, Bhaskara, and then Kerala mathematicians. They are very interesting result. In fact, it just comes to my mind. There was a person who is an IIT graduate, who is most of them get into this business management, and he was one of the top officials in one of the important international banks. He just came 4 days back, just I'm reminded of that. He came 4 days back and then he said, now I am studying mathematics with my son, who is in 9th, 10th standard. Then he said that there was a problem which appeared in IMO, the International Mathematical Olympiad, which had to do with geometry. And for the past 2 days, I have been really struggling to solve that problem. And finally I arrived at it. I'm so happy, he was just saying. And that he narrated the problem. I just said it has nothing to do with cyclic quadrilateral. Yes, it is cyclic quadrilateral, but somehow. So what I'm trying to say is, so this is a very interesting topic on which Indians have done very important and amusing work. Okay, so then the last talk that we heard was by Professor Dani. So this also is a very, very important talk in the sense of knowing who are our own immediate ancestors who have put all their time, energy, efforts in order to bring the glory of the Indian mathematical heritage to us by way of editing, by way of translating, by way of preparing mathematical notes. So he listed at least 3-4 of them. So that is very, very important to know. So he started with a list of the Western scholars, so who started at the beginning of 19th century. So he listed a few of them, Kaye, Holbrook, Thibault, and so on, Wilkinson. And then he primarily focused on 3-4 of them. One is this Bapudeva Shastri. Then we had this Sudhakara Dwivedi. So these people have picked up the modern mathematics besides their rooted training in the traditional style. So therefore they could make immense contribution. So their immense contributions were highlighted. Particularly he spent a few minutes on discussing 2 important texts. One is this Ganaka Tarangini and Ganit Ka Itihas. Ganaka Tarangini is written in Sanskrit, Ganit Ka Itihas is written in Hindi. So this Ganaka Tarangini primarily presents a few mathematicians, primarily in Sanskrit. So it quotes a few verses here and there. So these things were nicely brought out by Professor Dani. And he also mentioned towards the end that this book, this Ganit Ka Itihas, lists hundreds of mathematicians, or rather who have sort of connected with these kind of studies starting from very ancient period. So that's what he was mentioning. So Aristotle and a few Arabic mathematicians, astronomers, and so on. Okay, so overall, this whole day was a very, very important day where we could gain a lot of insights into the developments of mathematics which happened in India starting from this Shulva Sutra period. So we didn't get into this Vedic text as such much. So soon after that, so starting from 800 so BCE, so wherein this Bodhayana Shulva Sutra is estimated to till about 1800. So we saw a 1900. Even the later last talk was to just once again highlight who have highlighted. So this was a very, very interesting seminar where scholars who have spent decades of their time in studying these texts made their presentations, and therefore, so this I'm sure a few people in the auditorium and a few in the WebEx and YouTube would have, I don't know what the numbers were, but even if it is going to be seen later, so I'm sure thousands of people will be benefited. And the arrangements were very good, so we are very happy. So several institutions have joined hands, so AICTE, Ministry of Culture and so on. The conception is done very well. So this is the first event of what they call as Dhara, and there are going to be several other seminars like this, a day-long seminar on various other topics, so in which Indians have excelled. One will be astronomy, the other could be metallurgy. So these were certain things which were thought about by us. And the Secretary, Ministry of Culture, is very keen, and I was really appreciative of the kind of commitment and the keenness with which he was trying to make this event happen in a very short notice. I thank all the organizers. I'm sure Professor Murthy, Anuradha and various other people, I don't know, have also taken keen interest in making it a very success. Thank you. Namaste.
थैंक यू प्रोफेसर रामसुब्रमण्यन जी। ये इस सीरीज का पहला इवेंट था और कहते हैं कि आगाज अच्छा होगा तो अंजाम भी अच्छा होगा। आप सभी को बहुत बहुत सारी शुभकामनाएं। थैंक यू सो मच प्रोफेसर रामसुब्रमण्यन, थैंक यू प्रोफेसर मुखोपाध्याय, थैंक यू प्रोफेसर मूर्ति एंड थैंक यू सो मच दीपक इसरानी जी, डायरेक्टर आजादी का अमृत महोत्सव सेक्रेटेरिएट। आप सभी से मैं मनीषा दुबे अनुमति लेती हूँ। बहुत बहुत धन्यवाद, बहुत बहुत सारी शुभकामनाएं। नमस्कार, जय हिंद। थैंक यू।